Welcome to a C++ fundamentals course. This video is going to be mostly about teaching you the basics of C++, but I'm attempting to do it in a way that you grasp more of the fundamentals, the why and the how, rather than just the code. I don't know how well it'll work, and I don't know how much people even watch this, but I should also specify that this tutorial is not super beginner friendly. It kind of assumes that you have a little bit of knowledge about computers already. Not a ton of knowledge, but at least a tiny bit of basics. I also do recommend that you should watch this probably at 2-speed, instead of listening to me trying to stutter my way through this. And this is a perfect example of why you gotta listen at 2-speed. But this course, as I said, is mostly about learning fundamentals of why and how. And so kind of if you want to learn the more complicated concepts, or not necessarily the more complicated concepts, if you want to learn more of the code and new different ways to do things and different functions and stuff, a different tutorial is better. If you want to get geared up to understand exactly why everything works the way that it works, that's what I'm trying to make this tutorial good for. That's enough with the introduction. Let's go. Let's type in to our search bar Visual Studio. And right here, we're going to see Visual Studio IDE. This is called IDE, an integrated development environment. And what this is this is a piece of software that allows you both to edit code and allows you to run that code and debug that code and do whatever else you want with that code. So going down here, you want to press Community 2019, wait for it to download, which it will do in any second. I already have it downloaded, so I'm going to press cancel. It's going to open up a window that looks something like this. Let's take a look. Visual Studio Installer. Now, it's going to ask you something like that. We are going to be building desktop apps with C++. So you just want to select this package right here and then install. All the rest of these are for developing different softwares or using different coding languages. So right now we don't need these. I'm going to press close because I have it finished. Once this is finished though, you can close this and you can go to Visual Studio 2019. This will bring up this window and it'll go right here. These are random projects that I have. Let's press create a new project. And we're going to start with an empty project for now. We're going to be building a console application, but we're going to be starting with an empty project so you can know how this works from scratch. Let's name this tutorial, and it's going to be placed in this folder. Create, and it's going to bring up this, which looks extremely ugly. I'm wondering what's going on right now. Let's change this to probably that. That looks much better. Okay, we're going to bring you up with a window that looks like this. It's a little bit intimidating, but we don't have to worry about most of this. Let's look for now to this side right here. This is the Solution Explorer, and when you make a project in Visual Studio, it splits up your project into small pieces called solutions. So this solution is called tutorial, and it has all these sub parts. In the source files, directory right here. This is not a real directory, but let's call it a directory. We're going to press add new item cpp file. It's called .cpp, and a generally C++ files come with the extension .cpp. So this is going to be that. Let's call it tutorial.cpp. Press add, and we're going to get this text editor right here. And it's completely empty. So let's see, what do we have to do to write our first C++ program? We're going to write the most basic C++ program possible. Int main and I'm pretty sure that will just run and it'll stop. Yep. So that window that popped up, that was a console created by Visual Studio that gives us information about our program. And it printed out a whole bunch of extra stuff that this program didn't actually do. What this program does right now is it runs and then immediately finishes and returns, and it finishes and indicates that it succeeded. Now let's zoom in. That's Control Shift period, and right here we're going to see int main. Let's figure out what this does. So main, initially, this is what's called a function. Now C++ is built up with what is called functions. So if I wanted to make another function, I could say int Geobor, and I could provide something like that. You notice this time that these curly brackets are in a different position. That's because C++ is what's known as a free-form language, meaning that you don't need any, you don't need to put these in any specific order. This would be just as valid. Or that. Oh, actually, no, this does need a space. But that would be just as valid. And that would be the same with main. But generally, it's good practice to write your code, in a little bit better of a style because it just makes it more readable. So normally when you see any function, it'll generally be laid out like this. Now let's explain what everything is. Main is the name of the function. Int is what's called a return type, and we'll get into those later. These parentheses are what's called function parameters, which we'll also get into later. And this is called the function body. So let's see, what is a simple statement that we can place into this function? Return 0. So what this statement does, this is what's called a expression. It has this return keyword. What this return keyword does is it stops what the function is doing, and then it returns to whatever called the function caller. In this case, what would call the function would be Windows. When we run this program, would call the main function, and the main function would give Windows back a 0. Now, I said that Windows would call the main function. The reason for that is because the main function is a special type of function that when you run your C++ program, it automatically looks for the main function, and that's where it starts your program at. So without this main function, if we just had another function called Geobor, this would not do anything. This is valid, but running this would not do anything. So right here is we put the semicolon, and that is to indicate the end of an expression or a statement. let's take a look at another statement. Let's say int number. Now, what this does is we have what's called a variable. Now, a variable is an object, and you'll hear me refer to lots of different things as objects. That's because C++ is what's called an object-oriented language. And objects are the fundamental data types that everything builds upon. So number is an object, it's a variable, and it has a type of int. We'll figure out what that means later. But let's see what happens when we run this program. Again, this is all debugging information, so we, after this, press any key to close this window. That's what our program does, and we can see that it did nothing. Okay. What we can say is, let's say int number equals 12. So now we're saying that this number is equal to 12. This number object holds a value of 12. So let's see if anything happens now. And no, nothing happens. Okay, let's figure out why. Well, let's see what this program does. If we take a look at what this program is doing, it's saying that we have a number object right here of type int, and it equals 12. So number equals 12, and that's it. It's not doing anything else. It's not telling us to, for example, print anything out onto the console window. So it's not showing us anything. Let's allow it to do that. So the way we would do that is at the top right here, you would put a statement called include, and then you would put these angled brackets and put IOstream. IOstream standing for input output stream. Now int number 12, we're going to press enter right here and put another statement. This is going to be std cout, and then these two symbols, and then we're going to say number. Now this, I'll explain exactly what this does. Let's see first what happens when we do this. We see that we have 12 printed at the top here because number is 12 and we're telling it to cout 12, whatever that means. Let's figure out what this means piece by piece. So include is what is called a preprocessor directive, and that means that before the program looks at any of this main function, it will look at this include statement and it'll decide what to do with that. So it'll use whatever this include statement is telling it to do, and then it will continue and compile the rest of the program. And I didn't get to what compiling was. Let's figure out what that is. Compiling is a process where when you run this program right here, what your computer does is it looks at this code right here and it thinks about, well, instead of just running this code how it is, it needs to be able to translate it to machine code or closer to 1 and 0s. Not exactly, but closer to, so that it can run it without having to figure out what this code means every single time, because machine code is just instructions directly for your computer to execute. And so the compiler will look at this and generate those instructions exactly based on what this code is telling it to do. This preprocessor directive runs before that compiler. So this preprocessor directive, if we look at it, include, so include, you can think of it as actually include. We're including right here IOstream. So this IOstream, this is a file, and include is saying to the preprocessor which interacts with this include statement, the preprocessor will take the IOStream file and then copy its contents right here at the position of this statement. So that means that what we're doing here is that our program is now using all the code that's in this IOStream file. What that IOStream file contains is what are called objects and functions and classes. And so an example of that is cout. Cout is an OStream object. And so this cout comes from the IOStream file. If we delete this, you're going to see it's telling us that there's an error. It's because it can't find the cout object because it doesn't exist outside of the IOStream file. So now that we're copying the IOStream file in here, we can use cout. Now let's check what this std is. Std is what is called a namespace. A namespace is a collection of code that is organized into pretty much a name. So a namespace will include a whole bunch of code that kind of relates to each other. So if we include a statement like using namespace std, this is not a preprocessor directive, as you can see. It doesn't have this hashtag or anything like that. Using namespace std, and as you can see, preprocessor directives do not require the semicolon. This does though. So if we say using namespace std, then we no longer need this std thing right here. And so that's because our program knows that we're already using this namespace called std, and you can think of namespace as like what it literally means. It's a space filled with code that is given a name. So this no longer needs the std thing before it because we're already using namespace std. We can also do something like using std cout. And so we don't have to say using the entirety of namespace std. We can just say that we're only using cout from namespace std right here. And that will say our cout right here is completely fine. We can press F5 to run the program, and you see it still says 12 up there. Now let's get rid of this. Generally, you don't really want to say using namespace std, and the reason for that is, imagine you have another piece of code called cout and you want to be able to use that. Well, if you included namespace std, or included is not the correct word, if you specified using namespace std and you had another piece of code called cout, the compiler wouldn't know what you're talking about by cout. It wouldn't know if you're talking about the cout that is defined in namespace std or the cout that you created. But we're gonna preface cout by putting std cout, so it knows that the cout object is in namespace std right here. Let's press F5, still works. Now imagine we want to add some other stuff, right? So let's say that we have another number called, let's call it int number 1, and this is going to equal 13. Something I forgot to include was that those semicolons at the end of every single line, those are what end statements. So when you finish a statement such as int number 1 equals 13, you need a semicolon at the end of it. Another thing that I should mention is that variable names such as number and number 1, they cannot start with an actual number. They have to start with a letter or an underscore or something similar to that accord, right? What we can do, we can add another 2 of these little angled brackets that point into the direction of cout, and we can specify number 1. Okay, so let's see what this does. It prints 1213 with no spaces, and that's not exactly what we want, right? So how do we add a space to that? Well, let's do this, and let's add just a space like that. And so now we're printing number 1 and then a space, or number, then a space, and then number 1. Let's start this. Now we have 1213. Let's see exactly what this cout thing does. So if we have another statement here, std cout, what if we do, once again, number? And let's run this. 12, 13, 12. So this, as you can see, even putting it on a new line right here, did not specify a space or a new line. It didn't print it on a new line. Let's see how we would get that new line. Well, there's 2 methods. Either you can do this and then specify std end line right here. So std end line, you can see that this end line object right here, whatever it is part of the namespace std. Once again, we're using that once again. And let's see what let's see if anything happens from this. Well, you can see it printed a new line right here. It's an empty new line, but it's a new line nonetheless. Let's do std cout. This time, what I'm going to see out is Geobor. And you can see this Geobor is on that new line. So let's go in order and check exactly what this is doing. So this cout object is what is called an outstream. And stream is kind of like a queue of data. And you put stuff into that queue, and that queue will be looked at by something else, and it'll be decided on what should happen with that data. On the outstream, it is kind of decided that whatever's put into the outstream should be printed out onto the console right here. So this cout is part of that, or is places objects into the outstream. This number right here, if we check, is we can see that it has these little 2 arrows that are pointed into cout. What this does is it takes the contents of this number and it copies them to the outstream. So that means that whatever is in number, if we check what is in number right here, 12 is a number. So it takes 12 right here and then copies it to the outstream. So that means that now that 12 is in the outstream, the program will decide to or whenever the object that references the outstream, whatever manages the outstream, will look inside the outstream, see that number is inside of it, and number equals 12. So it'll see that 12 is inside of the outstream, and then it'll print 12 onto the console. What this outstream object also does is after it finishes this statement right here, it puts number into that outstream right here. It takes this whole segment and then it returns this. So after it finishes this whole statement right here, you can think of this as almost like, you know, this is what's called an operator. It's almost like a plus or a minus, but in this case it doesn't do like a plus or a minus. It puts stuff into the outstream. So after this is finished, this returns the outstream once again. So this whole statement turns into std cout pretty much. And so now that number is in the outstream and it returns the outstream, now it will look at the next section of the code, which is this. Remember, this section is now only the outstream. This section is the whole code. And it'll look at these and it'll say, well, okay, now we have to write this space into the outstream right here. Number is already in the outstream, and the outstream is now on the left side of this operator right here. So this space will be written into the outstream right after number, and then after that it will return, this whole thing will turn into the outstream once again, and then it will look at this section of the code and it'll say, well, whatever, for number one, write number one into whatever is on the left side, and that is the outstream. And it'll continue going until it hits this std end line. What this std end line does, this is what's called a manipulator, and it manipulates the stream so that it will end the line. This end line also, what it does is it does something called flushing the stream, which pretty much just deletes all the data inside the stream, get it ready for new data to go inside of the stream. So if we look back again, this outstream, first, number is written to it. This whole thing turns into the outstream. Then the space is written to it, and this whole thing turns into the outstream. Then number one is written to it, and this whole thing turns into the outstream. And then end line is written to it, and end line manipulates it and adds a new line and then clears the outstream, getting it ready for some new data. After that, we have this right here. This cout object, it's a different instance of cout, you can see right here, but cout refers to the same outstream every single time. If the outstream still has data in it, most of the time it won't, but if the outstream still has data in it, then when you call cout again, it will reprint everything that's in that outstream. It won't, most of the time, your outstream won't have extra data in it, and I don't know really what flushes the outstream normally, but this std end line manipulator flushed it right here. So when we write Geobor to the outstream right here, it will just add Geobor to it, and now it's empty, so it's just going to print Geobor. Let's look at another way to make a new line. Right here, instead of putting std end line, we can put this, and then we can put that. Now, what this does is this is what's called a new line character. So you can almost think of whatever is in these parentheses as a word, but instead of a word right here, we have a new line character. So this new line character is prefaced by a backslash, and this backslash indicates that whatever comes after it is not part of the word. So if we put a backslash right here, it would be saying that that B is not part of the word. That B does something else. In this case, it's saying that that N is not part of the word. That n is doing something else. If we wanted to write actual backslash, right? Because if we put here, if we wanted to write Geobor with a backslash at the end of it, that wouldn't really work. It's giving us an error. So how do you write a backslash? Well, you just write backslash, backslash, and it reverses it. So this backslash right here is saying that this backslash right here is an actual word. Normally this backslash says that the letter that comes after it is not a word, but since what comes after it is another backslash, it's saying that it is a word. So this backslash, backslash signifies that there's only one backslash that isn't a literal character. If we go back to here, this is what's called a new line character, and when your computer reads a new line character, it knows that a new line character acts like almost any other character. It acts like a G, a B, a space, but this new line character, what it tells your computer to do is to write a new line instead of any of those. So if we run this once again, you can see that there's also a new line. Now, this new line character, let's actually remove it so you can see more clearly that there was a new line that time. Right here, there's no new line. Geobor is printed right after the 13. How do I do this again? There we go. I was being kind of dumb. But right there, there's a new line character. And you can see that it's now on a new line. This new line character does not inherently clear the outstream. This new line character only signifies that there should be a new line. In this case, there's probably some other operation somewhere that is clearing the outstream automatically. And I don't know what exactly it is.
I want to let you know episode 2 came out today, so I'm going to watch it.
Episode 2 came out?
For Attack on Titan. I only watched dubbed.
Oh, dubbed. Yeah.
That's why I'm behind.
Yeah. I think episode 6 comes out for me.
It was amazing. We'll see what happens in episode 2.
Geobor, or something similar to that. But the outstream was cleared at a certain point there. The new line character doesn't specifically do that. The std and L manipulator does specifically tell your program to clear the outstream. Let's not get rid of some of this. Let's say, what if this number and this number 1, we deleted them. Now, obviously, these do not exist. Running it will give us an error, right? But what if we put them here? And let's try to run that. We're still getting an error. Well, that's because this program is read from top to bottom. So the program will call main, and then it'll look at this right here. It'll say, okay, so we got to write number into the outstream. It has no clue what number is because it's trying to write number to the outstream before we say what number is. So you cannot have variables like that are not defined. Now, another thing we can do is, what if we say number is, instead of 12, number is 6 plus 6, right? And when I press F5, it still says 12, because what this equals operator does is, remember how this operator right here for outstream, it returns this side turns into outstream. A similar kind of process is happening here. When this equals operator is looked at, or when C++ looks at this entire statement, we'll see this equals operator, and it will turn this right here into just a 12 instead of a 6 plus 6. And then it'll say that number equals that 12. That's how operations usually work in C++. So generally, they complete an operation, and then this whole statement right here is turned into whatever is the result of that operation. Same thing with cout. This whole cout operation right here turns into whatever is the result of this operation. And the result of this operation is cout with number written to it. And so now that this result is cout with number written to it, this space can be written to it too. Let's keep this at 12. And let's say, what if we had right here number plus 6? Well, let's run it. And let's see what happens. 18. Again, this number plus 6 turns into an 18. And then that 18 is written to cout. That's how pretty much every single operation works in C++, and it depends which of these operands you are using, which of these operators you are using. That determines in which order they're evaluated. So you see this time, or in this order, it sees this whole statement right here, and it first evaluates the number plus 6, and then evaluates the result of number plus 6, this operator, and cout. And C++ will decide based on which operators you use, it'll decide which order to evaluate it in. And the way that you can override this is, for example, you could put parentheses like that. And this is just like math. If you had, ignore that error for now, but if we had 12 plus 12 minus 6, or no, let's do 12 minus 12 minus 6. Well, if we evaluate 12 minus 12, this is 0, minus 6. If we evaluate it just from left to right, this will give us a value of minus 6. Now imagine that we put parentheses like this, right? This is just like what you learned in math class. This is going to say 12, and then we specifically put parentheses, so we're specifying that we want this whole operation, whatever this statement is, to be 1/2 of this. We want it to be one operand, which is, 12 is an operand, and this whole section is an operand of this minus operator. The parentheses is saying that we want this whole statement right here to be one operand of the minus operator. And so if we evaluate this first, this 12 minus 6 is going to give us 6. So what this statement is saying is 12 minus 6. So this will give us 6. This will give us minus 6. Now, let's just put this back to 12. Now, if we check what's happening here, this is giving us an error, and we'll see why. Right here, what we check is our first operator is not actually this. It is this operator right here. And this plus operator is telling us, well, take whatever is inside of this and add 6 to it. So if we remember, what does this return? This operator right here, these two arrows pointing to the left, this will take a number and write it to the outstream and return the outstream. So this whole operator right here, or this whole statement right here, is equivalent to the outstream with number written to it, right? And so once it evaluates that, it'll say add 6 to that. Well, it's not trying to add 6 to, it's not trying to, if we did this, for example, this would work because it would be writing 6 to the outstream, right? But the outstream, it doesn't know what a plus means. An outstream doesn't know what a plus means. It doesn't know what you mean by trying to add 6 to the outstream, because you're not trying to add 6 to number anymore. You're trying to add 6 to the outstream, and that it doesn't know what that means. You can write 6 to the outstream. You can read 6 from the outstream. You can't add 6 to the outstream. And then right here, if we say, even imagine that this somehow, somehow passed. Now this would be an error though, right? Because this would be trying to write whatever this is to 6. Or whatever the result of 6 plus the outstream is, which doesn't make any sense. You can't write a space to 6 or a number or anything like that. That's why you can't have parentheses like this. I did say though that we could do something like this though. And in this case, you actually really wouldn't need the parentheses though, because it's going to evaluate this number plus the cout. It's going to evaluate that initially anyway, so you don't need these parentheses. But if we did this, now you can see that it's going to say 12, 6, space 13. And that's because this number equals 12, and then there's a 6, and then a space, and then number 1 equals 13. And if we do plus, remember, it's going to take this whole statement, and it's going to use that as the right-hand side of this operator, giving us 18 here. That's how statements generally work in C++, which is good knowledge to know, because a lot of confusing things happen based on the way statements interact and not knowing how they interact. Let's take a look at some other things here. We have this int specifier, and this int specifier is what's called a type specifier, or yeah, that's a type specifier. And this is saying that number is of type int. Int represents, or it is a base type. That means it's included with C++. And it is a type that indicates a section of memory that it is a type that indicates a section of memory that is 32 bits long, or 4 bytes long. And this section of memory, if we classified this section of memory as an int, this would be a number. That's what this int is. It says that number is a section of memory that is 32 bits long. And so number 12, if you remember how binary works, let me check if I can remember how binary works. Well, this number would be 0. This would be 1. 2 would be here. Right here, that would be 3. I think this is, I'm bad with binary, but we can imagine that if this was a 2, then what would be happening in here is that it looks like this. And then when we add 1 to this, and turn it into a 3, it adds an extra 1 right here. That's what this means. But looking at this, what happens if we fill up all of these zeros with 1s? What happens if we get to the maximum value possible? Imagine we're at this value and we add 1 to it. What happens? Well, this does what's called overflowing. These all reset back to zeros. And that indicates that if these are all 1s and these reset all back to zeros, that would mean that whatever this number is, plus 1 equals 0. And 0 would equal that. So this plus an extra would equal 0 because this plus a 1 would reset everything back to 0. If you've ever heard of integer overflows or like 32-bit integer limit or anything like that, that's what this is. This is an integer overflow because an integer cannot hold more than whatever is right here. This number evaluates to roughly 2,147,000,000. So that is the maximum size that an integer can hold. Now, if we actually look at this, right, this is 32 bits. And if we go into our calculator, right, how you would identify 32 bits is each bit has two states, either 1 or 0. So you can say 2, right, to the power of 32. So 2 to the power of 32. That's because each bit has two states, and there's 32 bits. So it would be 2 times 2 times 2 times 2, 32 times. If we see here, though, if you did that in your calculator, that gives us 4,294,000,000. So that is double of what this can hold. And that is because there is something called signed integer types and unsigned integer types. Now, this right here, if I didn't specify it, this int is equivalent to integer. I don't know if that's how you spell it. But that int means that this is an integer. And an integer is pretty much just a number in computers. So we saw, though, that this 32 bits should be able to hold, theoretically at least, should be able to hold 4 billion instead of only 2 billion. So why is it the case that it can only hold 2 billion? Well, that's because by default, int is what's called a signed type. And that means that these bits are not actually laid out like this. They're laid out more like this. And that means there is, so 8 bits right here, 8 bits right here, 8 bits right here, 7 bits right here, and then a sign bit. This sign bit says whether the number is negative or positive. So if this is 1, then that would be negative 2 billion. And if this is a 0, this is positive 2 billion. And there was some extremely smart person at some point that created a standard that decided that this is what an integer should represent. So much smarter than both me and you. So that's what they decided. The thing is, your computer doesn't know that, right? Imagine you have something like this, right? Your computer doesn't know that that's a signed bit. It thinks that the data looks like that. And so when you add 1 to this, it flips this signed bit back to a 0. And so that would make it so it would go to a positive. If this was a negative and you added and you flip this bit at the top right here to a 0, the way that you would flip that bit at the top to a 0 is this number right here would represent, I think, that number should represent, I think, -1. Not -1 billion, but I think this number right here represents something like -1. And so when you add an extra number to it, right, all these reset back to zeros. Let me check if I have zeros copied. So all those reset back to zeros, and this -1, now that this sign bit is no longer a 1, this -1 knows that is no longer negative. And then it looks at the rest of this and sees, all right, what number should I be? Well, these are all zeros, so I should be a 0. And that's how that works. If these were all 1s, so I'm going to try to do that now. So if those are all ones and that's a 0, this represents positive 2 billion. Now, what happens when you add 1 to this? Well, normally, right, if you think about if the binary looks like this, right, if you add 1 to this, right, all these ones would reset back to zeros, and then this would turn into a 1. So it would look like that's what would happen if you would add 1 to that. And then once these turn back all into ones, you keep adding. And it gets to this point, and you add another 1 to this. Well, you can imagine, right, that the next bit would turn into a 1, and these all turn into zeros. And what does this represent? Well, when it's looking at this number, it'll say, well, the sign bit is a 1, so we know we're a negative, right? And let's take a look at these. The sign bit also indicates another thing. This, instead of this indicating 0, this indicates the lowest number in the signed values. So the lowest number would be 2 billion, right? Roughly 2,147,000,000. So this would be equivalent to negative 2 billion. And as you add to this, as you add 1 to this, and then you add, 2 and 3, this is going to be counting down this negative 2 billion till you get back up to the point where these are all ones. And it looks like this, and then you add another 1 to it, and then it resets back to 0, and it resets back to a positive 0. That's how generally assigned and unsigned values work, roughly. And so when we're saying int number 3, we're saying that this is a 3 that is not a negative, so it would assign to that number object, it would assign a piece of memory, a piece of RAM that looks like roughly like this, that, and that would be the sign bit. And since it's not a negative, that sign bit is going to be at 0. And that 1 indicates that that 1 right there indicates that this is a 3. A 13 would be equivalent to this. If this was a -3, then all it does is it flips this sign bit and then changes this to whatever would be -3, which would be a whole bunch of ones, which I don't feel like writing out. Now, what if we write right here, unsigned, right? I was telling you this is the signed bit. What if we write unsigned? Well, what this does is it gets rid of the signed bit. And now, this looks like just a normal piece of memory. This is a normal 4 bytes. And so you can no longer have negative values. This now only goes up to 4 billion, right? An extra 2 billion, double the size, because there's an extra bit. So this would go up to positive 4 billion. And then when you add 1 to it, it would reset back to 0. Because if you imagine these are all ones, and you add 1 to it, all of these are going to turn all the way back into zeros. And what those all as zeros indicate is just a regular 0. There's also a shorthand for writing unsigned integer, just unsigned, because normally when people are talking about unsigned, most of the time they're going to be using an unsigned integer. Now, what if we write long? What this long is this is just like an integer, except it's saying that instead of 32 bits, it's 64 bits. So it has an extra 4 bytes to work with. And this long is normally signed, so it does have one signed bit at the end, just for negative and positive values. And this would work exactly the same way as an int, just being able to hold much higher values. We can also say unsigned long, and this would have a long without the signed values, without the signed bit. We cannot just say unsigned, because if we just say unsigned, it thinks that we're talking about an integer. So we got to say unsigned long. And this number variable right here, this number object, would represent this piece of data. And it's a similar process for pretty much everything else. So if I look up on my other monitor real quick, let's move this here. 32-bit integer limit. We see that the 32-bit integer limit is this number right here. I'm going to get rid of these commas and spaces. And we're going to say this is an int, right? And we're just going to only print out that. The reason people say print instead of cout is because print is usually print is a lot easier to say, and there's a very simple programming language called Python, which instead of cout has a little thing called print that lets you output the result of something, and that print just became very universal for saying print out something onto the console. I also want to specify that the reason this is called cout is because C stands for console out, so you're outputting it into the console. But let's get back to what we were doing. Int number equals 2,147,000,000, right? If we run that, right, 2,100,000,000, it works perfectly fine. Now, what if we do that, right? I told you it can't do that, and it says minus 2,147,000,000 because the signed bit flipped once we added 1 to it, right? So if we did long, which is an integer that just has 64 bits, it would, at least it should, unless, well, okay, it did not work. And the reason for that might be because on some machines, longs and ints are the same size. So what if I said long, which is even longer? Now it works. So it just so happens, I guess, either one of two things happened. Either longs and ints are the same size on my computer, because they're different sizes on every computer. I just put the usual size that they're at. Or I got it wrong. It may be that ints are actually 16 bits and that longs are actually 32 bits or something like that. Another thing that could have happened is that somewhere along the way, the compiler automatically converted my long into an int, because it likes to do that, because ints for the compiler are usually easier to work with. And so at any chance it can convert something to an int, it will do that. And that a lot of the time will cause an error. We can see here that long worked, and it gives us this 2,147,000,000 with an 8 instead of a 7, because a 7 is the maximum value for an int, and an 8 is the maximum, or an 8 is just 1 plus that maximum value. We can also say right here, remember I said that unsigned ints can hold up to 4 billion. So if we put unsigned right here, this will also properly output that. If we just put a regular int, it's going to be a negative sign once again. So that's how data types work. There's a whole bunch of different data types, but we're working right now with ints. Now, let's see. What do we want to talk about? Well, let's talk about a new data type instead of an int, because ints are kind of getting boring. At the top right here, well, actually, let's not do that quite yet. Let's say, put these double quotes, because these double quotes are used for a data type called a string, right? Geobor right here is a string. If we output this, it's just going to write Geobor up to the top right there. And what you can do with strings is you can add stuff to them. So if we add, for example, a space, and then we say another space, or not another space, but is, and then let's do this again. Really epic. And I'm pretty sure this will not work. Yep. The reason for that is you cannot add, this is what's called a string literal. That means that it's not an object called a string. There's no, like, there is no, string object Geobor. There we go. I'm kind of autistic, so you gotta forgive me. Right here, this is not, proper syntax, but there's no string object called Geobor. So when we're trying to add this space to Geobor, it doesn't know what to do, because when you add a space to a string, it's trying to find the object that the string represents and then add on a space to that object. The thing is, this Geobor right here, this string does not represent an object. It's what's called a string literal. So this is only just a word by itself that's not tied to any object. That means that you cannot add any extra characters, letters, anything to it. If we wanted to add an extra letter or character, right here you can see that we're using strings, but string is a data type that is included in outstream, or these string literals. If we wanted to make our own string objects, we have to do this include string. So what this does is this, if you remember what include outstream does, string does a similar thing. String includes a library that gives us access to strings. So by default, outstream gives us access to these string literals. But if we wanted to use string objects, right? If we want to use a string data type, we would do something like that. And then so by default, you can usually use these string literals without including string, because outstream will include those string literals. But if you wanted to use right here, this string, this std string, that would be included in this string file right here. A lot of the time, well, let's not get into that. Something I wanted to mention as well is that this std namespace right here this stands for standard library. So when you hear somebody talk about the C++ standard library, or what is in the standard library, you should use the standard library header or something like that. They're talking about std namespace, usually. If you remember, this equals sign is just like an operator, just like this. Another operator that we didn't take a look at is actually these double colons. These double colons are also an operator. What this operator does is it says find whatever, or look inside of the std namespace and find string, right? Imagine, right, if we had something like let's copy this just so we don't have to mess up our code. This is not going to be valid syntax, but right here, imagine we have, right, another object inside of our string. So imagine we have our std namespace, then we have like another namespace or something else, and then there's another object inside of it. This will work kind of like how this worked. So initially, it's going to look at this whole thing, and it's going to start with this operator right here. Well, it's going to say, okay, so find kjsd, whatever that is, inside of this. And it's going to say, well, we need to find out what this is. So take this operator, or find string inside of std, and then return whatever that is as this whole statement right here. And then once it does that, it's going to say, okay, find kjsd on what inside of whatever std string returned. That's how that operator works, and that's called the scope operator. You can just call it the scope operator. Let's get back to this though. Let's see what we're saying right here. So we're saying inside of namespace std string word. If we remember, we said int number, and we said, for example, equals 12. This int number, if we remember correctly, this int was the type of number. And we said that number equals 12. If we look at here, this is the exact same thing. This word is of type std string. Whatever std string returns, std string returns string right here. And so that means that word is of type string, and word equals Geobor right here. So that means we can also do something, maybe make it a little bit clear. If we remember we put using namespace std, but we also did something like this, using std string, and then we can put a colon like that, and we can say that. So it automatically knows to just find whatever string is and just use string as that. So now we can see that int number, so number is an int and word is a string. If we didn't have this and we just put std string, that's the exact same thing. It just finds out whatever string is inside of std, and then it assigns whatever that is to word. Now, word is not a default, or string is not a default data type. String is included inside of the standard library, which is std. So that means it is there's somebody else who wrote a whole bunch of C++ code that says what a string is, for example. So somebody else decided what a string represents. So this word right here of type string equals Geobor, and if we output word right here, we can see it says Geobor, right? Let's get rid of this int number because we're not even using it. Remember I said that we can do something, or remember in the beginning, I don't know if you guys remember, but we did something like this. std string word. We're not saying that word equals anything, so let's run. Let's see. Nothing is outputted. Now that's because there's two different types of statements. There's initialization statements and there's assigning statements. So we can say word equals Geobor, right? And notice right here, we're not putting string word, right? And we'll see that this still works. Word equals Geobor. The way that this works is initially when we create a variable called word, once we create this word object, we have to say which type it is. And in this case, the word object is of type string. But moving forward, you no longer have to initialize that word. It always knows once you initialize it right here. This is initialization. This is an initialization statement right here. It knows what type word is, so it can now say assign whatever Geobor is to word. It already knows that word is a string because we say that word is a string right here. If we said, for example, that, well, it's giving us an error because it's saying assign Geobor to word, and then afterwards it's initializing word. It doesn't know what word is right here. So right here, it's called an initialization statement. An initialization statement has to take place for every single variable that you make. And then word right here is an assignment statement. This just assigns a value to whatever word is. It doesn't initialize word. It doesn't say what type word is. If we say std string word equals Geobor, this would be valid, except we are trying to, right here, this is valid, and now this is invalid, right? I don't know why the colors are not updating, but right now, the reason that this is invalid is because what this is saying is create a variable called word of type string right here. And then what we're saying again is create a variable called word of type string. This is not, we're saying to initialize a variable that already exists. We can't do that. What we could do is we could just say word equals gamer, and let's put this in. Well, that didn't work. Word equals gamer. So the reason this works is because word right here is already initialized, this initialization statement, and then it's assigned here. Let's run this and see what happens. So it says word equals gamer. The reason that this is not like Geobor and then gamer right after it, the reason we don't see like, the reason we don't see anything like that is because what this equals says is replace whatever word is with gamer. So whatever word contains, replace it with gamer. It's not like this operator, which writes whatever word is to cout. It just, this equals operator replaces whatever is inside of word with gamer. If we did, for example, plus equals, we see Geobor gamer, right? Because what this is saying is take word, right, and add gamer to it. Plus equals is equivalent to word equals word plus gamer. That's what plus equals does. And it's actually a little bit more efficient than saying word equals word plus gamer. Plus equals is a tiny bit more efficient than that. So it's generally a good idea if you can use plus equals to use plus equals. Plus equals also works with integers. Like if we put int gamer equals 0, gamer plus equals 1. What this would mean is that this is not valid syntax, but this would say that gamer equals 1 because 0, or this would be gamer equals gamer plus 1. So gamer plus 1 is 1. So up here though, this does the same thing. So word equals word plus gamer. If we remember correctly, we were talking about how you cannot do something like that. And remember, we cannot do Geobor plus gamer right here. That doesn't work. We can do like, 1 plus 2, but we cannot do Geobor plus gamer, because in the context of strings, what this plus operator says is take gamer and then add it to the end of whatever object is on the left, right? And in the context of numbers, what this plus operator is saying is it's not saying add 2 to 1. It's saying, well, it is saying add 2 to 1, but it's not adding 2 to the 1 object. It's saying take whatever this is, evaluate it, and return 3. So what this is saying right here is it's saying take the object Geobor, add gamer to it, and then return Geobor, right? Geobor, though, is not an object. Geobor is not like a variable called Geobor, so we can't add anything to Geobor. It's what's called a string literal. A string literal is not assigned any name right here. This is just a string that contains Geobor. We don't know what this string is called. If, for example, how would we see out Geobor right here? I don't exactly know. Geobor is not assigned to anything. So this is what's called a string literal, and this plus operator in the context of strings wants to return the left hand side of the operation. So this plus operator wants to take whatever is on the left hand side, add onto it whatever's on the right hand side, and then return back whatever's on the left hand side. Since this on the left hand side is not an actual object, it doesn't have any name, it doesn't have any specific value, it's a string literal, then it can't add anything to it because it is not named and the program doesn't know exactly where it is. So we could, for example, though, replace this with word, because now what this is saying is it's saying take word and add onto it gamer and then return word. So this whole thing equals the word object with gamer added onto it. And that's different from numbers, where 1 plus 2 doesn't equal 1 with 2 added onto it. It doesn't equal the 1 object with 2 added onto it. No, it just equals 3. It just equals a new object. It just equals a new value 3. It doesn't equal the 1 value with 3 added onto it or anything like that. Or rather, it doesn't equal the 1 object with 2 added onto it. It just returns a new one. That's not the case with strings, and that's something that's important to remember. Now, what we're seeing here, though, is that word equals word plus gamer. So this should return Geobor gamer, and that's what it will do. Right here at the top, it printed Geobor gamer. Let's get rid of this right here. And I'm going to say something else. Remember, we use these using declarations. A good use for using is what I showed before, std string. If you know you're going to be using string a lot, then you can say using std string, right? And instead of putting std string everywhere, you can now just put regularly string, because this using declaration will say you're using the object that's inside of that, whatever this std string expression returns. Now, you can also do something else. you can say using std string equals gamer. I don't know what type of or maybe I got the syntax wrong. It might be using gamer equals std string. Yep, that's how it is. So what this means now is that when you use the word gamer, it is using whatever is inside of std string. So now string doesn't work, right? Because we didn't say that we're using std string. We're saying that we're using gamer, and gamer equals std string. So if we put gamer right here, now we see that it works, because if we hover over this, it'll tell us that gamer is right here, and we can see that gamer is std string. So now word is still a string object. It's just referenced with the identifier with the identifier gamer. Let's get rid of this. Let's get into something a little bit more interesting. But before that, let's do one more boring thing. If we remember right here, when we were doing this I just want to check if this works. I'm not sure if this even works at all, first and foremost. Yeah, so functions need function bodies. This should work. I don't know why it's yelling at me. Yeah, it does work. Okay, but if we remember back to main, let's say two more things about main. So I said main is a function, and it's automatically called whenever you run your C++ program. If we remember, int, right, that's an integer, right? So why is an integer specified before main, right? We would normally use like int number, right? And this would be creating an integer called number. The reason that int is before here is for a statement that we weren't really using, but we should have been using: return 0. By default, in the newer C++ standards that we're using, it's not actually super new, it's kind of old, but they added it at a certain point, that by default, main used to have to return 0, but they added in a newer standard that just if you don't have any return statement in main, it automatically returns 0. But I said that this returned keyword, it stops whatever is going on inside of the function and then outputs or returns to whatever called the function 0. If you remember, 0 is a integer. It's a number. If we can put -1, we can put 1 or 2. But 0 in this context indicates success. So if main returns 0, whatever called main can say, okay, so that means that main succeeded. That means that succeeded. If we returned a -1, right, something is going to call main, something's going to run our program is going to give back to it a -1, and then the thing that called our program is going to know, okay, our program failed. If we check right here, the int, you can might be able to guess this, int specifies that that this function returns an integer, which is a number right here. We can also, let's continue with what I was saying. We can also say std string Geobor, and we can we're writing another function, as you can see. Let's make this function similar to how main looks, and let's return Geobor. So what this is now we can see that this integer right here, this is specifying the return type of the function. So this main returns integers, so we say int main because main returns integers. This returns strings, so we say std string Geobor because Geobor returns strings. Now, what I did here is actually not good practice, because after a function completes, all of the memory that's inside of the function, so wherever Geobor was stored, is kind of just erased. It's kind of not exactly erased, but it's marked as free memory. So anybody can now just go into that memory and overwrite whatever is inside of it. So Geobor might be overwritten by a whole bunch of new data, and we might try to check what is inside of Geobor. Right here, this Geobor string literal. We might try to read it, and then we're going to find a whole bunch of messed up data. So this is not generally what you want to do. That's because any string literals and stuff like that those are usually destroyed after a function ends. After the return, all these string literals are destroyed, and the memory is marked as free. What you would want to do is like std string gamer equals Geobor, and this should be in quotations or double quotes, and then we want to return gamer. So this would work though, because now this is not gonna this is gonna create a temporary value that's gonna properly return gamer to whatever called it. At least I'm pretty sure that's how it works. I read that in a book. It seems a little bit strange to me, but I might be teaching you misinformation, so don't take that completely seriously. Let's get into doing something a little bit more interesting. This time we're going to have return 0 at the end, because I kind of forgot it last time. And it's not necessary because it automatically puts return 0, but we're going to have it this time. Let's use a new function at the top right here to make it easier to use some functions. Let's say using std cout. I'm not actually sure if you can even do this. cin. No, this does not work. So I was trying to check if using can have multiple things in it. But no. If you remember what this does is we're going to be now using cout from the std namespace. We're also going to be using a new function called cin. If you remember what cout means, console out. So you can imagine that cin is console in. We'll see what that does. I also showed you that I tried to use what are called I tried to use commas to have using statements on the same line. Evidently that didn't work, but where I got that from is if you do int number equals 0. Remember, you can also do this though. The reason I would not recommend doing this, usually when you're initializing something like this, you usually want to give it a value of like 0 or something like that. The reason that you don't want to do this is valid, but it's kind of hard to tell what number equals. Number might equal 0, or it might equal nothing, or undefined, or it might equal just some random thing that will crash your program. So I recommend usually just giving it a value initially, right here. And so that's what I'm going to do. I can also, though, put a comma, say number 1 equals 0 as well. And what this does is we see that integer number equals 0, and then we comma number 1 equals 0. What type is number 1? Number 1 is of type integer, because in a statement like this, you can put as many commas as you want. We can say number 2 equals 0 as well. When you put a multi-line statement like this, this this integer applies to every single variable that you initialized in that statement. Let's do something else though. Let's do cin. Remember sin right here? We defined it up here, or we included it. I don't know what the exact terminology for it is, but we said cin. So if we do cin and we put this way this time, number, right? And then I'm gonna do cout number. Okay, interesting. Let's check what this does first and foremost. So it's giving us a blank prompt with a little dashed line right there. Let's see what this does. If we put 12 and press enter, it's gonna print out 12. Well, how does that work exactly? How that works is that if we take a look, this cin, remember I said that the cout refers to the standard outstream. This refers to the standard instream. And the instream allows us to type in numbers into the console, and then it'll write whatever is inside of the instream to whatever we put on the right side of these number variables. So this cin will call the instream, and then it will write whatever is inside of the instream into number. If we see right here, these arrows are going towards number. That's because it's writing what is inside the instream into number. And then these cout is writing into, or it's saying it's pointing into cout because we're trying to write number into the outstream. Right here, we're trying to write the instream into number because we typed in something into the instream and we're trying to put it inside of number, right? If we type 12 into the instream, we want to put 12 into number. If number is 12, we want to put that into the outstream so we can see it printed out into the console. That's how that works. If we do this, then we can see number 1, right? Let's see what this does. I'm also going to put a second cout statement right here, and we're going to print out number 1. And I'm also going to do that. So let's see what happens this time. So let's put in 11, and it's asking us once again, well, let's see what happened here, right? The cin is going to write the instream into number, and then it's going to return the instream once again. So it's going to return this, which is the instream. And then it's going to say, since this whole thing evaluates into the instream, it's going to write the instream once again into number 1 this time. So let's put 33. And we get out 11 and 33. Well, that's because right here, we initially typed in 11 into the instream. We put that into number. And then it asked us for another number because this evaluated back to the instream, and we put that into number 1. And then we write into the outstream number, and then we write into the outstream once again number 1. And when we write that into the outstream both times, it prints that out both times. I said also instreams and outstreams are normally not cleared. Somehow, I don't know exactly actually why they were cleared here, but at a certain point they were cleared by some, maybe operating system function. If this instream was not cleared, for example, what would be happening is that we would be writing 12 or 11 to number, right? And if the instream was not cleared, the instream would include 11, and then it would ask us for another number. We would write 33, and we would have 1133 in the instream. It would try to write that to number 1, which would not work. So at a certain point, it did clear the instream, and that might be some operating system function, or maybe these at a certain point clear the instream. But a lot of the time, if you're getting errors of like the previous stuff that you wrote into the outstream or the instream, remaining there, you're going to have to clear the instream or clear the buffer with, for example, the std end line thing clears the buffer. But I think there's also like a syn dot clear function or something like that, and this clears the instream. And there might be a similar thing for cout, but we didn't look into those functions yet, so we're gonna avoid that. What we see now is that we write into number, and then we write into number one, and then we write those out. What happens though now if we write into let's do this. Let's write into number 2, right? And then let's cout number 1 and number 2 here. So let's also, if you want to zoom in and out, it's a Control Shift comma and it's a Control Shift period. Let's take a look. So if we take a look, what should this program do? Well, it should write from the instream into number 1, then 2, or from number and then number 1, and then it should write into the outstream number and then number 1, then it should write into the instream number 2, or it should write from the instream into number 2, and then it should write from the outstream number and then number 1 and then number 2. Let's try it. Let's see what happens. I don't know why it opened over there. Let's do 11, 22. So it says 11 and 22, right? And now it's giving us a weird little prompt right here. What happens? Let's write 33. You can see that 33 is right after the 22. I'll explain why that's going on. And then it printed 11, 22, 33. So if we see what's going on, this initial 11, that's when we typed into number. This 22 is when we typed into number 1. And then this 11 right here and this 22 is when we printed them out right here. Then this CIN happens right after we print out number 1 and we type in 33 to it. So if we remember, we did not write a new line character right here. So if we did that, then what would happen is that this 33 would be on the next line. Once we write a cout, the CIN is not going to be inherently on the next line. It's going to be staying on the same line. So if we look back here though, number 1 and number 2, number 1 and number 2 didn't change, so it's still 11 and 22, and then number and number 1 didn't change, so it's still 11 and 22, and then number 2, remember we wrote from the instream into number 2, 33 right over here, so it prints out 33 right down here. Let's close this window again, and now that I added that end line character right there, let's see or end line manipulator right there, let's see what happens. 11, 22, 33. Now you can see how it works how we would expect it to. This is how you would get user input normally. And the instream, what's nice about it is that this instream will write into number whatever type number is. So number is of type int. So it already knows that int, that number is an int right here. What if though, let's say for the sake of argument, we did not define number 1 or number right here. Well, number is not defined. What if, right? We want to say int number. Would that work? No, that would not work, right? Because right here, this operator is asking for an operand of type int right here. This is not, int number is not an object of type int. It is an initializer statement that initializes an object of type int. That would not work. We would already need a pre-existing object of type int to work this. It actually doesn't have to be of type int. It can be of any type. Number doesn't work because it's not initialized anywhere. So now that number is initialized up here, this will work, and it automatically decides that this is of type int. What if, right here, let's get rid of most of this code, and let's cin, no, that's not what I meant to do. I was trying to do std string word equals nothing. Generally, it's the same thing with words, right? You don't really want to initialize them to nothing. It's not a huge deal for words, because when you initialize them to nothing like this, they just initialize to an empty string. So this word will equal an empty string. But good practice most of the time, just so you avoid undefined behavior, to initialize them to something like an empty string. And that's just so you can get used to doing that for most objects that you initialize. And over here, we can see number 1 doesn't exist anymore. So what if we do word? So, and let's see out word right here. Let's see what happens. So it's asking us for something. Let's put 12. It's asking us for another thing. Let's put 12. And it works, right? But we had a word, right? How did that work? We put in a number, and when it asks for a word, well, it will automatically convert that to a word. It automatically converted that 12 to a word. You can also put in that, and it'll see out that. What's nice about CIN is that even in a single line statement like this, the CIN will respect that number is an int, and then it will, even after it accepts an int, it'll accept a word or a string right after it, which is nice. Something that we can't do, though, is I was talking about how we wanted to assign why is that a big deal? Why is that a big deal that we can put in a string after we put in a number? Well, imagine we said that, right? Word right here equals number. Number is of type int, and we're trying to assign a number of type int to a word of type string. If we see that does not work, the reason is because you cannot assign normally objects of different types to each other. So since word is a string, it cannot have number assigned to it. Let's get rid of that. And that's nice, though, because CIN will accept a number, and then it'll accept a word after that. What we remember, though, is that word, when we wrote here, or when we wrote from the instream into word, we were able to put in a number, right? We put in a number for number, and then we can put in a number for word. The thing is, what is going on, it's not actually, I said it's converting automatically. That's not actually what it's doing. What it's doing is there's two different versions, or actually, well, yeah, there's two different versions of every single number. There is a number like this, and then there is numbers like that. Or, well, let me check if I can type. You see, these are what's called characters. And so characters, they can be in strings. What is going on, bro? With this code. So numbers can be in strings, but strings cannot be assigned to literal numbers. What is going on with my cursor? Okay, now is it? What is going on, bro? I'm gonna restart Visual Studio because That's being weird, bro. That's being weird. Let's open our tutorial. So as I was saying, we can put in like characters that represent numbers up here, but we cannot put in actual numbers. So without the quotes, those are literal numbers, and with the quotes, that is a string of characters of numbers. And every single number, as I said, has a version like that and a version like that, which this one is a character, that one is a literal number. And when we write from the instream into Word, it'll automatically decide from what is in the instream whether that should be the character version of number or whether it should be the actual number version of number. So when we write 1, 2, 3 into the instream and assign that to Word and write that into Word, it will automatically write into Word the character version of these numbers, so the ones in quotes, rather than the literal ones, the ones without quotes, which is nice. Because usually conversions between different types is a pretty big deal in C++, and that will automatically handle it for us. Let's try to do something a little bit interesting with our knowledge of strings. So I'm gonna include a using std string declaration up here, so we know that we're using a string. A lot of the time when people refer to strings right here, when they're talking about the strings that are used inside of this string file right here that you include, they're talking about library strings. And that's this std string object right here. They're talking about library strings. I remember I said that iostream includes its own string literals like that, which are strings that are not assigned to any object. So those are just string literals included inside iostream, and then the string actual file right here will include what people generally call library strings. I don't know if I mentioned this as well, but the std syn thing, this is also included in iostream. So this comes from iostream. Something you'll notice as well is that even despite the fact that these are included in the file iostream. So why are we specifying that they're in namespace std? Well, why don't we do like iostream string? Well, as I said before, iostream this is called a preprocessor directive. And so before the compiler looks at any of this code, there's a preprocessor that goes through here and copies the contents of iostream into here. So if iostream includes a whole bunch of code, that code is like physically going to be copied into this file. So you don't have to specify that it's within the file iostream, because all the code that's in iostream will be already copied into your file, which is nice. And the reason we use std string is because even within iostream, it is specified that the string data type is within the std namespace within iostream. So iostream only gives us access to the string because all the code for the string data type is written inside of, or well, I was saying iostream this whole time. I meant string file. But all the code for the string data type is written inside of the string file. And all that code, even within the string file, is defined within namespace std. So we still have to use std string, even though we're including a separate file. There's no include std, anything like that, because there's no std file. There's a whole bunch of different files that all use namespace std, and all of their code is within the std namespace. So down here we're going to be making a calculator, and we'll define multiple methods of making this calculator, but let's start with this basic method of making a calculator. So we're going to say CIN, or we're going to define something called num1 or int num1 equals 0. Int, or no, not int, num2 equals 0. You can't put multiple different data type specifiers into the same line. If I tried to do string here, that would not work. It does not allow us to do that because everything in one line will be the same data type that is in the front. But now we have these num1 and num2 variables both initialized to 0. Let's say cout and we're going to put a little nice prompt right here. Enter a number. Okay. And do this. And then we're going to do that. Then we're going to do CIN, or CIN has to be this way, num1. So if we take a look, what should this do? It's going to print out onto the console, enter a number, and it doesn't have any new line thing, so it's going to ask CIN on the same line. Let's add a space there, and let's do num2. Enter another number. So if we take a look, what should happen is that it asks us enter a number, and then we enter num1, and it asks us enter another number, we enter num2. Now what we're going to do is cout we're going to put a string literal here, the sum of num1 and num2 is and we cannot put the plus, remember, because this is a string literal. We cannot add anything to a string literal. We're going to say the sum of num1 and num2 is num1 plus num2. And I don't know why I put that way. It's supposed to be put that way. Let's also just put a just to make it nice. Let's see what this does. Enter a number. Okay, 2. Enter another number. Okay, 3. The sum of num1 and num2 is 5. So how do we exactly get to there? Enter a number. Since we have no new line, this is going to be asking us on the same line. We typed in 2 for num1. Right here, this is going to be asking us on the same line as well, and it's going to be asking us for num2 this time. We typed 3. Right here, we're going to be typing the sum of num1 and num2 is, so we type this right here is equivalent to that. And then we do num1 plus num2. Remember that for integers, for numbers, when we use the plus operator, it just returns the sum. It returns a new value that is the sum of those two numbers. And that new value is 5. And then we put end line right here, and we get this space. Pretty simple. Now, what if, for example, if I put in like 12 and then put a space and I put in a whole bunch of stuff? the way that this works is that let's try that again, because I actually did not expect that to do that. So let's do enter a number. What if we do 12 and 2? It gives us 14, right? It says enter another number, and then the sum of those numbers is 14. So it did not ask us to enter another number. Remember, it does not flush the CIN. It does not flush the instream after assigning it to number 1. So when we put 12 space 2 here, it assigns the 12 to num1. Presumably it flushes that part of the instream, right? It gets rid of that 12. Then it has another number in the instream, that 2, right there. And so when we're asked to write the instream into num2, it already has a value into the instream, and so it writes that 2 into num2. So what happens exactly here is that it asks us enter a number. We write into the instream right here, the instream, which is CIN. We write into the instream 12 and 2, because we put 12 space 2. And then cout, enter another number. This is printed out right here, because we told it to print it out here. And then when cin tries to write something into num2, it has another value to write into num2, 2 right here, which we already put in. And so it doesn't even ask us for another number. It prints out this, and then it already has another number to assign to num2, so it prints out this again, and then does num1 plus num2 right here. That's not what I was trying to demonstrate, but that's cool. That's an example of some errors that can happen, though. But here's what I really wanted to do. What if we put enter a number and I put in G? And it breaks as well. This time it says the sum of num1 and num2 is 0. That's because when we put in G is not a number. It has undefined behavior, because when we try to put in G, we have all these 1s and 0s. It's trying to represent a number as the 1s and 0s in a G, which doesn't really make sense. And so evidently it had enough 1s and 0s to fill both num1 and num2. That's why it skipped asking us num2. And then it just said the sum of num1 and num2 is 0, because it had some type of undefined behavior. That's why you don't really want the user to be putting in like the words or characters or anything else for sin. So we're going to be doing something quite nice. We're going to put if, this is a new word, or this is a new statement, if sin break, or, well, no, it's not break. I remember I got the wrong keyword. It's pass, I think. Oh, wait, no. Yeah, there we go. It's just an empty statement right here. You need a colon or a semicolon to indicate that this is an empty statement. This right here is a valid statement. Just like cout, enter another number, this is also a valid statement. It just does nothing. So I was thinking of another language when I was putting break and pass and stuff. That's not C++. We're going to put else cout bruh, that's the wrong type. And let's run this right here. It says enter a number, right? Let's type in 12, and then we type in 12, and we should get 24, right? That works all nice and good. Let's run this once again. So it's enter a number. What if we type in G? It says, bruh, that's the wrong type, and then enter another number, blah, 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 blah. Well, what this does is, let's go through exactly what happened. I remember I need to add one more thing. Right here, let's do -1. And we need to put that there. Now let's run this, and we'll see that this works better. So enter a number. If we put in G, it says, bruh, that's the wrong type, and then it kills the program. It does not continue. Let's see exactly what's going on down here. Let's put some enters so we can see what is going on. Make sure that this, see what this is doing exactly. So we're saying if sin num1 do nothing, else cout that and return -1. I'm going to go through this step by step. So an if statement is what's called a conditional statement. If. What this statement does is this statement checks whatever values you pass into these parentheses right here. It checks if they're true or false. So what that is called is that's called a type boolean. So if we type in bool, B-O-O-L, TF for true false equals true, right? This means this is just like an int or a this is just like an int or a any other type of number, but this is just like an int or a string or something like that, but it is a data type that contains true or false. This boolean can either be true or false, or if it has, for example, I'm gonna do something right here. I'm gonna take all this code and I'm gonna press Ctrl K C, and that comments all this code out. We'll see what that does later, but this code is not gonna do anything for now. Let's say bool TF equals true. If TF cout bruh. Let's run this. Let's also comment out this code right here. Ctrl K C. So now the only code that we're having is this code right here. It says bruh. So it says if TF cout bruh. What this if statement is doing is it takes a data type of type boolean right here. So TF is of type bool and TF equals true. And it checks, does that object of type boolean, is that true or false? So in this case, TF is true. So if true, do whatever is in here. Let's see. So TF is true, so it's going to do whatever is right here. And what is right here is cout bruh. So you can imagine if TF is true, then it's going to cout into the console. It's going to write into the outstream bruh. And that's exactly what it does. Now you saw I did write it like this at some point. I didn't have those brackets. Well, how does that work? It still writes bruh. But the reason you generally want those brackets is if you put another statement right here, that would not work. You need those brackets because an if statement can only have one body. So this is called an if statement. It can only have one body. So it has first the if, then it has this condition inside the parentheses, and then it has a body. What you can do, right, it can only have one body. So this cout is its body. If you wanted to make the body bigger, for example, right, because if you wanted to do something else besides just cout, right, if you want to cout bruh, and then say, let's do that, and then cout Geobor. I don't know. Right? Let's see. Well, it looks like it works, right? But imagine this is false. Right? So what should happen here, right? It should not cout any of these, right? Because TF is false. So it should not do anything that's within this if statement. It still prints out Geobor. And the reason for that is this cout Geobor is not included in this if statement. It is, the syntax looks more like that instead of like that. This, because an if statement can only have one body. If you want to extend the body, if you want to make the body bigger, you can't actually literally do that, but you can do this, which is pretty much what you're supposed to do. This is like the intended solution. So this right here, putting this block right here, this is equivalent to, you remember C++ is also freeform. You can write this block in any way that you want. You can write this block like this if you want. So now if we take a look, this if statement still has one body, right? Except this body of the if statement is what's called a block. And that is segments of code that are encased inside of these curly brackets. And I'm pretty sure that's the technical term for them, literally just curly brackets. This is hard to read though. So what people generally do if they wanted to write, a block, they do like that. And they do like that. And then after this, they would do something like that. Then they would do like that. So this is a much easier to read block. And a lot of the time, you can see that main also has a block right here. Main has this block, and it extends down to here. Let's push some of this code away so we got a little bit more space. So that's you can write a block like this, but most people do not write their if statement blocks like that. The general syntax for most people for an if statement is like that, and for a function, people generally write the syntax with the start of the block down here, like that. And for if statements, people generally write the syntax with the start of the block up here. So this is equivalent to having one body, but this body is a block, which includes multiple statements. That's so you can have multiple statements inside of a block. Now if you run this, right, let's see. TF is false, so if false, well, that's false, so this should not run. So we should not get Geobor and bruh out here. And we do not. Correct. Now if we change this to true, we get bruh and Geobor up there. So if we the way to explain what this is exactly is that if is what's called a flow controller statement. And there's a lot of different flow controlling statements, but if is probably the most general one. If you've ever, heard about the Yandere dev memes where he uses else if a lot, that's what they're talking about. They're talking about this if statement. And the if statement also has an else statement, which I showed. Now, let's do something else, right? What if, oh, well, that's how Visual Studio decides to run it. Something I shouldn't note is that every body of the an if statement body has to have a semicolon at the end of it. So if the body is a regular statement, if this if statement, for example, its body was just this line, this semicolon would suffice. But since this if statement has a body that has a curly brackets right here, these braces, we need a semicolon right there at the end of the curly braces, because the body has to end with a semicolon. So right here, this ends with a semicolon. So if this was the body, that would be fine. Since this block is the body, it ends with a semicolon right here. Let's check what this else statement does, though. This else statement is an addition to the if statement. So an if statement will have a body right here, and the body does not have to end with a semicolon right here if an else statement comes after it. So this else statement has its own body right here that contains this code, and then it finally ends off with a semicolon. So this if statement right here is linked up with this else statement right here. So when we evaluate this if statement, it says if whatever is in here is true, then do that. Else, do this. So let's demonstrate exactly what is going to happen. It says bruh. Okay. What if it's false? Geobor. The thing that this is doing is it's evaluating, this if statement is evaluating whatever is in here, and then it is checking, well, if that is true, then evaluate whatever is in here. In any other condition, evaluate the else block. So it doesn't even necessarily have to be false. It can be broken, undefined. It can be whatever you want it to be. As long as it's not true, it will do this else statement right here. So this is a very useful statement that allows us to do some very nice stuff. It is the basis of a lot of different logic operations in C++. Now, what if we do, for example, that equals 0? Let's run it. That is Geobor, right? If we do 1, it's bruh. So it's saying that 1 is true because right here, if TF, so if TF is true, then see out bruh. And we put in 1 for TF and it printed bruh. So it's saying that 1 is true. The reason for that is because not every single, but a lot of different data types like integers by default have a method of converting themselves to a Boolean data type. For integers, it is any number besides a 0 is true and a 0 is false. So a 0, when we assign a 0 to TF, it changes that 0 to false. And if we assign a 1 to TF, it says that's true. If we assign a 2 to TF, that's also true. If we assign a -1, that's also true. So bruh. So anything besides a 0 is true. If we assign a character, like a 1 right here, this, I think, theoretically should be true. And I think there is a method in which you can get a character to evaluate as false. Yep, right here. So this right here is what's called a null character. It's just like that /n, except this null character signifies nothing. This signifies that there's nothing there. And so when you use a character, then this evaluates as false, and everything else evaluates as true. So like R is true because it's a valid character. And every single or almost every single data type has its own ways of converting itself to a true or false value. And that's just something that you have to know. Like a string, for example. This string, I think, or let's see if bruh is true or false. So bruh is true because we see it printed bruh. If we say H, just the letter H, that is also true. I think the way that you get this to be false, no, an empty string apparently is also true. Like, what about a new line character? That's also true. And a null character is also true. I don't know what is false for a string then, honestly. Maybe a white space character? No. Everything apparently for a string is true. Maybe an invalid string is not true. But in this case, you can say that this equals 1, and that's going to print bruh because it's true, because 1, an integer of 1 automatically is converted to true, and an integer of 0 is automatically converted to false. Let's get rid of these blocks. Actually, one more thing I want to do. Let's say, right, we have an int num equals 0. If num bruh. So as you can see, this num right here, when it's put into an if statement, this if statement has a condition in here. This condition, whatever is in there, is automatically converted to a Boolean value, or a Boolean value, and it is determined based on whether that Boolean value is true or false. So num is an integer, but when it's put into here, it's converted to a Boolean, and it returns bruh because 1 converted to a Boolean is true, if you remember, and 0 converted to a Boolean is false. Now, we can do something else. If num equals, and we have to put a double equals for this, I'll show you why, equals 0. Now, remember, num is 0, so 0 evaluates to false normally for a Boolean value, but it says bruh. And the reason for that is because this is not, it's no longer converting num to a Boolean, it's converting this entire statement to a Boolean. And so it's checking, does num equal 0, right? And this statement uses the double equals operator. This double equals operator returns a Boolean value based on whether this statement is true or false. If this statement is true, it returns a Boolean value of true, and if false, it returns a Boolean value of false. If we say, for example, this equals 1, so num no longer equals, this is no longer true because num equals 0, not 1, right? So it prints out Geobor because it is false. Now, what is the difference between this double equals and this equals? Well, remember, this equals assigns, it copies this to this. So it copies this 0 to this num. What this does, the double equals, this is the comparison equals operator. This compares num and 1, and it returns a new Boolean value based on whether this statement is true or false. So since this is false, it returns a Boolean value of false. That's what this does. This, on the other hand, it adds or it copies 0 to num and then returns num. This compares num to 1 and then returns a Boolean. So we can also do another statement right here. Else if and then this is like another if statement. We can say else if num equals 2, right? Now, num neither equals 1 nor 2, so when we run this, we're not going to get anything out. That's because this else if block, it's no longer an else block that runs on any other condition. It is an else block that this is only evaluated once it is determined that this is false. So it has to evaluate the next else if, and this is determined false as well. So nothing is evaluated. What we can do is we can put another, once again, else, and we can say cout gamer. And let's press F5. And it's going to be gamer. Now, let's go through this. So, if it equals num1, that's not correct. So, it's going to say, all right, else if it equals num2. It's not correct either. So, else and any other condition besides the ones that I just tested right here, it's going to print gamer. And so, since this does not equal 1 or 2, right, it falls into the else block. And then prints gamer right here. So this else if is tied to this if block, but also checks, in addition to this if block, another condition. And then this else block does not check a condition. It just catches any other value. Okay. So, what was I gonna say? Oh yeah. In addition to this double equals operator, there's a lot of other operators. Before I do that, I want to talk about what is the point of the if-else block. Imagine, right, that we just had a whole bunch of ifs, right? So we're checking, all right, so if num equals 1, do this, right? And then if num equals 2, do that. Well, imagine for a second that num does equal 1 right here. And then we say inside of here, right, instead of printing bro, we say, okay, now num equals 2, right? And remember, we're using the assignment operator right here because we're using the assignment operator right here because we want to change the value of num to 2. We don't want to compare num to 2, or we're not initializing a new value called num. We're changing num to 2 now, right? So if we run this, what's going to happen is we're going to get Geobor. And why is that? Well, right, it should have just gone into this if statement. Well, what happens is that we go into this if statement. This is true. Num does equal 1 right here, we can see. It changes num to 2, right? And then it continues on with its code. It says, okay, now if num equals 2, print Geobor. Num does equal 2 because we changed it to 2 right here. To avoid something like that happening, because a lot of the time you don't want what happens in this if statement to affect what happens in this if statement, that's when you use the else if. Because now what's going to happen is it's going to check, all right, if num equals 1, right? Assign 2 to num. And then it's going to skip this else if block because it's already evaluated this if block. So it knows that it doesn't need to evaluate any of the other blocks. And it does not print anything because it evaluates this and then says, okay, this whole if condition, this whole statement right here is finished, right? That's why you would use it. If you change the value of your variable inside of the first if statement, you want to usually use else if statements to make sure that they're not checked again. Also, it increases performance to use else if statements versus just a whole bunch of if statements, because if you have a whole bunch of values you want to check, all right, so does num equal 1, 2, 3, 4, or 5? Instead of checking, if you had a whole bunch of if statements like this, I'll show you. Let's do that. And then you had a whole bunch more like that, and you just kept going, right? And you just wanted to check one of these, right? You wanted to check if num equals 1, 2, or 3, right? And imagine it equals 1, right? Then it would still be like, okay, so it equals 1, and let's ignore what happens here, right? So it equals 1. Okay, that's good. Do whatever it needs to do because it equals 1. It's still, after it finishes that, gonna check it. Does it equal 2? Does it equal 3? Because you're not telling it else if. If you put else here, it's gonna say, okay, so now I only need to check one of these conditions in the entire if statement. And let's do that. So now, right here, it's going to say, all right, does num equal 1? Okay, then do what num equals 1 does, and then skip to the end. Because we know we don't need to do the rest of these else ifs. And then you would have, for at the end of this, usually like an else in case none of these conditions are correct. The last operators right here I want to show you is right here. There is the well, let's get rid of all these else if statements for now. And I'm gonna see out bruh. And we're just gonna do if tf or bool tf equals 1, and I put if. There we go. So now we're back to a simple if statement right here. So what if we do, for example, or let's take this again. Let's do tf1, and let's actually, oh, also this right here, this box that pops up that auto completes a lot of your code, this box automatically, you can use the up and down arrows to choose something, press enter to use that. What's annoying sometimes though is you can press tab to automatically also complete it. What's annoying sometimes though is like sometimes you just want to move down in your code after writing something. So if I write true here, it's still putting me in this box. So how do I get out of this box? You just press escape and then you can move down with the arrow keys. Right here though. So now we have two Boolean values right here, tf and tf1. So we can do if tf equals tf1, you can compare Boolean values. Now, since this is false and this is true, it's asking, are these the same? Not whether these are true or false. It's asking, are these the same? And it returns true or false based on whether these are the same. These are not the same, so it's not going to print anything. Even though tf1 is true, right? It's not asking if tf1 is true. It's asking if they're the same right here. We can put true right here. And it's going to say bruh because now they're the same. We can also a little bit counterintuitively put false for both of them, right? And it's going to say, bruh, because it's not asking whether these are true or false. It's asking, are these the same? They're both false, so they are the same. So this double equals returns true because these are the same. What we can do as well is we can say if that is not equal to tf1. This is just like the double equals, except it reverses what is on the right-hand side and then compares them. So this, what exactly it does is imagine this and this is true and false, right? This, so TF is false. If false does not equal false, then this is true. So this should be false because we want these to be different if they're going to be true. Right here, this is false because the only way for this to be true, this is called the not equals operator. This returns true if these are different. And the way that they check if they're different is this not equals operator will take whatever's on the right-hand side. So if, for example, if TF equals TF, this should return true. And the way that this works is this operator, this should probably make it a little bit easier to understand if we do that. So this not equals operator will take what is on the right-hand side, right? It will reverse it and then check if this is true. So if we evaluate this statement right here, is this statement true? TF equals TF. Well, let's see. TF is false and TF is false. So this statement right here, this whole thing in parentheses is going to return true. Okay, so if TF does not equal true, then this whole statement is true. Because this side is true and this side is TF. So if TF does not equal true, then this whole statement is true. And the way that this will check whether TF does not equal true is it will reverse what this is. So this is true. It will change this to false. And then it will compare them to the equals operator and check if TF equals that. So best way to explain this. Imagine this is true, right? It will change this true to false. Then it will change that to the equals operator and check if this whole statement is true. So if TF equals false, that is true because TF does equal false. And if we put TF does not equal true, that is also true. Because remember, this will reverse that true, turn it into a false, and then check if this whole statement is true. This true can also be any statement that you want it to be, as was the example by the TF equals TF. Remember, this thing in parentheses is the same thing as true because TF does equal TF. So this is true. And if TF does not equal true, then this is true. That might be a little bit confusing, but That's how the not equals operator works. Let's also check some other operators. So tf1. I actually do not know how these operators work. So some other operators that we can use. True. If tf is greater than tf1, tf is not greater than tf1 apparently. If we check if tf1 is greater than tf, that is true. And booleans are classified as greater than when, or true is greater than false. So this greater than operator will check, okay, so this side is a boolean, so is true greater than false? That is correct. This greater than operator also works with int num1 equals 0, num2 equals 2. This greater than operator also works with numbers. So if num2 is greater than num1, I didn't put num1 here, then this whole statement is true. And I have an error somewhere. It's because I don't have there. So num2 is greater than num1, so this is true. Remember, these operators are not specific to Boolean values. They don't have to compare Boolean values. They can compare almost any value. But they do evaluate this whole statement and return a Boolean value based on this statement. We can also use the less than operator. This is going to evaluate as false because 2 is not less than 0. So we can use the not equal to num1. So that returns true. So it says num2 is not equal to num1. Now, if num1 equals 1, we're going to see, I think, something quite strange happen. No, this still works. I honestly I did not expect it to work because of some complicated C++ logic. But it says if we change this to 2, right, this should not work, right? It's empty. So that says num2 is equal to num1. So this returns false. What else can we do? We can also use greater than and less than signs with numbers. So if num2 is greater than num1, that should be false. That is false. If we increase num2 by 1, what was I trying to do? Now that is true because num2 is 3 and num1 is 2. So num2 is greater than num1. Then there's also greater than or equal to. So this should also evaluate as true. Yep. Greater than or equal to, you can imagine what that does. It's just greater than or equal to. This also evaluates as true because it takes into account the equal to part. 2 is equal to 2, so that is true. And then there's also less than and equal to, or just less than. And those act how you would expect them to act. If you, let's do something like string num1 equals gamer, and that is 5 characters. I don't know why I'm putting num2 and num1 for strings, but here we go. Now, strings are defined as greater than or less than, I'm pretty sure, by the size of the string. So this should evaluate as false. Yep, and that does evaluate as false because num2, if we check, num2 is Geobor, is less than num1, which is gamer. Geobor is longer than gamer, so Geobor is greater than gamer. If we put the sign the other direction, this should evaluate as true. That is true. And so these operators right here are very much based on which data type that you are using will determine exactly what it means to use those operators. Most of it is intuitive, but certain data types are not super intuitive to determine it, what those operators do. Let's get rid of most of this and let's see what is exactly going on right here. How's this code operate again? Well, actually, I see why I put these again. Let's Ctrl-Shift-K, or Ctrl, I remember it's Ctrl-KC to comment this out, but Ctrl-KU to uncomment it. I guess I should teach what commenting is right after this. Let's see what this does. So now we know what the if statement is. But what does this condition do? This is not a comparison operator. This is not a greater than or less than or equal to, or not plus plus, but there. So how does this operator work, right? Because this should return a Boolean value, right? But how does, because if an if statement requires a Boolean value to either be true or false to evaluate, right? But how does sin writing into num1, how does that return a Boolean value? Well, the way that it returns a Boolean value is, remember, this operator right here, it writes whatever is in CIN, whatever is in the instream, into num1, and then it returns the instream once again. So what that means is that this pretty much evaluates into the instream. And the instream returns either a true or false Boolean value based on whether the data inside of it is of the correct type. So what does that mean? Well, this is going to evaluate into the instream, and then it's going to return either true or false based on whether that was a valid instream or that was an invalid instream. Let's check. So if we enter a number, right, num1 is of type int, right? So if we type in 12, right, that's a valid instream. That means we check, is this valid, right? That is valid. So, right, this checks, was 12 a valid instream? That was a valid instream, so this evaluates to true, and that does nothing. And it skips this else statement because it already evaluated this if statement, and then it moves on. That's why nothing happens. Now, imagine we put in an invalid instream. Let's try that. So what is an invalid value for num1? So num1 is an int. An invalid instream for an int would be g, right? You can't put g into an instream. So what that does is it says, well, that is false, so evaluate the else, right? And the else says cout, that's the wrong type, and return -1. So remember, we're in int main. So if we return -1 in int main, that indicates failure. That indicates that our program has failed. And that's why it stops right here. So that's quite nice. That's how this operation works. Now there's a way to simplify this. We do not need this else statement. If we do, this, and then we do this. And let me make sure this works, because I'm not, I'm not 100% sure that, I wasn't 100% sure that would work. You have to do this, right? Because this, this operator, this is not the same operator as that, but it does a similar thing. The exclamation mark operator negates whatever is on the right side of it. So this operator returns the opposite of whatever is on the right. The thing that's on the right is this cin num1, meaning that the result of this whole check right here, the result of this whole statement, is going to be the opposite of whatever this is. So if we put in a valid value for this, it's going to result as true, right? And then that's going to negate this, turn it into a false, and then it's going to, the if is going to check and be like, okay, we have a false, so we're not going to do this. Let's see if that works. So 12. So what happens when I type in a 12? Well, the sin has a 12 in it, and it writes that into num1 and checks, well, was that a valid instream? Well, writing a 12 to an integer is a valid instream, so this evaluates as true, and then it negates that. So this whole statement evaluates as false. The sin num1 is true, but the negation of sin num1 is false. And then this if statement will look and see, okay, this whole statement was false because we negated sin num1, and so do not do what's in the if statement's body. In the other hand, imagine we do put in an invalid value, right? It says, bruh, that's the wrong type. How does that work? Exactly. Well, the way that that works is, let's see, sin of num1, it says, okay, so let's put the whatever is inside of the instream into num1, and that is an invalid instream when you try to put a g into an integer. That's invalid, right? So this whole sin num1 thing is going to evaluate as false, and then it's going to negate that. So this whole statement right here with the negation is true. So that means if whatever this is, this evaluates as true. So that means that this if statement is going to execute whatever is in its body. Its body is going to print out, bruh, that's the wrong type, and then return -1. Let's go back. And we're going to copy a similar thing for this. And this time it's going to be for num2, right? And finally, we can run our program. Actually, I'm going to run it. I was pressing F5 to run this program this whole time. I'm going to press Ctrl F5 this time. And it runs it in a little bit nicer of a mode with a little bit less junk going on, not debug mode. So let's enter 12. Let's enter 12 again. It says sum of num1 and num2 is 24. That's nice. Right, that worked perfectly. Now what we can see though is that if we type in 12, right, and we type in G, it says, bro, that's the wrong type. Now it catches when we try to when we type in the wrong thing, and it breaks us out of the program before trying to add together a number and then whatever G is, because that's not possible. There could be very, very bad consequences to adding together a number and then whatever G is. In this case, what we do is that we return -1, which ends the int main function. We don't necessarily have to do that. We could do anything else. We could, for example, when we encounter an error like that, we encountered that we typed in the wrong thing, right, the wrong type. We could say that's the wrong type and then pass off that to another piece of code that handles the fact that we typed in the wrong type. So there's going to be another way to do this. So what we're going to do up here is I'm going to comment out this code again. Actually, I said I was going to go over comments right after this. Let's go over comments. So now let's learn what comments are. A comment is formulated like this, and it is pretty much my worst enemy because I am terrible at spelling. But what a comment does is it's just a comment. It's just a piece of text that you include in your code to kind of explain to other people that are reading your code what exactly this does. So, you know, generally you wouldn't put a comment here, but maybe you could put something like that, and most people would see int num1 num2 equals 0, stores numbers to be added, and they would know that this comment is probably referring to these variables right here, and I'm trying to tell whoever's reading this code that that's what these variables do. And they're useful for stuff like that. Generally, you don't want to spam comments everywhere, though. They are ignored by the compiler. When the compiler is going through this to turn it all into machine instructions to run your actual program, it'll see a comment like this and it'll ignore it. And the way that you specify comments is you put these double slashes here. I'll show you another way to do comments, but these double slashes will just comment out everything that's on one line, but not anything that's on the next line. Generally though, like what you could do is you could say like right here, you know, maybe tests for valid input. And if somebody sees the exact same type of code block right here, they could probably infer that that's what it does. And generally, you know, if you're putting a simple statement like this cout right here, you don't need to explain to people what the cout does. You don't need to explain people what every single thing does. But if you have a more complicated code segments, you probably want to put some comments around to explain to anybody who's reading your code what's exactly going on. Another way to do comments is like, I think comments can go like something like that maybe, or maybe they cannot be in strings. I'm not exactly sure. No, they're like this. And look at that, Visual Studio was helping me out. But yeah, you can use this. And this comment allows you to do multi-line comments like that. And what it does is it takes this little specifier right here and it comments out everything up to the next specifier right here. So that's quite nice. What you can see though is if there's no specifier, it just starts commenting out everything. And if I put the specifier down here, which if I remember correctly went something like that, it'll comment out just everything up to this specifier. This can also be useful not only for multi-line comments, but for example, for putting comments in the middle of a thing, which you don't really want to do. That's kind of annoying when people put a comment like right here. But if you do it correctly, that's not too bad. There can be comments like that. If you're using comments though, a lot of the time, make sure your comments are correct. One, because if you put a comment and it says the wrong thing, like if you're just a complete idiot and you start putting like a comment here saying adds numbers, and you see you're so much of an idiot that you put nimbers, right? If you're that much of an idiot where you say that this if statement adds numbers and somebody's sitting there being like, bro, how does it add numbers? You're just confusing people. So make sure your comments are correct. Make sure you don't spam comments everywhere. Make sure you don't got like comments that just are annoying. Like some people put comments like and then they do something like this. And then they do something like this. And then they put like don't do this. Just do not do this. Whatever you do, do not do that. That is pretty much the worst thing that you can do. Let's learn a new statement though. Because comments make the compiler ignore stuff, they're useful for something like this. If you press Ctrl K, C, comments out this code. This means, you know, this code is acting like a comment. It's supposed to be like telling people what's going on with this code, but this is not actual. This is not an actual comment. It's just code that we can use comments to comment out and then tell the compiler not to compile that code. And then we can do something else. We can learn a new statement. So how about a while statement? A while statement is a lot like a if statement. It just acts like a it's also called a while loop. So a while statement or a while loop will be like an if statement and have these parentheses after it, and it'll have a specifier inside of it. And I'm gonna write pretty not complicated, but while. Oh, wait, what am I even doing, bro? But I'm gonna write something pretty a little bit more complex of a while statement at first, and we're going to be able to figure out what that does in a little bit. So while okay, let's see what this does. Enter a number, 12, right? That works. Something I remember I did not specify is that despite the fact that the CIN is inside of these brackets, the CIN still executes the same way as if it would be outside of these parentheses. So that's something to keep in mind. Even if it's inside parentheses like that, it does the exact same thing. But let's check what this CIN does. As we checked, this executed, and then it put whatever I typed in for sin into num1, right? Well, let's take a look. We remember we explained this equation, right? If this is a valid instream, then this returns true, and then this negates that. So that means that this while loop would not run because this is a valid instream. So because that is a valid instream, that while loop would not run because this while loop is like an if. It checks. Okay, so is this true? Well, let's see. We put in a 12, so that would be true, and then negate it, so that would be false. So that's not true. So it does not run the while loop. It still runs the sin, but it does not run the while loop. If, for example, let's press F5 and let's put in something incorrect. Let's put in a G. Well, it's giving us another prompt. This is actually another sin. It's running the sin again. And that's because what a while loop does is if the statement inside these parentheses are true, it runs the while loop again. And so we can press G again. I did not press that into the correct place. Oh, I understand what's going on. This while loop is not correct. This is not what we want to do. So what we want to do is actually something like this. We can also put another body for a while loop, like a if statement. We can say sin.clear And we can put in G. And this should work, but I don't know why it's not working. So I've fixed the errors in this code. Let's go over it again. So while not sin num1, sin num1 will return false if there's a invalid data type or invalid data input for num1. So for example, if we put in a G, that would be false. And since that would be false, this negation operator is going to return this as true. So while loop is like a if loop or an if statement. It only runs whatever is in the while loop's body if the statement is true. And this statement is true if there's an invalid input for num1. Let's see. Now we call this function called sin.clear. This is like a function, almost like main. Not quite exactly like main. It's called a class function. And that is a function that is specific to an object, or an object function, I guess you could call it. Sin is the object right here, and sin includes a function called clear. So object functions only work for objects of that type. So to call an object function, use the dot operator, and we'll get into those later. But right here, we're calling an object function sin.clear. What this does is when, remember I said how cout refers to the same outstream every single time. No matter how many couts we have, it's the same outstream object that it refers to. Cin is the same way. There's only one instream, and so whenever we call cin, it refers to the same instream. That instream, though, will have flags on it when it fails an operation, like this one, when we put in G and that is an error, it's going to have a flag raised saying that there was an error. We use the sin.clear function right here to remove that flag, reset it. Then we use the sin.ignore flag, or .ignore function, to ignore all the data that's inside of sin right now, to reset it pretty much. Then we cout try again as a prompt. And so let's take a look at what happens. We typed in G, right? This fails, and it returns true because it fails. Then we clear sin, we get rid of all the data inside of it, we reset it pretty much, and then we try again. We cout try again. What happens here is after it gets to the end of the while loop, it will go back to the beginning right here. Once it gets to that end, it goes back to the beginning, and it will continue to run this while loop until this statement is false. Once this statement is false, it's going to continue on with the code down here. So the way to make that statement false, if we look, the only way to make that statement false right now is to put in valid data for num1. So if we put in G again, it's going to go through the entire thing again. Right here, we're doing cout try again every single time it goes through this loop. And so no matter how many times we put in G, it's going to constantly go through the same loop and going to say try again and try again. If we put in 12, for example, though, once we put in 12, it's going to check this, and this is going to evaluate the false. So it will no longer run the while loop. And this is enter another number. And since right here, every single time it's asking us for a prompt, it's using the same sin right here, because it's going through the while loop and then running sin again and putting it into num1. So every time we run this G, it tries to put it into num1. Once we write this 12 right here, it actually does put that 12 into num1 and succeeds, so it moves on. right here it asks us for another number, and we can do, 12, it'll give us 24, and that works. And so instead of just breaking the program, returning -1 once the if the value is invalid, we're using this while loop, which goes through the loop every single time to make sure that that is a valid piece of data putting into num1. What we can do now, though, is we can go and get rid of this. We can copy all of this code. We can put it here, and we can change this to num2. And now num1 and num2 will act the same. So num1, we can put in h, g, whatever we want. I don't know why it's asking us a whole bunch of try agains. Oh, I think I know, actually. It's because every single letter we put in is remember how sin is a instream object. So when we put in multiple letters, it tries to put that letter into num2 multiple times. Because if we remember last time, I accidentally put like a 12 and then a space 2, and that did work. It's because sin is a queue. It's a stream. So it's a queue of data. That D is in a queue and that S is in a queue. And so it tries to put that into num1 2 times, and it prints try again twice because it tries to do that 2 times. The reason they're on the same line is because no new line is created. The only time the new line is created is when we input something, because sin creates a new line right here. When we put in 2 things right here, when it doesn't ask us for a prompt, right? Because we're going to do this twice, and it's not going to ask us for a prompt the second time because it's putting the data in a queue. It's going to print try again twice because there's going to be no prompt for the first time. We can finally put in like 12 though, and we can see the same thing works with the second object. If we put in 12 again though, we're finally going to get 24 after this whole adventure right here. This is not a perfect program. As you can see, there's a little bit of bugs, like putting in those multiple characters. And you can do multiple different types of checks to make sure that no bugs like that occur, but this is good enough for our purposes. Now, there's another type of loop right here, and it's very similar. So let's run it right here. And let's press F5 and see what happens. Enter a number, G, and it says it does pretty much the exact same thing, as you can see, 24 again. So what does this loop exactly do? Well, it's called a do-while loop. It's exactly the same thing as a while loop, except it does everything inside of the function body first, the while body, and then it checks this parameter. Like a while loop right here. First, it checks this parameter, and then if it's true, it does this. This does all this stuff and then checks if the parameter is true. And if it is true, then it does all this stuff again. So what people often use this for is if they have an operation that they want to put in a loop that has to be done at least once. So if it has to be done at least once, then you can put it in a do while loop. And it will do it at least once because the first time around it doesn't check. Let's check the Snapchat that I got. Let's see, it's probably going to be useless. Yep, it's one of those, like, Blank and Blake are on Snapchat. Bro, what do I care? I don't got no friends. I'm doing a C++ tutorial, for real. But the do while loop is pretty simple, pretty easy concept to grasp. And we could replace this while loop also with a do while loop. So I think we're finished with this program finally. Unless, no, I wanna do a few other things with this program, because this program is for adding, right? And it's I said I was going to do multiple different methods of adding together stuff. This method is going to be using a function. So what we can do is we can say int add numbers well, since this is a function, I like to put my functions like that. Let's do something like that for now. So remember, this int right here signifies the return type. Since we're going to be adding numbers together, we probably want to return a number. So we're going to have the return type as int. This function is going to be called add numbers. And it's going to have these little parentheses. So add numbers, though. Oh, do you see that? Right here, my cursor is a block. And then when I press insert, it changes to a line. I didn't even know that happens. But anyways, we're going to probably need to give this function, right, some numbers so it can add them together. So up here, we're going to declare some numbers. Number A. And we're going to int A. And int B. And we're going to say return var equals and then what we can do is we can go here we can say add numbers 1 and 2. Or let's do 12 and 12 because we've been constantly doing that. And one last thing. Well, actually, let's run this and see what happens. It gives us an error. Reason for that is because this add numbers right here, we're telling main to call add numbers. It doesn't know where add numbers is right now. Add numbers is underneath of it right here. So there's a difference between a definition of a function and a declaration of a function. So right here, this is what's called a definition of a function. And if we want to do a declaration of a function, how we do that is up here, for example, we do this. Now this function is declared, so we're telling C++ that this function exists somewhere. And so C++ will find this function down here, and then it will allow us to use it right here. Because this is above that, now main knows that this function exists. So it says the sum of num1 and num2 is 24. How exactly does this work? Well, let's take a look. Oh, one last thing I wanted to mention. You do not need this declaration if you do something along the lines of this. And get rid of that. Is 24. So there is a reason that you do use declarations though, instead of just putting every function on top so that they can find it. One thing I didn't mention about declarations is I think they need the semicolon right here. Yep. So there is a reason that you would use declarations instead of just definitions on top. It's just a lot of the time nicer to have the main on top and then all the declarations on bottom. Another thing that you use declarations for is a lot of the time functions are defined somewhere else, right? And just like we included this IO stream in this string file right here, what we can do is we can include a file that has a declaration for a function. And this declaration for a function will be on top right here. And so that file, like iostream, might contain a line that looks something like this. And so now we can use functions from iostream. That's why that's what declarations are that's what declarations are usually used for. So when we go to this add numbers function right here, generally what happens is we take a look at this right here. This is what these parentheses is what's called the call operator, and it takes whatever's on the left side of it and it passes in the parameters inside of these parentheses into the object on the left side of it. The object on the left side of it in this case is, it goes up here, it finds this function declaration, and it finds out that this function is defined down here. This function, add numbers, right? If we check what parameters it has, it takes an int a and it takes an int b, right? So it takes two variables, a and b. And so these variables a and b are initialized right here, just like if we were to initialize a variable like int num right there. So these variables being initialized right here is very similar to variables being initialized right here. If we check right here, what we're doing is these two things are what's called parameters. So we're putting in 12 for the first parameter, and then you put a comma, and you don't have to put a space, but space looks nicer. You can put another 12. And that's going to say, for the first parameter, we want to pass in 12. For the second parameter, we want to pass in 12. So down here, if we look, what is the first parameter? Well, the first parameter is a type int a. The second parameter is a type int b. So we need to pass in, when we're passing in parameters, an integer, and it's going to be defined as a in this function. So when we pass in this 12 gets assigned as an int a, and that 12 gets assigned as an int b. Then what happens is we initialize another variable right here, return var, and I just made up that name return var because it's a variable that we're going to be returning. And we're going to say that return var is a plus b, right? A is 12 and b is 12 in this case. So return var equals a plus b, and then we're going to return var. And what return does, if we remember what we said, main returns 0, right? And that means that when the operating system, when Windows calls main, it's gonna main is gonna give back to the operating system a 0. In this case, what's happening is that we are calling the add numbers function right here with these parentheses, and it's gonna, when we call this add numbers function, it's gonna be evaluated to whatever is returned. In this case, it's gonna return var, which equals a plus b, and a plus b is 24. So this add numbers 12 equals 24. Another thing you could do is, I said that this is not ideal earlier, but I'm not 100% sure about myself on that one. I read it in a book, but no, not that. I read it in a book that you shouldn't do this, but I'm not exactly sure why you shouldn't do this. Let's check if this works. It still works. But I read in a book somewhere that you're not supposed to return literals from from functions, and I don't know exactly why. And a literal being something that is not a variable. So that's something I definitely need to do some more research on. But right here, this also just returns a plus b. A plus b evaluates to 24. So this returns an int 24, and that add numbers equals 24 in this case. After a function is called, this creates an integer a and creates a new integer b. That is a little bit costly in performance. Not like if you're doing this right here, but if you're running this like hundreds and thousands of times a second, then it's a little bit costly on performance to create a function or create a new variable every single time. And there's methods to remedy that, but right now what we're doing is we're creating a variable a and creating a variable b, then copying 12 to a and then copying 12 to b, and then we're returning a plus b. When we return something, this add numbers thing turns into what's called a temporary variable, which is something that the compiler creates to hold a value that is returned from a function, or that it to hold a value that it needs for something else. This is going to be a temporary variable with no name that's going to be assigned the value 12. After this function runs, everything inside of it is destroyed. So this a variable right here, after the function is called, this a variable is destroyed. It's uninitialized. This a variable no longer exists, and this b variable no longer exists. Something that you notice, right? Let's say we wanted to one thing also I want to mention though is, since these a and b variables are destroyed, when you call the function the next time, they have to be reinitialized. You have to recreate them and then recopy stuff to them. So it's not exactly the fastest, most efficient process, but it's really good in certain circumstances, and not even in certain circumstances, in a lot of circumstances, and we'll see those circumstances. Let's see out though. Let's say, for example, right, we got a up here, right, int a. We cannot see out a because a does not exist inside this function right here. Inside these braces right here, there's no a anywhere. This a is only confined within this add numbers function. I don't even think you can do something like, you can't even do something like this. Variables that are defined inside of a function, initialized inside of a function, are not accessible outside of that function unless you return them. So if I returned a here, then I could use a, but I can't use a outside of here because a is nowhere to be found. It's inside the function only. This function though, we're only doing this once, and it's not like it's super costly to copy over the data and initialize these variables. It's just a lot of the time you can avoid that, and we'll learn about that later. Now, I want to learn about something called chars, and you might have seen me use these a few times throughout this tutorial. A char is, let's see out with single quotes an a, and let's run F5. Right, we get an a. Right, now let's put a b, right, and run F5, and we get a 24930. And that's because chars is a data type that stores the value of a specific character on your system, and that's defined on, based on which Unicode standard your computer is using. So, an A, it would be some type of combination of 1 and zeros that is defined by the Unicode standard, and this knows to print that A. When we print a B, right here, now this is it doesn't know what that means. It's a whole bunch of 1 and zeros that doesn't really mean anything because there's no char in our Unicode standard that is AB. It doesn't exist. We can do a char, pretty sure like that. That would work because despite the fact that this has a slash, this slash only indicates that this n is the new line character. This slash is not part of the actual char. So this would work, and it's going to print just a new line right here. We can also do /0, which is the null character. This indicates nothing. And when we create a string right here with these double quotes, it is actually just a whole bunch of chars like lined up next to each other. It's just a list of chars pretty much. Like this JK, well, I'm going to, shorten this so I don't have to write out a whole bunch, but this is kind of equivalent to something like JK HD and stuff. And so what's nice about that is, imagine we have a string right here. Remember, I can use string because I said using std string up here. And we say that this string word equals Geobor, right? Now we can say cout Geobor plus A. Let's say just a char A, right? Remember, I used to add other types of words to Geobor. I would do stuff like that. Remember, Geobor is also an object, so we're allowed to, or no, not Geobor, Word. Word is an object, so we're allowed to add on additional data to it, but we're going to get Geobor AD as FSD. And we can also do that Geobor A. And then also we can do that. We can add a char instead of a string, because if you put double quotes, it's a string, and single quotes, it's a char. This is just going to add that A to it as well. And that's because Geobor inherently is a list of just a whole bunch of chars. So it's a char G, E, O, B, O, R. And so we can add a char A to that, which is nice. What we're going to be using chars for right now is we're going to be creating a function, add numbers right here. We're going to rename it to operation. We're going to have int A, int B, and a char this time. We're not going to be using only ints. We're going to be also using a char. And this char is going to be C, because why not? This time, we're going to say an if statement. If C equals plus, then we're going to return A plus B. And do that. Well, actually, I want to put else if. And that looks good, kinda. Let's do something like that. And let's get rid of this else. Or that if. return a b. And this time we're going to be saying this is that, that is that. So now you can probably imagine what this function does just by looking at it. Let's change one more thing that's probably important. So what this function is, if we specify that C is a plus, then we add A and B. If we specify that C is a minus, then we subtract A from B, and so on and so forth. So if we oh wait, something we are missing is these equals. They all have to be double equals. The reason that we do not have an else if here is because we know that if A is not, or if C is not a plus, a minus, or a times, it's probably a divide. The issue with having that else though is that if we put anything else besides like we don't even have to put a divide. We can put an I or a J or an H, and it will think that's divide because it's saying it's only checking for plus, minus, times, and then it's assuming divide if it's not plus, minus, or times right here. That's fine for our use case. Let's declare operation right here, and it's saying that function definition for operation not found. It's because we have to include the new parameters list right here. That the parameters are different now, so there we go. That works now. So let's get rid of the string word, and let's instead cout operation. Let's do 12 minus, and we can't just put a minus like this. This minus has to be a char. So let's put a plus like that. Let's run that. We're getting 24. And if we do minus, we should get a 0. And if we do up here times, we should get like 144. If we do divide, what will we get when we do divide? I'm kind of dumb, so we get 1. I was thinking 0 for some reason. This is the guy that you're learning C++ from. So what's interesting now is that we can just call this function and you can tell it which operation you want it to do right here. And it'll look through here. We're using else if though, because we know, right, if it checks if and C does equal a plus, we don't even need to check the rest of these. We can just return A plus B already and move on with our day. We don't need to check the rest of these. It would not actually check the rest of these though, because remember, return would break from the function and return A plus B. It wouldn't do anything else. Once you hit return inside of a function, it just breaks the function and returns whatever is after the return. So even if these were all ifs, it would not have to do multiple checks. It wouldn't have to do 4 checks anyway. But we're having else if because that is a little bit more coherent. Now, what if we didn't want to specify like this, divide symbol all the time? What if we just wanted to do that and assume that it means we want to add that, right? Well, what we can do is that C equals plus. And so just like if we were to define a variable right here, we can initialize a variable of int num, and we can do that. For a function, or I told you that you shouldn't generally do this. You usually want to assign it some type of value. For a function, you don't really need to assign it any value by default, but if you do assign it a value by default, that allows you to that allows you right here to not specify the value right here. It will just assume the default value. So C by default equals this plus. So we don't have to put in C. We could, though, if we wanted, we could put in, you know, a divide, and it would work. And just like num, we could put in a default value. It's kind of like if you, default values are almost like just putting in right here a 0 for num. While another way to do this is just do int num equals 0. So normally when you do a function, it initializes the variable, so it initializes a, and then it copies over 12 to a. So num, it copies right here 0 over to num. So that's what it normally does. If you have it like this, where C equals plus, it's kind of like just saying num equals 0 right here. And later on, if you put this division symbol right here, you can say, it's like saying num equals 1 later on. It's initializing it to 0 right here by default, but then later on you're copying 1 over to it. And in this same way, it's initializing it to a plus, but you're copying over division symbol to it. So in this case, it should divide. And it says 1, so it does divide. But if we do not put anything, you can see that there's an error. Is that because char C has to be declared like that up there? Or what? Actually, why is that not working? Operation redefinition of default parameter. Bruh. Line 17. Operation redefinition of default argument parameter 1. Redefinition of default argument parameter 1. What's that mean? Is it because we do not need this? Or is it because we only need it right here? Oh, yep. Wait. C. Oh. Right here. Finally. Yeah, this is the guy that you're learning C++ from. This works now. The reason that didn't work last time is because, remember I told you that you cannot do int num equals 1, and then later you can't do int num equals 2. This is not assigning 2 to num. This is creating a new variable called num, but that already exists. This is an error. Well, I did that right here on accident when I said that at the top right here, this is read first by the compiler, so it assigns plus to a C to C. And so when it's defined down here, C doesn't, actually, I'm not even sure that we need this char specifier anymore. No, we do still need the char specifier. But I defined C as plus up here, and then C down here, I also put equals plus, which was like creating C for, it was almost like creating C again when it already existed. So you cannot do that. C just has to be, when you're declaring the function up here, you can assign a default argument, but when defining the function down here, you have to assume that the default arguments are given by the declaration. And so that would probably get a little bit more complex when you're getting your declarations. As I said, these declarations might come from files like iostream or string. And you might get declarations like this, and so you have to make sure to that you're not conflicting the declarations with the definitions. But now this works. So by default, it's going to say that char c equals that, and that means that we don't need to put in a default parameter because it's going to assume that we mean plus if we don't put in anything. Something else though, as I said, we have to put, let me copy this so this is going to be a little bit easier. If we do that and then copy this, now int main is down here. You can kind of see why it's a little bit confusing to have your functions above main, but right here the c equals plus, this works now perfectly fine because we don't have any declarations, so the definition is what assigns the default values. Okay, I'm gonna go take a piss. So next we're gonna be learning about iteration. If we remember, we have string word equals Geobor. Now string right here, we remember it is a std string, word is a string object, and I was talking about how string is actually like a list of chars, characters. And because that is the case, right, what we can do is cout word 1. What does that do? Well, this is an operator. These brackets are an operator called the subscript operator. What this does is this looks into something called an array. An array is pretty much a list of data. In this case, the array would be this string, which is a list of characters. So word 1 would actually be E, because what this does is, what 1 is what's called an index. And an index is going to be at position 1. Or an index is going to be a number that specifies which position in an array we are in. An array is a list of data, as I said. So position 1 is actually E. Position 0 would be G. So if we put position 0, then as you can see, we're going to get a G up here. And position 1, right, we're going to get an E up here. Now, imagine we want to figure out how many positions are in Geobor, right? We can cout word dot size, and this is what's called a class function. I explain these later. This is a function that is called with the dot operator that is specific to a string object. Word is a string object, and so we can call the size function on word using the dot operator right here. Let's press F5. We're going to get 6. Well, why is that? So that's because that's 6 characters long. And so if we wanted to find out how many indexes there are in Geobor, we can just do size minus 1. Because if we check, G would be 0, E would be 1, 2, 3, 4, 5. R would be 5. So it would be the size minus 1, because the size is how many characters there are. The indexes are, they start at 0, so it would be the size minus 1. So we get 5 indexes. Right? That's quite nice. I think there's also another function right here, and it's not specific to words. I think what you can do is you can call size and then just put in word. Let's run this. And we also get 6. And so size right here is a function that is non-specific. It is not specific to word. It can use with a whole bunch of other different types of arrays and such. But we're going to be just using word.size because it has a specific function built in. If you see though, there's a whole bunch of other random functions that it has. You can kind of just look at these. You can look up these functions and figure out what they mean, but we're going to be just going with size. And you have to put those parentheses after it because that's the call operator. We're calling size on word and it's returning some type of value. In this case, the value that it returned was 6. So actually, one thing that I want to show is, well, no, I'll do that later. Imagine now, though, we wanted to see out all of the letters in Word. So how would we figure that out? Imagine we didn't know how many letters are in Word. It was generated by some random part of our program. We have to figure out how many letters are in there. Well, let's put a while loop. While, we're going to say, while index, or while I, or while int I does not equal a condition, while int I equals 0 does not equal word dot size. And we're going to call these right here. Then we're going to put on this, and we're going to say I, we're going to say plus plus I. Or, well, we're going to say first, initially, or not std, we're just going to see out word I, and we're going to also do std and line endl. Then we're going to do plus plus I. Okay, so let's see what this program does. Well, it continues printing 0. And that is because that I is reset to 0 back. I forgot we weren't using a for loop, which is something we'll learn in a little bit. So right here, we can just say int I equals 0. And now we'll run this, and you'll see what happens. This prints out Geobor. So how exactly does this work? Another way you can do this is that, but I quite like not equal to. So the way that this works is first we initialize a string called word, and it's called Geobor. Then we initialize an int I. I'm saying as a shorthand for iterator, and iterator as an iteration, as in going one at a time. So this iterator is initially going to be at 0, right? And we're going to say while I equals 0 right now, does not equal word.size. So word.size is probably 6, right? While I does not equal 6, this is going to be true. So while that means while I does not equal 6, we're going to print out word I, word being Geobor, I initially being 0. So while I does not equal 6, we're going to print we're going to print word I, so word 0, then we're going to do plus plus I. The plus plus operator, what that does is it's the increment operator, or the prefix increment operator. What that does is it adds 1 to I. And that's it. So that means that I after this is going to equal 2. So while we go through this loop, what's going to happen is that it's going to check, does I equal word.size? No. Okay. So then print out word I and add 1 to I. So initially I is going to be 0. It's going to say, okay, this is true. So print word 0, which is G, and then add 1 to I. Then it's going to go through, okay, does I equal 6? No. So print word 1, because I now equals 1, and then add 1 to I. Now I equals 2. So it's going to keep going till it hits 6, and it's going to say, okay, so does I equal 6? Well, yes, so this is false, and then it's going to not execute the code inside the while loop. Now, let's go through some of this stuff. This plus plus operator, there's 2 different versions of this plus plus operator. There is plus plus I, or there's I plus plus. And now what that does is plus plus I, if we had another variable, I'm just going to do that. What this would do is variable is not an actual variable, but if we had something like this, then it would assign I plus 1 to variable and then increment I. So in this situation, if I was 0, I is going to equal 1 and var is going to equal 1. If we had a similar situation down here, what's going to happen is var is going to equal what's going to happen is that imagine I initially equals 0. var is going to equal 0, and then I is going to equal 1, because it's going to assign whatever is I to var, and then add 1 to I. You can kind of think of it as what is closest to var is what's going to happen first. So if I is closer to var, it's going to assign I to var first, and then add. And then if plus plus is closer to var, then it's going to assign I plus 1 to var. And you generally want to use the prefix operator unless there's a very specific reason to use the postfix operator, which is this one. You most of the time use this one unless you need to use this one for a specific purpose, and you might find purposes that would be useful for. And a place that would be useful for is, well, I'm actually not sure right now, but I was actually going to explain the reason that you don't want to use the postfix operator is because what this operator does is the postfix operator, well, it says, well, we need I to, if you remember plus equals, I plus equals 1, and then var equals I. That's what it does. So our temp and then var equals temp, which equals I. So the reason that you don't want to use the postfix operator is because what it does is it creates a temporary variable right here. It assigns that to var, and then it assigns I to I plus 1. So that temporary variable, it causes a tiny bit of a slowdown. It's just better to use the prefix operator most of the time. If you need to use the postfix operator, then use the postfix operator. But prefix operator will not generate a temporary variable for your thing, because it's first going to add one to I and then assign it. It doesn't have to save the variable. It doesn't have to save a version of the variable not added one and then plus 1, like the postfix operator, because the postfix operator has to have one variable that is I's previous value and then one variable that is I's new value. I also was showing operations like plus equals. If you remember what plus equals mean, if we have like var plus equals 1, that's the same thing as var equals var plus 1, except the plus equals 1 is a little bit more efficient for reasons that I forgot. I don't even know anymore. What else? There is also, besides plus equals, there is minus equals, there is times equals, and there is divide equals. And those just do what you would expect them to do. In terms of the increment operator, there's the plus plus, and there's also minus minus for the decrement operator. And it just does the exact same thing as plus plus I, except for what minus is instead. Well, let's do that. And as you can see, this statement can stand alone because it has both an operator and a variable. So now that we're taking a look at that, take a look at here. So constantly, as this loop is going on, its value is changing. And so initially I is going to be 0, so it's going to print word 0, which is Geobor, then word 1, which is E, or word 0, which is G, then E, then O, then B, O, R. So that's how that works. You can, I said not equals right here. You can also use less than, but generally people use not equals in C++. I'm actually not sure why. Not equals might be a little bit more efficient or something like that. Now, I remember when I had more of a syntax looking like this. Int I equals 0. And let's run this. Let's see what happens. This keeps printing E. Okay, the reason that it keeps printing E is because actually, why does it keep printing E? Int I equals 0. It should be printing G, but at some point that would mean, right, that would suggest that I is constantly 1, which would be strange at the very least. I actually do not know why. I guess that's probably why you do not want to reinitialize variables up top here constantly. The reason it's erroring out is because we're reinitializing a variable every single time. What you want to do with while loops is you want to say I. Most people use I, so I is pretty much a shorthand for scenarios like this, because when people need to iterate over something like a word, then they'll use I. Imagine, right, we wanted to do something else besides just print out all of them, right? We wanted to say, all right, if, let's actually make some space for our if statement. Let's say if word I w equals O, and this has to be a char because word I would be any index or any char inside of word. And if it equals O, then what we want to do is we want to say word I equals A, maybe. Why not? And remember, if statements, they do not require brackets. They only require a body. And the reason that this works is because this body is going to be just this word thing. The curly brackets are only required if you're going to have multiple lines. So that's also the same thing with while loops. While loops do not require these curly brackets. They only require those curly brackets if you want multiple lines. Let's run this though. And I forgot to do something. Let's cout word and okay. Now we see GEABAR, because what this loop does, you can probably imagine, is it says, okay, so it goes through every single I inside of word, and it finds, okay, so if word I, so for example, this could be word 2, which is an O. If word 2 equals O, word 2 does equal O, as you can see, then word 2 equals A. So it changes word 2 to A. And let's try that. It works. We can also change this to a G, and it's going to change them to G's instead. Let's keep it at A, and let's change this to B. And it's going to find every single B inside of it and change it to an A. So if we add a whole bunch of B's in here, there's going to be no B's because they're all going to be A's, which I don't know why I did it like that. That just makes it hard to see. Yep. So that's an example of something that you can do. Now, this word.size function, as I said, functions are not super efficient. So if you're going for something that needs to be super efficient and needs to run super fast, what you might want to do is you could save this I, or this word.size function into an int. So you can say, well, since I already have an int here, let's actually just define another one. So we're going to say int s for size equals word.size, right? So now s should equal 6. So we can just put s here instead. And so what happens now is that instead of, or it's going to call the word.size function once, and it's going to say, okay, that's 6. So s is now 6. And then it's just going to keep asking, does I equal 6? Instead of does I equal word.size? And because it had to call word.size every single time, that was a little bit slow. So we can do that, and it does the exact same thing. But instead of calling word.size a whole bunch of times, it just knows 6 right here. Now this runs into an issue. Let's put back the word.size thing, right? And let's say, what if we wanted to do something like what if we want to do something like how do I describe this? Word plus equals a. As you can see, this is not doing anything. It is eating up RAM. That's the only thing it is doing. And the reason for that is because this while loop never stops. It just continuously adds A's to the word and then checks word.size, because word.size continues increasing because every single time we're adding an A to it, so it's continuously increasing. So sometimes you might want to add stuff to the word and still iterate through it. Like, for example, what you could do is let's bring back that if statement actually. If word equals that word plus equals A. So if it finds an O, it's going to add an A to word. So let's do this. And it's going to add two A's because there was two O's. Now, what happens though? You might do something like that, and you might add extra size to the object that you're iterating through. In this case, that object is word. And you might want to look through that extra size at the same time. And in this case, that word.size function is fine, because as you increase the size, it's going to continuously increase the amount of indexes that you have to search. So if the size is 6 and you add 1, the size is going to be 7. So now you're going to search an extra spot. If, for example, you used s instead of word.size, it will not search through the new stuff that you add to your word. So it will only search through the first 6 spots because s equals word.size. Word.size is not increasing anymore. Or because s is not increasing, because s only is specified as word.size right here. It's not specified as word.size down here. So it's only going to search through the first 6. And that might be an issue sometimes. Not actually an issue in this case, but because if we run it, it's going to say the same thing. That's because there is no O's after the first 6 characters. So it doesn't matter in this case. But in some cases, it could matter. And in that case, you don't want to use an S. You probably want to either call word.size here, or you want to say, after you add that, S plus, or after you add this, you could do something like and then you can just say S up here. So this would do a similar thing. It would be a tiny bit more efficient than word.size though, because instead of calling the word.size function every single time, this time we're going to call it once, find the initial size, and then every single time we increase the size, we're going to add 1 to S. Now again, we're doing something very, very, very simple. So these optimizations that I'm doing right here to search through 5 characters or 6 characters, it's not super necessary. We don't need to, optimize the search through 6 characters. It's going to go extremely fast anyway. But if you were doing something that is going thousands and millions of times a second, then you might want to take into account some optimizations like this. And we'll be trying to do something that happens millions of times a second later in this program. But you see this whole while loop is kind of like messy. Let's make something a little bit easier. So we're going to get rid of this right here. And instead we're going to say a for loop. So for int I equals 0, Then we're going to say I does not equal, nope, that's not what I wanted. Or we don't need std. So this is what's called a for loop. In the syntax for a for loop, well, actually, let me do one thing right here. We're going to end line. So the syntax for a for loop is initially we put one expression right here. And this expression, what it does is instead of saying int I equals 0 up here, we can actually get rid of this. We can just define that int I right into the side of this for loop. Then what we can do is we can say I does not equal word.size. In a while loop, we had that condition that we checked every single time, right? This is that condition in a for loop. So we check this condition in the for loop every single time we pass through the for loop. So the for loop is going to continue going as long as I does not equal word.size, which is 6. And then this last expression right here is a piece of code to execute after every single loop of the for loop. And in this case, what we're going to be executing is plus plus I. We just want to add 1 to I because we're going to be going through every single index in Word. So we're going to just add 1 to I. Something else we can note is that you don't have to put any statements. You can put blank statements for these. So if you don't need to, for example, define a variable right here, you don't have to. You don't have to initialize any variable I. What's nice about a for loop as well is that this I variable is local to the for loop. This means that nothing else sees that I variable. That means that you can reuse that I variable. You can remake that same I inside of every single for loop that you use because it's local to the for loop. It gets destroyed after the for loop ends. And so if you had, for example, I up here and you said I equals 0, you can't just, well, you can reuse I for every single while loop you have, but this I, it would be kind of tricky and you wouldn't be sure that I doesn't have some leftover index in it, because I right here, if you specified int I equals 0, maybe after it comes out of the for loop, now I equals 12, and you would have to reset it back to 0 next time you enter a loop and want to use the same I, or you would have to just create another variable. This way though, this I is local to the for loop, so this I is created specifically to iterate through the for loop, and it is destroyed after the for loop. Let's run this. Let's see that we get Geobor and Geobor at the end right here. This for loop can do pretty much every single thing that that previous while loop could do, just much more condensed. Right here, as I said again, we first define or initialize a variable to use, then we put a condition to check, and then we put a statement to write at the end. So we're going to increment I. We're going to say I or plus plus I because we just want to do it for every single index I. And then we're going to print out I right here, or word I. There's another for loop, which is a little bit more simple. Let's do that. So the syntax for this for loop would be a little bit more like for char C in Word. And what's nice about this for loop is this for loop right here, you don't have to use I and you don't have to specify like word I. What this does is it automatically creates or it automatically assigns C to every single index of Word. So instead of, having, Word I and I could equal 1 or 2 or 3 or 4 or 5, it just has C, and C, it automatically assigns it to Word 1 and 2 and 3 and 4. So it's a lot easier to use. C is automatically assigned to those variables. If we check though, so C is initially going to be word 0. Word 0 is going to be G. Then C is going to be word 1, which is E. Then C is going to be word 2, which is O. And it keeps going like that. Reason we specify char here instead of int is because last time we were adding 1 to the integer so we could find that index inside of Word. This time around, they're automatically finding that index for us. We're just giving a char variable because every single index contains a char. This string is made up of a whole bunch of chars. And so we define C to hold those chars when it iterates through those indexes. Now, some issues with this for loop. Imagine you can't work with those indexes directly. You can't say like C. Well, if you had something like word 1, right? You could add 1. You could say like word 1 plus 1 to get the next value in there. Since we do not have an I though, you would normally do like word I plus 1. We don't have an I in here though. We don't have any thing. Like if we wanted to find out, if we wanted to, for example, change every character after an O to an A, like if we wanted to do that, we would do something like we would find I, and then we would add 1 to I to find the thing that is right after I. So if I is 2, I plus 1 would equal 3, and we would be at this B. We cannot do that here. We don't have any word I, we only have C. If you're doing something simple and only iterating through these characters, then that's fine. If you want to do any math with the I, then you should use the previous for loop. Another issue with this for loop, you cannot change the size of word in this for loop at all. You cannot change the size. It will have undefined behavior. So, for example, if we, for char C in Word, if we just start adding extra chars to the word, then it breaks the for loop. The for loop starts having undefined behavior. It does not allow it, does not work. So, yeah, that's that for loop. Let's see. What else do we have to think of? Those are most of the loops. Let's think of a switch statement. So, remember if we did if instead of doing like if I equals 1, then do stuff, and then what we would have to do here is we would have to put else if and then imagine we have a scenario something like this. And what's going to happen is that if this was a much longer list, it is certainly better than a whole bunch of if statements, right? But imagine we have this in a super long list. We want to check, all right, does I equal 1, 2, 3, 4, 5, 6, 7, 8, all the way up to like, 10,000, something like that. Or not really 10,000, but imagine we got to check a whole bunch of stuff. What we can do is we can use something called a switch statement instead of doing all this. And a switch statement is used specifically for scenarios where you're checking if one variable equals one specific value. But so like if I equals 1 or 2 or 3 or 4, not if like I is less than 1 or I plus 2 equals 5 or anything like that. No complicated math. This is specifically to check what the value of I is. You use something called a switch statement. So switch, you say case. Oh, let me actually look up the syntax of a switch statement because I forgot. Right here. So switch, and you put in a variable that you're going to be checking. So I in this case. Let's do word because it actually exists. Must have integral or enum type. I forgot. That's kind of sad. Let's do int num equals 1. And we're going to put in num for this. Then we're going to say case 1 cout 1, and then we're also going to do and then last thing we have to do is break. And now what we can do is copy this. And you can put, enter behind all these breaks. And then you can change this to like that. And we're also going to change this to 3, 4, 5. Right here. So what this does is, as you saw, this requires either a int or enum type. Let me check if you can actually do like a char. I'm not sure. A char seems to work, but you cannot do like a string. String does not work. So I'm pretty sure the reason for that is this has to be like a specifically like a single character type of thing, type of ordeal. I don't even know if you can put like, yeah, you can put 12 because 12 is defined as a single number. But you would have to put in pretty much either a char or an enum, which we didn't learn about, or an integer in here, and these cases would be in the case. We can just kind of ask or say it in this way. In the case that num is a 1, do this stuff. In the case that num is a 2, do this stuff. In the case that num is a 3, do this stuff. Now num right now equals 1, and so if we ran this, we should see that we see out 1. And that is correct. We see out 1 right here. And it printed Geobor because Geobor is right there. Break right here tells us that after we do whatever is in here, break, because the switch statement is over. If we remove this break right here, it would not indicate that the switch statement is over. And so in that case, what it would do, it would print 2, because after a switch statement only jumps directly to each of these cases. So when a switch statement sees a 1, it will jump to case 1, and then it will execute everything linearly down, just down the line. It ignores all the rest of the cases. So even if it will execute everything that's in case 2. In this case, why it only printed 2 and not 3 is because it executes everything in case 2 and then breaks. Break is kind of like return for a function. So return ends the function and destroys everything inside the function, and goes back to the caller. So what break does is break will end the switch statement and jump back to the bottom right here. So these cases almost act like headers for the num. So in the case that it's like, if num is 1, start here and start executing code. Like start at this header 1 and start executing code. If it's 3, start at the 3 header and start executing code downwards. And it will execute everything in the rest of these headers. You cannot normally define variables inside of a switch statement. So generally, you can't do something like int num equals, or int num1 equals 12. And let's run this. And it says that num1 is skipped by case label. And what that means is that I forgot the exact reason, but you cannot initialize variables inside of switch statements. You can, however, I think if you have something like a block like this, and you int num1 equals 12, you can have something like this. I'm pretty sure this should be good. Yep. And so this is kind of like a block, like almost like a function block right here. If you see, it looks like that, except this is unnamed, and so there's not much of a reason to do this. It will execute the code in here, but there's not much of a reason to have an unnamed block like that. The only reason you would use this is because it allows you to define variables inside of a switch statement. The reason, actually, I remember now why you cannot define variables inside of a switch statement or initialize variables inside of a switch statement is because the switch statement is all in the same block, and a block is similar to a namespace in the context that a block, when a variable is defined inside of a block, everything inside of that block has to have access to it. But case 2 would not have access to a variable up here because case 2 would skip the initialization of that variable. But it has to have, case 2 has to have access to that variable because it's in the same block. But it's skipping the initialization of the variable, which would break things. So you're not allowed to do that. That might be a good way to transition to what are blocks. Let's get rid of this switch statement. Let's think about what is a block exactly. So a block is like these curly brackets around the main function, and inside of a block, any object. So if we created, for example, some code out here, we cannot say num equals 20, because num, even though num is up here, it's above this. The issue is that num right here, or this num variable, is what's called out of scope. So it does not exist to the num outside of this main function, because this block is the num right here cannot see anything inside of this block. So if you have what's out here, anything out here cannot see what's inside of that main function. And the way that you would get them to see what's inside of functions is this wouldn't work with functions, but I think you could, maybe this does work with functions, I'm not sure. But yeah, this generally wouldn't work with functions. There's other types of blocks that this would work with, but functions, you can't really redefine the behavior outside of the function block. It doesn't allow you to do that. Now, inside of here, though, imagine we have an int num2 equals 0, or let's set it equal to 2. Int num1 equals 1 plus num2. This does work, because anything that is in a block can see every single thing that is outside of this block, that is on the previous level of this block. So this is in the global block, because there's no curly brackets around it. So this is in the global scope. This is another name for block is scope. We're going to be using that now. So this is in global scope. And people don't like variables that are in global scope, because imagine I have a whole bunch of different functions, and each of those functions normally won't interact. So if I had a function int Geobor, this int Geobor function could also use the num variable, because it could make its own num variable. And I also have to return, just to get this to not yell at me. And let's also do that so this function is a little bit nicer. Why is this yelling at me? There we go. And we don't actually need this because that's a function. But as you can now see here, after my trials and tribulations, you can see that we have our own num variable right here. And this num variable is completely separate from here, because this block does, or this scope, this Geobor scope, does not interact with this main scope. However, this Geobor can access the global scope, and this is in the global scope. Imagine I'm trying to use a variable, right? I'm trying to use a variable. I'm trying to make a variable called num2. I can't make a variable called num2 because num2 already exists. Unless I do that, that should be fine. I actually can make a variable called num2, but it starts getting confusing when I'm like, I do something like cout num2. Am I printing out this num2 right here or this num2 right here? You can't really be sure. If I do this, well, I need to call this function. Let's call let's just do this for now. A void function, I can explain that very quickly. Void function is a function that returns nothing. It doesn't need to return anything. And since this function is just printing out something, it doesn't need to return anything. So we're going to have it as a void function. And we still have errors. Where are these errors at? Geobor identifier not found. Because we need Geobor up here. Now, what's happening? This function doesn't return anything, as you can see, but now it's printing out num2 right here. Num2 is 20. It's printing out 20. Okay. So what if we get rid of this, right? So obviously it's printing out this num2. Even if we get rid of this, though, it's not saying that there's invalid syntax, because now it's using this num2. And so now it's printing out 2. But okay, we can still initialize a num2 like that, but now we can also just say num2 equals 18. And this is just as valid right here. Because now what's going on is this function is taking this num2 right here and it's changing it to 18 and then printing it out. So it's just very confusing on how exactly global variables work and whether you're trying to print out a global variable or a non-global variable. Let's imagine, right? We have int num2 equals that. Imagine I want to access this variable now, this num2 right here. How do I get access to that? Well, use the scope operator right here. And you put nothing before it, and that indicates that you want to use global scope. And so that would just be this num2. And it gets very, very confusing. So it's kind of a taboo in C++ to use global variables. People don't like them, generally. Because global variables will affect every single function that is in the file. And so it's very not nice. Let's see. Let's get rid of this. Scope is going to come into play more when we start getting into classes and structs and such, but mostly classes. Let's think about what do I want to go through next. I think we're going to go through references, pointers, iterators. Then we're going to go through structs, vectors. Then we're going to go through classes. And then we're going to build a final app, and then this tutorial is going to be finished. Who knew that recording yourself for 5 hours or something like that is crazy difficult on your voice? I had to eat something, take a rest for an hour, but now we're continuing the tutorial, finally. I researched a little bit of things, and this is what I've determined we have left to figure out in this tutorial. We're going to go through arrays, constants, classes, constructors, preprocessor directives, structs, vectors, floats, references, pointers, iterators, the compiler, and then revisit returning string literals in a function. So initially, we're going to start this with arrays. So if you remember correctly, this Geobor string is what I said is it's a list of characters, and you could iterate through them. Now that's all fine and nice, but it's a little bit there's a little bit of other things that you can do with these list type objects. These objects are actually not called lists, they're called arrays. And for example, if we wanted to create an array, we would say int array, and this doesn't have to be an array, or this doesn't have to be array, we can specify whatever. And then we put this. This can just be, let's just call it nums, because this is going to be an array called nums. And we're going to hold 5 objects in here. And let's say these objects are 0. Let's say 5, 4, 3, 2, 1. So 5 objects in here. This number that you have to input is a number of objects that you're planning to store in this array. You don't have to specify every single object. For example, I could say there's 5 objects in this array and only give it 3 objects right here. Let me put a semicolon so this is nice. I can only specify 3 objects. In this case, these last 2 objects are what's going to be called value initialized. They're going to be initialized to the same value as they would be initialized if I just typed int num. So they're going to be default initialized to whatever an int returns. In this case, that would probably be 0, which isn't a super big deal. Most of the time, if you're using these static arrays, though, you're going to be knowing all of the stuff that you put inside of it beforehand. Now, let's say that, let's say that this has the 2 and the 1 in here. What happens if we, for example, specify 3? This gets angry at us. It does not work. If we specify 5, this is correct. Now, the only reason that your program currently knows that this is an array is because this operator right here, this identifier right here, specifically tells the nums, or specifically tells the program that nums is an array. It's an array and it's full of type int. So in this array currently we have on the index 0 we have 5, then 4, then 3, then 2, then 1, and 1 is an index 4 because this is 0, 1, 2, 3, 4. If we write a for loop for let's just say n, or int n nums, cout n end a line. Let's run this. This works. It just says 5, 4, 3, 2, 1. Very simple. And you should remember how this for loop works. It just assigns n to each index of this array. And a string that we used previously acts just like an array. The difference between a string and array is this array is static. We cannot add anything to this array. We can change what is in this array. So we can say n equals 1, and then let's write another for loop right here. Cout n, and then let's run this, and that was strange. for int n in nums. Let me try something else. We're going to use the different form of the for loop. So int n or int I equals 0. I is not greater than nums dot. And what you notice here, nums does not have a size function. That previous default size function right here is now what we have to use on nums, because nums does not include its own size function. We might have to do std size as well to get this to work, because size is a function that's probably defined inside the std namespace. Right here, we're going to put ++I, and we're going to say, after all is said and done, nums I equals 1. And we're going to put a, and now this works. So what you can see here is that we're changing every single item inside of the nums array into a 1. And then down here, we're iterating through every single number inside the nums array and returning a 1. Let me check something else though. I just want to see something, if something works. Because if we remember, this did not work. Let's see, int n in nums. Actually, I'm not entirely sure. I might have been doing something wrong my entire C++ existence. Let me check. Do these for loops even need those semicolons? Let's see. I'm going to do something that you guys probably will not know. We're going to say equals. Let's run it. And those build errors. Let's run this once again. And this still does not work. Okay. Okay, I see what happened here. In this context, we would have to use something called a reference, which we did not learn yet. But this would work if I did this, and then I said n equals 1. And now we get all ones. And we'll learn what this reference is later. But that's how arrays work. Now, the thing with arrays, and this is the same thing with a string, if you try to access an item that is not in the array, so for example, if I tried to access a nums index 5, right, because this ends at index 4 right here, this is index 4. If I tried to access index 5, it would check what is in the next spot, what is the next memory address that comes after the index, what comes after the loop, the array, and it would just see some random arrangement of the zeros and ones, and it would try to interpret that as an integer, for example, giving us undefined behavior. And that's why you cannot access something that is outside of the range for an array or a string or any iterable object, any container type. A container type is a type of object, an object like nums right here. that holds other objects. Nums in this example holds integers. So you are not allowed to reference an index that does not exist within this array, and that's the same thing with strings. It creates undefined behavior, which is a very, very common cause of a bunch of bugs and errors and crashes in programs. Let's look at quite an interesting object, I think. So we're going to be looking next at something called a struct. So if we create a struct here, struct, and then you do that, and within this struct you put actually, before I create this struct, let's test if these for loops require semicolons, or if I've been doing it wrong my whole existence. Let's put this here, because I very well may have been writing C++ wrong my entire existence. Again, this is the guy that you're learning C++ from. Why? So apparently for loops do not require semicolons to be at the end of them, which is very strange. I don't know if that's a Visual Studio exclusive feature, but apparently they do not require it. Okay, so right here we're going to be writing struct, and this is going to create a data structure. We're going to say right here that inside of this struct is going to be, well, actually we should name this struct first and foremost. This struct is going to be a book, and we're going to say that this book has int, or actually let's do a float price equals 24.99f. And let's say, well, let's put a semicolon here. Let's say that we have a string title equals, this title is well, actually I should not put that. I should put probably 0.0, and this title is just going to be an empty string. Now what we can do is we can say book 1 equals, or we can just say book 1, then book 1 dot price equals 24.99f, and book 1 dot title equals the adventures of Geobor. Okay, now what we're going to do is we're going to do std, or we don't need std, we can just do cout book 1 dot price book, or let's do a space, probably do that, right? Dot title. And let's also do one more thing. I'm actually going to say, like, using declaration up here. Now let's run this and let's see what we get out. 24.99, The Adventures of Geobor. What is it? What exactly is going on here? Well, initially we can see that down here we are printing out a book1.price object and then a space and then a book1.title object. Well, let's see, what does book1.price equal? Book1.price is 24.99. Then we have the space here. Then we have the book1.title object, which is The Adventures of Geobor. We can see up here that this book1.title was assigned to The Adventures of Geobor. Okay, that makes sense. Book1.price was assigned to 24.99f. Interesting. And then we say up here book1 or book1. Well, what exactly is going on here? Well, a book object, as you can see, this book1 initialization is initializing an object or a variable called book1 with a type of book. This book1 object has a type of book. It's just like putting int num1, except we're saying instead of num1 we're saying book1, instead of int we're saying book. So num1 would be, we would have an object num1 of type int, we would have object book1 of type book. Now where does this book type come from? Well, up here we can see this keyword struct and this variable or this name book. Well, how exactly does this work? Well, we have this is what's called a struct, and it creates our own data type. Right here we can define these parentheses, and within this data type we're saying two things. We're saying that a book data type includes a price that is represented with a float, and it includes, or well, there's a better way to say it includes a price object of type float, and includes a title object of type string right here. So whenever we create a book object, every single book is going to include a price and a title object. If we see, a float is an integer, except it has a float is an integer that has decimals. Now, if you've ever heard of something called floating point precision, and that is talking about these float data types right here. So a float by default has some type of precision value. Maybe it could be precise up to the first 13 decimal points. So you could write a float up to 13 decimal points and put a 1, and it would accurately calculate that. But any more, and it would not be able to accurately hold that. That's what a float is. It's an object that can hold up to that many. It's an object that holds decimal points pretty much, and it holds up to a specific amount of decimal points based on its precision. And so a float right here might be 32 bits, and there's other types of floats. So another type of float that we can say is double. And a double is a double precision float, a float that can hold twice the amount of decimal points because it is twice as precise. It's 64 bits perhaps. And then what we could do is type in long double, and that might be 128 bits, and it could hold twice as much decimal points again. What happens when you exceed the amount of decimal points that a float can hold is that it can no longer accurately tell you how it can no longer accurately tell you the value that you put in for that float. So a float right here with too many decimal points, with too many zeros, would not be able to accurately hold this one. It would give you probably some very random number. And when you put in maybe a 0.25 right here, like that, it probably is not actually holding a 0.25. It's probably holding like 0.24999999, like that. And that is just because the precision of this floating point is not 100%. Now, we have this little f at the end of this number right here. What this f signifies is that this number is a float. Let's get rid of it. Now, it's saying that this is, if you can see that, I don't know if you can see that, it says it's a double. By default, when you create a decimal point in C++, it will automatically be of type double. So just like how there is string literals and how there is integer literals, which do not include W's, just like how there's string literals and integer literals, there's also floating point literals, and these floating point literals by default are of type double. If you hover over this right here, if we say int num equals this, if you hover over it, it's saying that it's an integer. And that's because a number literal like this is by default an integer. We also could do long right here, but if we hover over this, it still says integer. What's happening when we assign an integer to a long is that it automatically converts this integer to a long. And an integer is easy to convert to a long, so that's not an issue. The compiler can do that automatically. But imagine we didn't want to convert it. We wanted to specify that this exactly is a long. You could put like an L, and now this is a long. What if you put in an LL? Well, now this is a long, and you're trying to put it into a long. So let's there's a whole bunch of different things like this. There is with capital L's, which is generally a better idea. There's F, which indicates floating point. And you would probably want to put a 0 like that, and then F. And then a floating point, this would be a floating point, and you would try to assign it to a long. Floating points can be assigned to longs or ints, and they can be automatically converted to a long. They can be automatically converted to an integer or a long just by removing this decimal point. If you convert a floating point or any number with a decimal to an integer, no matter how high this 99999 is, it automatically just gets rid of this. It automatically just changes it to a 0. If it's 0.25, rounds it down. If it's 0.5, rounds it down. If it's 0.6, rounds it down. 7, rounds it down. It truncates this number by default. Now, if we do not have this F here, what happens is that this is no longer an integer. This is what's called a double, and I said a double is an integer, but double precision. And so if you were to assign, for example, if you wanted to specifically use floats and you assigned this number to your float, you wouldn't be assigning a float to your float. You would be assigning a double to your float, and then you would have to convert that double into a float. What you can do instead is you can specifically specify that this is in fact a float by putting that F right there. And so it does not have to convert this to a float anymore. It just automatically knows that, oh yeah, that is a float. And it's going to be stored like a float. No conversion needed to be done. And so we're storing a float or a price object of type float right here, defined by a float literal right here. And the price by default, we're going to set it to 0.0. And we're going to set we don't need this int number. Now, actually, I used floats right here, but we're using such a simple program right now. There's not really any issue with just using simple doubles. And double, like int, is the default for a number with a decimal in C++. And so this, by default, is going to be a double. Generally, double precision is not much more complicated to perform operations on than a float of type single precision. And so, especially when you're using simple programs like this, you can reasonably confidently use double precision without any second thought. It's simpler. You type double and you type the 0.0, and by default this 0.0 will be a double. The way that you make it a float or something else is you have to specifically specify that it is a literal of type float by putting an F right there. Right here we set book1.price to 24.99 F. So we set that to a float. I'm going to set this just to a regular double because we're using a small program. Double is probably not a big issue. Now let's take a look at exactly what this does. This obviously this struct book. So this book signifies that we're creating a book data type, and this data type includes the double price, includes the string title, and these are default initializers. So when we create an object of type int, for example, int num, generally, if you were to imagine that there was a struct like this, similar to book, but this time it defines num it defines int instead of book, you can imagine that this num object or this int struct would have some type of default value for when you create an integer. And that default value for an integer is generally a 0. Right here, we are specifying that the default value whenever we create a book is 0.0 for the price, and the default value for the title when we create a book is an empty string right here. And that is just like initializing. That's just like if we initialized an integer right here and we did not provide it a value, it would have its default value. So if we go down here, we have this book right here. We're saying book one, book. So book one is a object of type book, and we're initializing it right here. And so this book one object is given the default values of the book struct. This book struct default values is 0.0 and an empty string. So that means this book one includes a price that is equal to 0.0 and a title that is equal to nothing. Right here, we say that book1.price equals 24.99. Remember, when we used the dot operator previously, we were using the dot operator to, for example, call if we had a string word equals Geobor, we would say word dot size, if you remember. Now, what this dot operator does is it says, find inside of the left-hand object, the thing on the left-hand side has to be an object. Find the right-hand size, or the right-hand side method or object. This in this context, the thing on the left-hand side of this dot operator in word.size, the left-hand side is a variable word of type string. So that means that string includes a function called size. And so when we use this dot operator, we're saying find inside of this string the function size. And we do a similar thing when we say book1.price. We're saying inside of book one, well, what is book one? Book one is an object of type book. So inside of a book object, find the price object. And the price object inside of this, inside of a book object, is a double that is default initialized to 0.0. And so we're going to assign it this time to 24.99. And so we do the same thing with the title. And now we have our own unique book called book one that has its own price and title. Now we could also do almost the same thing. Well, what if we wanted another book? Well, just like we can create another num, we can create another book, and we can say book2.price and book2.title equals these same things. So now book2.price is 19.99 and book2.title is the Adventures of Hillary Clinton. Now we can go down here, let's put another cout, and let's change these to book2.price and book2.title. When we are printing them out right here, this dot operator is doing the same thing. It's saying, okay, look inside the book2 object and find the price object inside of there. And the price object inside of book2 is 19.99, so we should see that this says 19.99, The Adventures of Hillary Clinton. This should say 24.99, The Adventures of Geobor. Let's press F5. Let's take a look. And that is exactly what it does. That's generally how these data types work. Now, as with when I was using something like word.size, size is a function. If you remember what a function is, it's a function like int main, except specifically included inside of the string data type. Now, structs do not support functions. You cannot make a function inside of this struct. I could not say, for example, add 1, or I could not say like double add 1. And let's say price plus equals 1. This, theoretically at the very least, should not work. So I'm gonna, right here, actually, I want to add, instead of just an integer 1, you can add an integer to a double right here, right? Because the price, if we see the price is a double, we want to, if we're adding 1 to the price, it's probably better to add it as a double instead of an integer. You can add an integer to a double, but sometimes some wonky stuff happens if you do that, so it's better to avoid that if you can. Let's add 1 to the price. And in this book1.price section, let's just say that, let's just call book1 dot add 1. And as you can see, this does not work. This add 1, if this was a data type such as string does include functions that look like this into itself, but a struct does not support functions like this being added into its data type. You cannot call a function from a struct. A struct is specifically a data type that only holds data and not functions. And so you cannot call a function with the dot operator on an object that is a struct. String is not a struct, so you can call the dot operator and call the size function on the string. Let's get rid of this. You can, however, just normally take book1.price, and you can say book1.price plus equals 1. And now it's 25.99 because we added 1 to it. And you can also make a function out here called add 1 or double add 1. And let's say turn, this is going to take a double D. We're going to say D plus 1.0. We can also call book1.price equals add 1 book1 dot price. And I have to put that there. And that should work, but it's breaking for some reason. Let's see. What is exactly breaking? Add 1 identifier not found. It's because I did not specify that this function exists. So let's do that right here. Now let's run this. Now we can see we got 25.99. So this right here is a function that does not exist within a specific data type. This is not a class function. This is a regular function down here called add 1. A class function would be a function that is specifically tailored to a data type. So if we had a data type that actually could include functions, a struct does not define a data type that can include functions. But if we did, we're going to figure out how to do that later. So right now, we cannot use the dot operator to call any functions on book1, but we can call an external function and then pass book1 into it right here. That is generally how a struct works. And book1.price, what this dot operator does specifically is it returns this price object right here. So this whole statement right here evaluates to this price object, which equals 0.0. So if I could assign, for example, book2.price to book1.price. So book1.price equals book2.price. Just because book1.price evaluates to 24.99 and the book2.price evaluates 19.99, you can assign the 19.99 to book1.price. And both of them are the same value. Let's get rid of these because this code is getting a little bit messy. Let's talk about some other things. Let's get rid of this. Next, we're going to be talking about references and pointers now. So imagine we have a variable a, right? Or no, let's have a variable num. So int num equals 1. Right? What we can say is we can also specify another variable, int num, but we can do this equals num. And actually let's change this to num r for reference, because what is going on right here is that we are making a reference, and you can see that Visual Studio automatically moved this little ampersand over to the left. That's because that's usually the proper syntax. That's usually what people do. I'm just a bad programmer, so I use the improper syntax. But now that we got the proper syntax, let's see out num r. Okay. We get 1. Okay. We get 10. So how is this any different from just creating a regular variable called num_r and assigning num to it? Because if we see here, we still get a 10. So how is this any different? Well, what happens if we say now num_r equals 5, right? We would imagine, well, num_r equals 5, and then we're going to see out num_r, so we should get a 5. And we do. But now, let's see out num . 5 and 5. So right here, we assigned num to 10, so num equals 10. Then we assigned the reference num_r, or we assigned num_r as what's called a reference to num. Right here, this ampersand, if it's on the left side of the equals equation, it signifies that we're assigning this num_r as a reference, an int reference to num. Now, a reference is not an object. It does not take up any space. It does not take up any data. This reference right here, it creates a reference. And we can see what type of reference it is by looking at this type specifier. This type specifier is int. So that means, okay, we are referencing an int. This ampersand signifies that it's a reference. If this ampersand wasn't here, this would just be a regular int object. If we do that, now it's not an object, it is a reference. And so this is an integer reference called num_r, and it references the object num. Now what reference is, it's almost like another name for num. It's almost like we gave num another name, num_r. Num_r is pretty much an alias to num. So when we assign something to num_r, 5 right here, what we're really doing is we're assigning it to num, which means that when we assign the 5 to num_r, we're assigning it to num. But num_r is num, so num also equals 5. Num and num_r both equal 5. And so when we print num and num_r, then we get 5 for both of them. Now, what this entails is a few different things. I said that num_r is not a object. It does not store any data. So what that means is that we could not, for example, we could not say that int num_r, not this, we cannot say that int num_r equals 56. And this is not working. Why is that? Well, as I said, num_r is a reference to an object. 56 is not an object. 56 is a literal. 56 is not stored anywhere. It is merely temporary. It is an arrangement of ones and zeros that is not indicative of any object anywhere. And so num_r does not create an object, and num_r must be a reference to an object, and 56 is not an object, so we cannot create a reference to 56. Because imagine we tried to use num_r later equals 40. Well, we cannot assign 40 to 56. 56 is not an object that's assignable. So you cannot use a reference to something that you cannot assign anything to, or that has no space or takes up no space. That's not a literal object. At its best, it's a way to directly interact with an object without like copying it over or creating it multiple times. So, for example, if we have a string and it is equal to, well, let's call this string word, and it's equal to Geobor, the classic Geobor word. And we say down here that for char c in word. Now I'm kind of realizing I never really explained this context. Right here, all we're doing is we're defining a variable, and right here we're giving an iterable. So an iterable object is an object that has that you can use the subscript operator for. So word would be iterable because you can use that subscript operator for it. Now, so and you need this colon right here as some type of to split up these statements, and that's not a semicolon, that's a colon. This is a little bit newer of a loop. It was introduced not back in the day in like not back in the 90s. It was introduced in 2011, this for loop. That's why the syntax is a little bit different. If we create this though, what is happening in this loop is it's actually copying every single index to C. So every single time it iterates through, it's saying C equals word 0, right? That means that if we were to imagine, right, say C equals 20, or no, C equals, because this is a char, G, or well, word 0 is a G, so let's just say H. It would not change because we're not changing word 0 right here. We're changing C. C just so happens to equal word 0. It copied word 0 into C. When we change C, we're not changing word 0. We're only changing C. Now, imagine that C is a reference to word 0. Imagine we specify a char reference to word 0. That means that this would not be it would not be copying word 0 to C. It would be saying C is a reference to word 0 every single time. And so what that means is that if we were to assign to C, right, assign H to C, well, C is another reference to word 0, meaning that when we assign H to C, it also assigns H to word 0. So you can see that in action when we say C equals H, and let's put H in single quotes, and that's not going to do anything because I didn't see out. Now it's all H's, because since this is a reference, we are directly accessing every single index of here instead of copying the value of that index to C. C is a direct reference to that object at that index. And that's a very useful thing that you can do with references. Another thing that you can do with references is you can say int num equals 1, and we can have num r2, and you're going to see what that is a little bit later. Int num equals num, and this is actually going to be num r, and this is going to be just num like that. Now let's take this and let's say num r2 equals num r. So does that work? Well, let's see how that works. We get a 1 out. This does not work though, because what's going on here is when we say that int num equals 1, we're not saying, or we're saying that there's an object num that has a value of 1. When we're saying int reference num r equals num, we're saying that num r is a reference to num. And so when we say num2, the reference num2 equals num r, num2 is not a reference to a reference. In fact, num2 is a reference to num. Num2 is the exact same thing as num r, because when we put num r over here, num r returns num. And so num2, this is the exact same thing as saying num2 equals num, because when we put num r here, num r is already a reference to num, and so it returns num right here. That's why we cannot put perhaps, because this syntax would indicate that this is an int reference num2, right? And that's exactly what it is, because we're referencing an integer num. We cannot do an int reference because you cannot have a reference to a reference. A reference is not an object. Now, actually, let's press Control Z, get back num r, and let's see out num r. And let's see some different operations that we can do with num r. So numR equals 1. What if we put that ampersand sign right here? Let's see what happens. We get a memory address. Interesting. Now, what if we put this multiplication operator right here? This does not work. So what is going on is that when you use this ampersand operator on the right side of an equals equation, or just when you use it anywhere else besides the left side of an equals equation. Right here, we're using it in the left side of an equals equation, or of an assignment expression, to indicate that we're creating an integer reference. But imagine we use that on any other side. Imagine we said, what happens if we use it on this side of that equation? Well, what happens is that this turns into the reference operator. And so the reference operator, what it does is it returns the memory address of whatever is on the right side of it. So this would return the memory address of num. And the memory address in this case, we don't know it. We would have to do this, and we can figure out what is the memory address of num. Well, 012FFBD4. Let's run that again. 00EFF934. And so the memory address changes every single time. Whenever we run the program, our computer decides what address in our RAM to put that object at. And so when we create a reference, or when we create a reference is almost just an alias to that memory address. When we use it on this side, we're kind of saying that numR is whatever is at the memory address of num. So we're just kind of saying that numR, we're saying that numR is whatever is at the memory address of num. And so in that case, numR would have the exact same memory address as num. And so numR and num would both be the exact same object. Hence why we cannot assign a reference to a reference, because a reference is not a physical object. It does not exist anywhere. It is actually, in fact, the exact same thing as the original num, because they both point to the exact same address in memory, and an object is inherently its address in memory. So right here, though, when we use this reference operator on the right side of an equation, what it does is, instead of saying that this is an object, this is whatever object is at this memory address, this is saying return the memory address that this object is at. And so numR, since it's num, we're seeing that num is at this memory address. And that can be useful in a whole bunch of different circumstances when you just want to keep track of a specific memory address. And that's why we can see another reason why that for loop previously worked. I don't know if I can Control Z my way back to that for loop, but we'll see. Look at that slowly typing out. Right here. Let's Control Y actually our way back, or Control Z. Well, that's not going to work. Cout word if we look back at this right here, now we can take a look and see that C is not only a reference to the object at word. C actually is whatever is at the memory address of that object that it is being assigned to. And so whatever is at that memory address, we're saying right here, whatever is at the memory address of C is being assigned H. And so we're saying we're saying that whatever is at the memory address of C is being assigned H. And two objects, if they have the same memory address, they're the exact same piece of data. And so word 1 in this case, or word 0 or word 1 or word 2 would have the same memory address as C, because C is being assigned to whatever object is at the memory address of word 0 or word 1 or word 2. And then that memory address is being assigned H when we assign H to C. And that's how we get these 5 H's right here. Next, we're going to go through something called a pointer. Well, actually, before a pointer, I just want to explain some general naming procedures for variables and stuff. So, if you're making a variable, generally you want it to be lowercase. If you're gonna have like multiple variables, like if this variable is gonna have multiple words in it, like imagine you have a lines vector variable, and this would be a variable to whatever. The issue with this naming that I did just here is it's hard to type. Imagine I tried to type lines vector right here. I would have to rely on the auto finish right here, the autocomplete, to capitalize that L if I missed the capitalization in the beginning, or I would have to put capitalization like that, and then there we go. It's a hassle. So generally you want your variables to be lowercase. When you have structs, a lot of the time right here, a lot of the time you either want the second word in your variable to have an uppercase, or you want to have like a underscore to it, so it's easier to see that this is not a line vector. This is a lines vector. And generally what I like to do is I do a mix of both, but a lot of the time I would put something like that with a lowercase l in the beginning to make it easier to type, then a capital V later, just to separate the words. A lot of the time, if you're having like an object that you created yourself, a lot of the time when somebody creates like a struct book, what they'll do is they'll say this is not a book struct, this is a book struct with a capital B, because they're signifying the importance of this variable, because it is the name of a data type. Or a lot of the time, some people like to put for their functions uppercase, and some people like to put lowercase for their functions. And it mostly depends on what type of function it is. I would recommend lowercase for your functions, though. It's easier. And put short function names. Like if you're gonna have, don't have a function name called like function that returns error when called function. No, nobody wants to read that. Just call it error or something. You want to make your names both descriptive and short and easy to type. a lot of the time, one last tip I have on variable names is a lot of the time you'll see a variable prefaced with like, you'll see a variable like somebody will type they have a float f line value. And what a lot of people like to do is they like to preface the name of the variable with kind of the data type that they're using. So in this case, they're using a float, so they would preface their variable name with an f to signify that that variable is a float, and that's just to make identifying it easier. You'll see that sometimes. Some people when people use classes or structs, they could preface it with an S or a C. And a class is like a struct, but it's a data type that we define on our own. We'll talk about that later. But when people have a data type or a variable that would be of a class type, a lot of the time they would preface it with a C. The next thing we need to talk about are constants. So I don't even know what I did just there. Let's delete this. And let's define a variable. Let's say const int num equals 20. And let's say cout num. Okay, let's run this program. And we get 20 out. Okay, interesting. Now, let's say num equals 30. All right, and we get an error. So what a const is it's a object that is a modifier, a type modifier that makes it so the object after it cannot be modified. And so what we can say is that int num 20 is a const, and so no longer can num be modified at all. We can, for example, say int num1 equals num, and I'm not printing out num1. Let's print out num1. Let's do that. We still get 20. So we can assign a const. We can copy the contents of a const to a non-const. Num1 is a non-const. Num is a const. But we cannot change the contents of a const. And generally, you would use a const for data that you know is not going to be changed in any way within your program. And another thing we can use a const for is we can say const, or we can say, what if we create an int reference to, let's say num_r equals num, and then let's print out num_r. Well, it obviously is already going to give us an error. What is going on? Well, we're saying that this is a reference to a type int, but we're not referencing a type int. We're referencing a type const int. So we gotta say it's a const int reference. And now this works. That means num_r can no longer be used to assign to num. And remember, when we said that references cannot be assigned to literals like 50, because we would be able to later go on here, say num_r equals 40, Well, if this is a const int reference, we can assign it to a literal. And the reason for that is because no longer can we change the value of this literal. The reason we could not assign it to a literal before, previously, was because we would be assigning numR to the memory address of wherever this literal is, or to the contents of the memory address of wherever this literal is stored. And that literal is stored at some temporary memory address that could be marked empty and used by other data at any time, and that could cause undefined behavior, especially if we try to write something new to that space in memory. Now, though, we can say it's a const, and no longer are we allowed to write anything to the memory address that 50 occupies. Now, that memory, we can write a const reference to it, and the 50 will be stored forever there as a temporary variable with no name, only a name of numR as its reference, and it will not be allowed to be changed because numR would be a const. So let's see what I'm talking about. If we press F5, we see that we're getting 50. What's happening here is 50 is a literal integer. So it's created at some random memory address somewhere, and numR tries to, we try to have numR be a reference to the contents of that memory address. The issue is that you cannot have any references to memory addresses that do not include an object, except this is a constant reference. So this reference would not be able to do anything to change that memory address, and so the compiler deems it worthy to occupy that memory address. And so a temporary object is created at that memory address with the value 50, and we have reference numR to that temporary object in that memory address with the value 50. And since numR is a const int, that means that we cannot write anything to numR. numR is merely just merely used as a static value. Now, this is very useful for some things. For example, if we have an int add function, let's say, and it takes int a and int b I was saying previously that it is a mistake to put something like a plus b here, and I realized it was kind of dumb of me saying stuff that I wasn't entirely sure of, and so I researched it. It is fine putting a plus b here. I now recognize what I exactly was talking about, and once we get to a scenario like that, I'll explain to you what I was talking about, where I said we're not allowed to return literals to here, but returning a plus b is fine. Now, as I said a while ago in this video, adding or calling a function right here, add. Let's do that right here. Let's call this add function, and let's say 12. Now, what happens when we call that function? If we remember correctly, this initializes a variable a and copies the value 12 to it. Then it initializes a variable b and copies 12 to it. And then it returns a plus b. Now, this is an error. Oh yeah, because we need to define this up here. This works all nice, but what happens, say, for example, if we want to add 1 to just a number. We want to take in a number. Let's call it num equals 1. And we want to add 1 to num. Well, what we can do is we can go down here and this is what we get. Now, you're going to see there's an error here, and if we run this, there was that did not work. The reason for that is, let's also do this. This still does not work. The reason for that is this function does not return anything. So we cannot write anything into the outstream right here because this add 1 function does not evaluate to anything. Imagine though, we just call this add 1 function right here independently of anything else, and then we just say print num. Well, this add 1 function, normally you would not expect any function to be able to modify the parameter that you put in. This function should return a parameter. But what we are going to do is we are going to input this as a reference. And so when a is put in as a reference, that means that we are not initializing a variable called a and then copying the value of num to it. Now we are initializing a reference a that has the value of the memory address of num, because num is passed into this as its first parameter. Let's press F5. Let's see what happens. There was build errors. Let's see what happens. Add 1 function does not take 1 arguments. Oh, I see what's going on. Up here, we need to make sure to do that, and then we can add num. So, as I was saying before, this is, come on, what? Cannot overload function distinguished by return type alone. That's because it's not a void. Oh, I forgot to mention overloading functions. We definitely need to cover that. Actually, we can cover overload functions in this tutorial right now as we're going. But as I was saying previously, normally when you call a function, it copies the value, it initializes the variable a, copies the value of num to a, and then does whatever and returns a value. This time, since we're passing in a reference, this is creating a reference a to the memory address of num. So a is whatever object is at the memory address of num, and then we add 1 to a. So a effectively is num. If we press F5, we get 2, because right here, even though this function does not return anything, and normally a function cannot affect its parameters, but we're passing in those parameters as a reference right here. So we can directly access those parameters and change them, and then print them out right here. What's cool is that's a good way. That's just like that for loop that we used, where we put a reference into that for loop to directly access the objects inside that for loop, or the objects that for loop was iterating over. Imagine we want more of a traditional function, right? We want this add1 to return an int, and we want this int, so return a plus 1, and we want to call this add1 function right here, right? And we want to do something like that. Well, this works, of course. Adds 1 to a, right? But it's copying over num. It's initializing a and then copying the value of num into a. That's not super efficient. We could do that more efficiently. And the way to do that more efficiently is we can copy over num as a const. So in this context, we're going to be saying const int reference right here, and we're going to be doing 1 plus a. Now let's redefine this up here, and let's run this, and we get a 2. Now, what is going on down here? Well, first and foremost, we do not actually need this const right here. I'll tell you why we had that const. Let's remove that const from here as well. That's probably a good idea. And we get that 2. Oh, once again. So if we imagine, let's remove this const for now, just so we can see what it's doing without a const first. And then we can see what it is doing with a const. Well, down here, when we call add num or add1 num, we are, since this is a reference, we are creating a reference a to num, and then we are adding 1 to the reference a. So what that means is that we're saying return a, or return 1 plus a. The reason that we do not return, or actually we can return a plus 1 here as well. This will work, except if we put a const here, it will not work. Oh no, it actually will work. I was just being dumb. What actually will not work is if we say a equals. We can do a plus 1, because a plus 1 does not change a. It uses a in an equation and then returns a new value. So let's see what this does without a const initially, though. Right here, we are creating the reference a, and we're saying return a plus 1. This way, this is a traditional function, but it negates the slowdown of having to copy or to initialize variable a and then copy over the contents from num to a. It removes that that slowdown, and so what we can do is this function can be more readily used without having to worry about potential slowdown from using this function constantly, from using this function over and over and over again. Something you'll notice about this, though, is what if we put in 30, right? And we get rid of this. Well, now we have an error. And this error is because it's giving us random things here. Well, what's actually going on is it cannot assign a reference to a literal value int. So this int is a literal, and so it cannot create a reference to it. Remember, though, the reason it can't create a reference to it is because if you created a reference to it, you would be able to write to that memory address. Now, what if we made it so we cannot write to that memory address, saying const? Now we can create a reference to that int. This means we can put both numbers. So we put in 30 and got 31, and we can put in variables or objects into here, and it does the same thing. This num equals 1, and we got 2. So this negate, if we put a const here, and it's a const to a reference, it negates having to copy over the contents and initialize a variable. And the const also allows us to use objects that besides an actual variable, we can use literals like an actual 30 instead of just a num that contains a 30. So that's what that const does. The issue with using const, though, here is no longer can we change what a equals. We can't say that, plus plus a, because that would be incrementing a. We can't do that. We can't increment a const. Most of the time, though, if you know you're not going to be changing the values of any of the parameters, and there's a good chance that you're not doing that if you're using a function, then a lot of the time it's a good idea to put the parameters of your functions in as a const int or a const data type to a reference, or a const data type reference. So you could have this data type as anything. Even if we had that book struct, we could have a book data type. Now, what about, I said I was going to go over overloading functions. Overloading functions is quite a nice topic. Let's have two functions. Add one. One of them is going to take a const int. One of them is going to take a const double. Right? They're named the same thing, remember. And this one is going to be a plus 1.0. Right? And then we're going to define this at the top right here. We're going to declare it. But these are named the same thing. These are both add one. Right? What happens? Well, let's see. I run this and it runs fine. How does it know which add one to choose? Well, this is what's called function overloading. When you have two functions of the same name, the compiler will automatically choose which function to be used based on the data type that's being passed in there. So right now we're passing in a num. Imagine we pass in a double, though, so 20.49. And let's run this. Actually, that is not exactly correct. That's not what should have happened. I see. I was just being dumb. So right here in the double function, we were supposed to specify the return type as a double, but I didn't create it manually. I just copied over the int function, and so I forgot to specify that the return type was a double right here. Now that the return type is a double, though, this is going to be a double add one. This is going to be a double add one, and it takes a data type of double. now you see 21.49. That's because the compiler automatically looks at what we input for add1. Well, it sees that we input a double. Now it sees that there's two functions called add1. Well, which one best matches the parameters that we input? We input a parameter of a double. And so if we look at these two functions, one of these functions accepts a const int reference, or a reference to a constant int. And then this one accepts a double. So it's going to use the double add1 function. And so the double add1 function, what it does is it takes a and then adds 1.0 to it. The regular add1 function takes a and returns 1 to it, or adds 1 to it. And the double one returns a double. The int one returns an int. That should be mostly it with references. So next we're going to do pointers. Pointers are like references, just more complicated. So we're going to start with int num like we always do. And let's actually see out num for now. So right here, we're going to have an int pointer called p num for pointer num. And this is going to equal the reference num. And let's see out p num and let's see what happens. Interesting, right? Well, what happens if we change this to 10? Does the same thing. Well, if we put a dereference operator right here, we get a 10. Interesting. So if we explain step by step what is going on here, this num variable, this num object holds a 10. We're saying right here we want to create an int pointer. And since this is on the left side, we know we want to create an int pointer. A pointer is an object that holds a memory address, right? And if we remember, using this ampersand symbol on any other context besides on the left side of an assignment statement, using it in any other context returns the memory address to the object. So this ampersand symbol is giving us the memory address of num. And we're assigning that memory address to p num. P num is a pointer. Pointers hold memory addresses, and so we can hold the memory address of num inside of p num. And so what we can do is later we can say p num, we can print out p num right here, and when we didn't have this operator, it gave us the memory address because p num is holding the memory address of num. And now, just like when we use this this star operator is the multiplication operator, but it's also the dereference operator and the pointer specifier, type specifier. This operator right here, if it's used in any other context besides specifying that it's that we're making a pointer, used in any other context, like right here, for example, it is called the dereference operator. And what that does is it is the opposite of the reference operator. The reference operator, remember, it returns the memory address of the object. The dereference operator returns the object that is held at a memory address. And so p num holds the memory address of num. And if we dereference that memory address that's held in p num, then we get num. And so when we dereference p num, we get 10 because p num holds the memory address of num, and we're dereferencing p num to get num. which is quite useful. Now, what we can do is get some undefined behavior. Like this would crash our program. Not necessarily, but this is undefined. And we get an 11. Interesting. Why is that? Well, what pnum does is pnum, when you add 1 to it, it moves on to the next section of memory that it thinks may hold an object. And in this case, it moves to the section of memory right after num. Num equals 10, and oh, wait. No. It gave us an 11 because I was adding 1 to num because I was using the dereference version of this. I meant to be using the reference version of this. You can see though that the dereference operator, since it returns the actual object, we can add to that object. We can add 1 to num because dereference pnum returns num. But if I do not dereference it and I add 1 to it, what this does is it moves on to the next memory address, the memory address right after wherever num is stored at. So let's press F5. And we get that. Imagine we take parentheses. Remember, parentheses lets us specify in what order operations are done, right? So we're going to take pnum, the memory address of pnum. We're going to move to the next memory address by adding 1, and then we're going to dereference whatever is at that memory address. Fine, I don't know what's going to be at that memory address, but we're going to dereference it. And we get a 0. That's because this is undefined behavior. There could be anything at that memory address. It could be another program is using that memory address. We're not sure. That's why it's similar to if you were to take the index of a word that or an array that does not exist. So if an array has 6 objects in it and you tried to take index 6, which is 1 more than 5, if an array has an array starts at 0, remember. So if it has 6 objects, it goes up to index 5. So if you tried to take index 6 and index 6 doesn't exist, what is actually happening is you are trying to take a pointer to index 6, and then you are dereferencing that pointer and looking at what's inside that index. And that is undefined behavior because anything could be inside that index. We don't know what's inside that index. If it's an index that is not defined inside of that array. And so I just said now, though, that that arrays, when you index them, they return a pointer, and that actually is true. That's one of the main uses for pointers. Pointers are actually how, when you subscript an array or a string or anything like that, the pointer is how it actually accesses that piece of data inside that array. And so let's take a look at an example of that. Imagine we have, let's use an array for this, just because we haven't used many arrays. Let's say int array equals, actually it looks like array might be a keyword. So we're going to say nums, and remember you have to put this for this array, and let's put a 0. Actually no, because we don't want the array to be a 0 length. Let's put 5 because we want it to have 5 objects in this array. Let's put 1, 2, 3, 4, 5. And now let's see out just nums. What happens? Make sure we put a semicolon right here, and let's press F5. Well, we get a memory address. Why is that? Well, when you reference an array, when you try to print out an array object, what actually happens is this array, this nums, is actually a pointer to the first object in nums. So if we dereference this, we get 1 because the first object in the nums array is 1. Now, remember, if we add 1 to a pointer, it goes to the next spot in memory that holds an object, or that's not exactly correct. It goes to the end, it goes to the next set of memory right after the object that it was currently at. So if we say nums plus 1, it's going to find the memory address of 1, and then it's going to go to the memory address right after wherever 1 is stored. And then we're going to dereference that. So let's see what happens. Well, we get a 2. If we plus 2 to this, it's going to go 2 memory addresses ahead. And we get a 3. And the reason for this is because how arrays work is that this 1 is stored at some memory address, and this nums object right here is a pointer to that memory address of the first object, and that's all it knows. It knows the size of the array, and it knows where the first object pointer is. So when we are actually referencing, or when we're gathering objects in an array, usually those objects are brought to us by pointers to each of those objects. And objects in an array are always ordered one after another. So if 1 is in a certain spot in memory, the next spot in memory, the next memory address will be the next object in that array, 2. And then the next memory address will be 3. And then the next memory address will be 4. So knowing that, we can use pointers to access every single object in an array. And we can do the same thing with a string. So how can we do that? Well, we can say for int pointer, let's do p. For int pointer p equals nums, p does not equal p plus 6, I think we want. And then let's say plus plus p. And for this for loop, let's say cout dereferenced p. And let's also let's run this. Pretty sure this should be good, and an exception was thrown. I think that's because we want a 5 right here. Stop. That is an example of why we do not want to access an index that's out of range. Evidently that was out of range. And that was also out of range. Oh, yeah. We want +4, not +5. Let's kill this program. Let's see. Well, that program's dead. Let's press continue. Perfect examples of why we don't want... Oh, another exception was thrown. For real? Why are you learning C++ from me? Okay, maybe we gotta do something like this. Now does this work? Still does not work. This might work. Oh, yep, that does work. So I actually don't know why exactly that wasn't working, but this std end function, it just returns. You put in any array or any iterable object, any container type, and it returns a pointer that is one past the end of that object. And so what we're saying here is we define an integer or an int p or an integer pointer p, and we say it equals nums. Remember, nums returns, when we say p equals nums, it returns a pointer to the first element in nums. And so this is a pointer to here. Right here, what we do is we say, this is the condition. As long as p does not equal std end nums, std end nums returns the index of right here, undefined. It returns an index one past the end of your your array, which is nice. And so we can imagine it's going to keep going until we're going to see it's going to keep going until we find that p does equal that index one past the array nums. And so it's not going to go in that case. And right here, we're iterating p. We're just saying p++. Remember, when you add 1 to a pointer, it goes to the next memory address. So over here, we're just printing out p dereferenced. Remember, p is a pointer. It's a memory address to every single object in this array. So when we print out p dereferenced, it gives us the object that's within that memory address. In this case, that is a 1, 2, 3, 4, or 5. I actually want to test once again, like p plus 3. Will that work? Because I actually don't know why this wasn't working. Yeah, for some reason, this is giving us some type of exception where it's trying to access some type of index that does not exist. And this, I imagine, will still not work. Yeah, this throws an exception as well. Even if we put parentheses, I imagine this will throw an exception. Ooh, I know why it throws an exception. Because this function is evaluated every single time. So what happens is that since this condition is checked every single time, p plus 1 is always changing. Even once we get to the end of the array, p plus 1 is going to be continuously changing. So even if we put p plus 4 here, right, we would think that p plus 4, right, if p is this, then plus 4 would be 1, 2, 3, 4. It would be this object right here. We really want it to be p plus 5 because usually when you're iterating through arrays, your final iteration is going to be one past the last object in your array. So you can say p does not equal that object. That's one past. So as long as p is not one past that object, then you can you're fine. You can do whatever is in the for loop. The issue here is that p plus 5 is constantly changing. Initially, p plus 5 might be one past the end of this array, but what happens is that when we iterate p right here, p plus 5 also gets iterated. So p is always 5 ahead, or p plus 5 is always 5 ahead of this p right here. And so this for loop never breaks, and it keeps reading memory that is undefined, and it crashes our program. That's why you can't have, you can't read indexes or memory that does not have objects in it. You don't want to do that. This is a very, very common mistake. And so you can just use different operations like, or different functions like std end right here. And this end function returns the end of nums. And so this std end nums, this never changes because the end of nums is always going to be the same thing, unless we add stuff to nums. But that's impossible because nums is a fixed size array. And see, we print 1, 2, 3, 4, 5. Now, there is a difference when we use pointers to arrays versus pointers to strings. So imagine this is not an array. This is a string, and it's going to be our classic string Geobor. And this is going to be called word. And let's say word right here. And let's say string. Will this work? Well, no. Because word, despite the fact that word is actually effectively an array of, G, E, and you get the idea. Despite the fact that it's an array, it is a library class. It is a data type that's defined by the standard library up here in this string file. And they defined it so that when you call word like this, it does not actually return a pointer to the first object. Word actually just returns this whole word right here. And so we can't have that. What we can do, though, is we can say auto p equals word dot begin, and put in parentheses like that. And we can say end. And let's run this. We're going to say we get Geobor. Now, we use this auto keyword, and that's because p is, you would imagine, right? Because this is an array of chars, so you would think that you could put char pointer, right? Let's try that. What happens? That is incorrect. It's giving us an error. Well, no, it's because word.begin, this is a library type, so it does not return a pointer to an object. It returns what is called an iterator. And an iterator is almost effectively a pointer, except it is specific for different types. Like this library type, this word defines its own iterator. And an iterator is, as I said, almost exactly a pointer. It really is a pointer. But we use auto. And when we do this, we can hover over auto. It'll say using std string iterator. And so iterator is iterator is what is returned by this word.begin function. This word.begin function returns an object called an iterator, and that iterator is specific to this word class, this word, or this string data type right here. And this P is assigned to that word.begin. And this auto keyword tells the compiler, do whatever you want. Figure out what that means. Figure out what word.begin returns. And so automatically assign P to whatever that is. We could also do string iterator P equals words.begin. And remember, we can use string right here because we put using std string up here. So we don't have to put this std in the beginning of string. But string almost acts like a namespace. String is what's called a class. And we'll learn about those later. But string includes something called an iterator. And that is that is what's returned by word.begin. And it's kind of a hassle to figure out exactly what the iterator is called for every single data type or every single class. So we can use auto. It'll automatically figure out. And this works for anything. If we used, we can use auto word equals Geobor. And the issue with auto right here is I don't think it actually returns this std string data type. It returns something called a C style string, which is literally a string that is actually just an array of G, E, that auto probably assigns word to be exactly that. We don't want word to be that, so we're going to use string, because the library type of string is much more efficient and much easier to use than any C style string that we could use. This works, and what we can do is remember we have this word.end. This means that this .end function is specific to a string data type, right? Because word is a string, and that dot is specific to the string data type. What we can do, imagine we don't have this dot begin, because previously for that array we didn't use any dot. We just used begin. So this is just an external function, and we passed in word. So if we run this, it did not do anything. Why is that? Well, because begin word, this is looking for a pointer to the first object in an array. The string class from this string file right here is not exactly just an array of characters. It's defined slightly different, and so these begin functions won't find the first pointer to it because they can't find any pointer to it at all. That's why we have to use the dot begin, because the string words, the string class is defined a little bit differently to just an array itself. You can see, though, we're using the exact same operations on every single iterator, or on every single iterator as we were using on all the pointers. So if we change this to it for iterator, a lot of people use it for iterator, and so that's what I'm going to use right here. You can see this iterator, you can use the exact same operations, the exact same things on it as you could for a regular pointer. If we press F5, this still works. We can add to it, and this iterator goes up a memory address. We can dereference it, and it returns the object at the memory address. We can do whatever we want with it. And this iterator is defined automatically using this auto keyword. This auto keyword, you could also just use it for like num equals 12. And it will automatically decide that num is an int. If we put L here, it'll decide that num is a long, because this 12L, if you remember, putting an F or an L or something like that after a number will change it into that type. If we change it to an LL, this is a long. So this auto assigns to num whatever the data on the right hand side of the assignment operator is. Now, something about pointers is that a pointer right here, if, for example, we had a string pointer, and it's called p, and it equals the reference of word. The thing with a pointer is that this pointer, this p object, this is an actual object. It is, unlike a reference, this has its own memory address. So imagine we have a or imagine we have we want to create a pointer to this pointer. We would type in string and 2 of these, and then p. Well, let's call it pp. Haha, funny. Well, because it's a pointer to a pointer, so obviously we gotta do pp. And let's have it equal a reference to p. In this situation, what happens is that since p is an actual object, p has its own memory address. P is an object of a pointer type that stores a memory address, but it also holds its own memory address. In this case, we press F5, it's giving us no errors. This works. The reason that we need 2 of these is because what this signifies is that pp is a pointer to a string. Now, if we std, or we don't need std, if we cout pp, haha, funny, end line, and we do that. Now, let's see what happens. We get a memory address. Now, what happens if we dereference this, right? So we should get the actual p object now, right? But it's still a memory address. That's because when we dereference p, it just dereferences it again, or it still is a memory address. So we have to dereference the dereference, and we finally get a Geobor. Now we can think about this as is this dereference operator. It dereferences whatever is on the right side of it. And so what is on the right side of it? Well, it's pp dereferenced. So this will dereference pp and return whatever is the result of it, which is p. And then it will dereference p and give us Geobor. Now the thing is, if we want to create, for example, let's cout word and line, and let's say the p dereferenced equals gamer, right? That string gamer. Let's Run it. Now we're getting gamer because that dereference equals gamer. Yeah, it all makes sense. All seems nice. Now, what if we said const? Well, this does not let us assign to it anymore. Okay, interesting. Word equals Geobor, right? And if we take P dereferenced should also equal Geobor, right? And is that correct? That is correct. Now, what if we said, what if we have, let's assume we have another string, right? This is going to be word 1, and this is going to be 2. Bruh. Now imagine if we have a string pointer to, this is going to call, I'm just going to call it P1, and it's going to be a pointer to a reference to word 1. If you didn't catch it, the reason that we have to use a reference when we're assigning something to a pointer is because a pointer holds a memory address, and this reference operator returns a memory address of whatever is on the right-hand side of it. Let's say that, though. And so now we have P1, which is a pointer to word 1. What if we say P equals P1? Does that work? Well, yeah, that does work. Well, how does that work? The way that this works is that this constant string, this is not saying that this is a constant pointer. This is saying that it's a pointer to a constant string. It is not really a constant string, but it can't determine whether your string is constant or not. And so when you say this is a pointer to a constant string, it's not going to allow you to write to that string anymore because it's assuming that that string is constant, even if it's not constant. Let's see. Got a few more things that I want to check out, but let me look up exactly that syntax. So the other thing that I was looking at is, instead of this being a pointer to a constant string, imagine this is a constant pointer. So how do you do that? Well, you do it like this. And now this no longer works because it's no longer the string that is constant. It is the pointer itself. And remember, a pointer is an object. So any object can be constant. And this object just so happens to be a pointer that is constant. And you cannot no longer change the value of the pointer. Now, what happens? Imagine we try to assign something to P, though, because the string inside of it is not constant. Let's see if that can happen. So dereferenced P equals dereferenced P1, let's say, because that should return bruh. Right, if that's correct. Let's see if that works. And that is correct. This string right here is not constant. It is only the pointer that is constant. So the actual pointer object, you cannot change the value of it because it is a constant. And right here would signify that the actual string that the pointer is pointing to is a constant. You can pass in pointers through functions. Imagine we just have a function right here, int. Well, actually, let's make a void function. Void add 1. Actually, we don't need that. And since this is a function, let me improve the syntax like that. And we're going to say this is an int a, and it's going to be a pointer to a. Let's declare that up here so that this function can see that, and let's int num equals equals 1, for example. Now, since that's a void function, it does not return anything, so we're just gonna pass in num directly. This is gonna print out num. We're gonna say add 1, and we're gonna say a reference to num. And that was not successful. Expected a line 12. Right here. I forgot a semicolon. Let's run this again now. Now we get 2. Remember when I was talking about how when you call a function, it creates this variable? This variable right here, a, still has to be initialized. Despite the fact that it's a pointer, remember a pointer is an object. So this is a pointer to an int a. And a, when you call this function, still has to be created. So if you create a function with a pointer as its parameter, this function requires for you to either pass in a pointer or a reference to a pointer, or a reference, because imagine we have a pointer to num1, right? So let's say int pointer p equals the reference of num1, and let's pass in p right here, and then let's check what happens. So it's not num1, it's just num. There we go, we still get a 2. And the reason for that is because this int this int pointer p equals dereference num. When this int pointer right here is asking for a memory address, and you can either pass in a memory address through passing in a pointer object, because a pointer object holds a memory address, or you can pass in a memory address through passing in a reference. And what we did last time was we just passed in a reference to num, which gives us a memory address back, and that works. This does not benefit from this is not a reference right here. This has to still create this a, so this doesn't benefit from the speedups due to references in functions. Something else I should mention is imagine we have a string right here, and this string equals Geobor. Let's put that in double quotes. And this string is called word, right? And we have a function down here. What this function does is this returns a string, and it takes in a string parameter a, and it returns, or it says a plus equals Geobor, and it says return a. Now let's define this function up here, or declare this function up here, so that the compiler doesn't yell at us. And we're gonna cout, and the function is still called add1, but whatever. So theoretically, this should add a Geobor with Geobor attached to it, and it does not. Why is that? What happened? We're getting a memory address. Return a plus equals Oh, I forgot. That's because we were returning a pointer to a function. You don't generally want to do that. So we're going to say add 1, and we're going to pass in word. Now we get Geobor. What is happening here? Well, we're passing in word into the add1 function. Still, I don't know why it's called add1. And obviously this takes a string parameter, a. It says a plus equals Geobor, and it returns a. Well, that's nice. That's completely fine. What if we said return a plus Geobor? I was saying that returning literal values or expressions like this was invalid. And what I meant was, I did a little bit of research to see exactly what I was talking about. And what I meant that doing this with a string literal is invalid. You can do it with pretty much everything else, except for things that are arrays, things that are types like this, where you got a G, E, O, B, O, R, you can imagine. Or if it's an array like 1, 2, 3, 4, 5, 6, etc. And the reason for that, you cannot return arrays like that. And the reason for that is, if you remember, if we tried to access an array in those for loops previously, when we could specify, or when we tried to pass in the array, it gave us the pointer to the first object in the array, and that's what's going to happen here. When we press return, we are actually getting a pointer to the first object in array. So let's press F5, and that's not necessarily what we're getting. We're getting the full string literal, but the string literal is stored through the pointer to the first character in the array. And this array, when it's created as a string literal, is stored in the memory that this function allocates. So when this function is called, it allocates some memory, and this string literal and expression result is created in that memory. And when we're returned this function, it doesn't copy over that array to right over here. No, instead, what it does is might be better, more easily visualized if I do something like this. Nope. Instead, what it does is it points us towards that array by giving us a pointer to where that array is stationed in this memory. This memory, though, if you recall, after a function ends, is destroyed. So this array does not get copied over. It's still in that memory after the memory is destroyed. It's marked as free. And so it's not necessarily overwritten with zeros or anything like that. It's just marked as free. So anything can access this array. And this string literal is stored. That would mean that this string literal is stored in some type of free memory, some type of memory that has already been deallocated by the program. And that's not an issue with something like number. You can return a 1 because it will copy over the contents of the 1 into Word, because 1 is not an array, so there's no pointers to deal with when you're returning 1. And another thing is, you can return a the reason why we might have not been getting like bad results, the reason why we were not getting issues was that even when we did this, I specified the return type as string right here. The old C style strings would probably be would give us an issue. So if this returns an array to char, then that would probably be an issue. Let's see if I can get that to work. And no, I don't know if I am going to be able to get that to work. And the reason for that is because, as I said, arrays would normally be deallocated, and we would be returning a pointer to it. The reason this does work, though, is because this should, theoretically at the very least, automatically be converted into the std string object, which is not going to be giving us a pointer to the first character in the string. And so this, as far as I know, may actually be valid. But when working with arrays and C-style strings, then you can't really return them because it's going to try to return the pointer to the first character in the array, and that array is going to be stored in the function's memory, which has already been deallocated and marked as free. So generally, though, I don't think you have to worry about that. So right here, we can define a function right here. And in this function, imagine we wanted to make a pointer to this function. So we could access this function through a pointer instead of just this name. If you put this, we get string pointer add 1. And right here, we would have to do the same thing. And we would have to return a pointer to a string. Generally, there's not much reasons that you want to return a pointer to something when you are making a object. When you are making a function, you don't really want to return references or pointers to things because all the stuff inside of your function usually is destroyed at the end. The only time that you are supplying a pointer to something is, imagine you have a reference to A, and in this case you could return a pointer to A. So you could return a you could just return A like that as a reference, and this will be valid because it will the reference of A can be converted to a pointer. And this is fine because A exists outside of the function somewhere, and we're returning the reference to A once again. So this is fine because A is not destroyed after the function ends because A is already an outside object.
1.2 billion.
That was my notification noise. It's Joe Biden saying 1.2 billion. Man, I love Joe Biden, bro. He is my man, bro. But what was I saying? This is fine because we can return A as a reference here, and if we put something like that, we're going to see that we get a memory address, and that's because word is passed into here, passes in a reference to word, and it returns a pointer with its value being word, a reference to word. And so the reference, this just returns a reference to word as its, or a pointer with a reference to word as its value. That's pretty much what it does. It's not super useful right now. Imagine, right, we wanted to create a pointer to add 1. Well, how exactly do we do that? This doesn't do that. This is the same thing. Well, actually, the syntax for that you would have to put parentheses right here, because you would want to specify that add1, that this is a pointer to add1, and this does not work as a declaration for a function, because you can't declare a function as a pointer to a function. What you would have to do really is you would have to say, well, add1 equals that, right? And this pointer to a function, we're going to put it in global scope for now, because, you know, I don't it doesn't really matter right now. I don't feel like changing it. But, oh, and we can't return a reference to A. But we're going to put it in global scope for now, just to see it easier. Down here, we're going to say, we could do auto add1 equals, or auto p add1, because there's going to be a pointer to add1, equals add1. And this auto is this auto declaration, I'm not sure exactly if it gives us what we want, so we're gonna test that by doing by actually, instead of putting that in here, we're gonna put that down here, and we're gonna see out p add1, or pad1, I guess, and we get a memory address. I'm pretty sure this is what we want. Let's dereference this and let's see what we get. We still get a memory address, and the reason for that might be that this p add1, this should be a reference to a function. And so imagine we do p add1 and we pass in word, right? Let's see what we get. We get Geobor. Well, that's because p add1, when you normally call a function is the it returns a memory address or a reference to where this starts. It returns pretty much a pointer to where the function starts at. Now, when we do p add1, we say that p add1 is a pointer to the function, and so this can be essentially a reference to our function down here. We should also, I think, be able to specify this as a reference. And so if we do this, this is going to do the same thing. Now, instead, p add1, this is no longer a pointer. This is now a reference to the add1 function. So this is no longer a object. We can't change anything about it. It is only a memory address, only an alias for the add1 function. And if we change this, then now it's a pointer, because this auto will evaluate that we want to make it a pointer to the add1 function. Because add1, normally when we call add1 here without any parentheses, it returns a pointer, and so auto will determine that this is a type pointer. Okay, so I have consulted the manual. This is how you are actually supposed to define pointers to functions. And so instead of auto right here, what we do is we say instead of auto right here, we're going to place in a return type of the function, string, and then we're going to put in parentheses the name of our pointer, dereferenced, like that, with the dereference operator to indicate that it's a pointer, and then put in the arguments of our string. And this should string should be valid syntax. So we can say this equals add1, and this is valid syntax. What this is saying is that this is almost like declaring a function. This is saying that, okay, so we have a function, its return type is a string, and then we check what is the function name. Well, actually, the function name is not a function name. It's actually a pointer pad1. And here are its parameters. And this pointer is going to point to add1. And this pointer has to have the same parameters and has to have the same return type as add1. A good use for this is, if you remember, we did something like, well, I'm going to change this to int add1, and we're going to be just returning an int, and let's replace all these things right here real quick. And imagine we have something like double add1, and this takes a parameter that's a double as well, and we initialize this up here. The interesting thing is p add1, we can normally, when we use overload function like add1, this will automatically decide, well, why is it giving us an issue? Oh, is it asking us for, oh, that's because this has to be a const double. Because remember, this is a literal, so that has to have a const right there. So this normally, what this add1 will do, it'll look through every single function called add1. It will decide, okay, so do we want to use the double or the int one? Sometimes we have functions that are very, very similar to each other. Like maybe one of them is a double and one of them is a float, and you have a decimal number that is neither a double nor a float. And it's just deciding, okay, do I want to use the double one or the one that's a float? And maybe it's picking the float one when you want it to be picking the double one. So, for example, right here we could have something where this is a float. And maybe you want it to be picking this float one, but it's always picking this double one. How do we override that? Well, we can create a pointer to this float function right here. So it specifically goes to that function right here, and we create that like that. Pointer, call it p add1, and this is pointing to add1. So this is saying we have a function float, and instead of a name, we have a pointer to a function, and it has these parameters. Well, it's going to find the function add1 right here that has the exact same parameters as it. In this case, there was none, but it's going to find the add one function that has the exact same parameters as it. So it's always going to be using the one with the float instead of the double. So if we check right here, we put p add 1, we're going to see that p add 1, I don't know if you can see that, but it's saying that p add 1 returns a float. So if we press F5 right here, we're going to get 20 as a float, and it just said 20 because 0.0 just it doesn't print anything if you put 0.0. Is there any way I can demonstrate that this is a float though? How can I demonstrate that this is actually this? Because we're telling it that p add 1, it has these parameters, but how can we know that it's actually picking the add 1 function that has the same parameters as it? It should, but I'm trying to think of a way to demonstrate that it does. I think best way to demonstrate that would be, instead of using a float right here, I'm going to use an int. And we're going to do p add 1 takes type int. And actually I want it to be a const int. So normally putting in this 20 is a double. So normally if we were to just use the regular add 1 function, it would use this double function because it wants to return a double, right? How do we prove that it is, while using p add 1, it's using the int function? Well, let's return a plus 1. So we should return 21 here, and we should return 20 if it uses the double or the float version. And it returns 21. The reason for that is if we just have the regular add 1 function right here, it's going to choose the double. Let's see. And we get 20. The double does not add 1 to it, so we just get 20. The way that p add 1 works is p add 1 is specifically said to be a pointer to the int version right here. And this int version, you have to make sure that this has the exact same parameters and exact same return type as the function that you're trying to find. And so this probably most usefully is a way to, pointers to functions is probably most usefully a way to specify exactly which overload function you're trying to use. You can also put auto for p add 1 equals add 1, but I'm not exactly sure which one it will pick in this case. Auto cannot deduce auto type, and that's because add 1 could be any of these three function types. It could be a function that returns int and that takes a constant int. It could be a function that returns double and takes a constant double. It could be a function that returns float and takes a constant float. So this auto keyword cannot deduce which of these add 1 functions it should be using. Specifically determining the parameters like this though will tell the pointer which functions or which specific version of add 1 that the pointer should be pointing to. So now we're going to be getting into creating header files. To create a header file, normally in Visual Studio, you can either do it manually, add new item. You could manually create a file with an extension .h, and this would be a header file. But Visual Studio has its own way of doing it. Going here, pressing add, new item, and clicking header file. And then it will automatically put this preprocessor directive at the top. Now, header files, what they do is instead of using this pragma once, we're going to be using, well, I'm going to be explaining what this is called. If n define, and then we have to put a variable here. We're just going to call it, and it's oftentimes this header is going to be maybe starts with an underscore, header file, and usually it's going to be like the name of the header file that we're using. So define header file. And we're going to put in, back into our tutorial.cpp file, let's put in all our functions into here. Just because, why not? We'll put all these functions into here for now because they're taking up a lot of space in this file. Just get rid of them. And we don't need these declarations anymore. Now, all we have to do is say, at the top right here, include, and we're going to do header.h because our file is called header.h. And you notice here, I'm using double quotes instead of the angled brackets. Angled brackets are only used for files that come standard in the C++ library, not files that we create ourselves. Also, this .h, you can see that those files right here, this IOStream doesn't have a IOStream.h or anything like that. Well, the reason there's a .h is because this is a header file. They just decided for IOStream and string and the normal C++ library files to just not have a file extension for some reason. I'm not exactly sure why. But they don't have a file extension, and when you create a header file, you're going to usually have a .h file extension at the top right here. What this is saying, though, this header file is quite literally when the preprocessor, which is what happens before we compile our program, before this turns all into machine code, the preprocessor will look at this include header.h, then it'll go into here and it'll be like, okay, so right here, copy, all right, paste. That's what the preprocessor will do. Let's Control-Z that because you get the idea. And we have some interesting stuff in here. It says, if n define header underscore file, define header file. And so what this means is this would be mostly used for other types of things. For example, when you run your program, there might be some type of program, there might be some type of preprocessor directive that's like that you have different standards of Unicode, for example. So Unicode, and you have, you know, your first standard of Unicode here, and you have your second standard of Unicode here, and you only want it to compile code based on which standard of Unicode that you're using. So if you're using Unicode standard 2, you only want it to compile whatever code is in this block right here. And if you're using Unicode standard 1, you only want it to compile whatever is in the block right here. So how would you get the preprocessor to do that? Because if you're using Unicode standard 2, or if you're using just, you know, depending on whichever Unicode standard that you're using or something along those lines, you're going to want to tell the compiler which set of code to compile. In this case, this is where the preprocessor comes in handy, right? We're not using Unicode standards here, but right here we're saying if header file is not defined, then define header file as all of this stuff and then end the definition. So that means that that if header file is already defined somewhere, then because imagine we have somewhere previously in the code maybe this is a very long code base, you're going to see that this went gray. That's because header file is already defined. So it's not going to have to define anything is in here. It's not going to have to compile any of this code right here because header file is defined. And if header file is not defined, then it's going to define header file as all this stuff right here. And this could be used as a Unicode standard to and other just codes up here. You're gonna like nd there's stuff like ndebug might specify that the compiler should compile certain things and ignore certain things. In this case, the reason that you have the if and define thing is, imagine you have this header file, and well, let's create another header file. We're going to call this header.h, and let's actually rename this to double.h, and we'll see why. Let's get rid of this pragmalons for now. Imagine this double.h has int Geobor in it, and this int Geobor function returns 0. Identifier R is undefined. Where? Bruh, I'm just returning 0. Why is it getting mad? There we go. Now it's not yelling at me. Okay, so imagine we have this double.h file, and we really need this Geobor function in this header file. This header file really needs Geobor. All right, so we say, okay, include double.h. So now this is going to go to this double.h file, and it's going to copy everything from that double.h file and paste it into this header file. So it's going to go here, copy all this, and that's going to be pasted right here. Okay. And imagine we also needed to include this double.h in our main C++ file over here, right? This double.h is required in both this header file and in our main C++ file. Well, what's going to happen, unfortunately, is it's going to go to this double.h, right? And it's going to copy this, and then it's going to go here, and it's going to be like, okay, include double.h. Okay, paste the code here. Then it's going to be like, okay, include header.h. So it's going to go over to header.h. It's going to go over here, and it's going to copy all this, and it's going to go here, paste the code. Well, now we have to include double.h again, right? Because header.h also included double.h. So let's go here, and let's paste double.h here. So now we have this int Geobor function defined twice. That's because we included double.h once inside this header file, and then once inside of here, and so it copied into our main C++ file once from us including double.h in here, and once from us including the header file, which included double.h. And so we get these two functions that are exactly the same, and you're not allowed to have functions that are exactly the same. Now, the way to fix that, imagine, let's Ctrl Z all this stuff. Imagine double.h has something called if n define we're going to call it double h. we're going to do this hashtag. And we want to put end diff. I was struggling bad there, bro. But what's going to happen now is when we copy this into header.h, so let's do that now. I'm actually going to get rid of all the rest of this code in header.h just to simplify it so we can see exactly what we're trying to do. So imagine there is down here header.h stuff down here. But it's going to take the stuff that's in double.h and it's going to paste it here. Be like, okay. And then we're going to go into tutorial.cpp and we're going to paste in double.h. So, okay, so take double.h right up here and paste it into here. And then go into header.h. Okay, we need to go into header.h. So let's take all this stuff and let's paste it into where header.h is. Now what happens? If we read it from the top, if not defined, double.h, define double.h. So if double.h is not defined already, and if we check up here, it's not defined anywhere up here, so double.h is not defined. So we're going to define double.h as all this stuff. And then the end diff will signify that we're ending the definition of double h. And so this is included once because double.h was not defined. Okay, now let's scroll down. This is the double.h that got included from header.h. It says if not defined, double.h. Well, double.h is defined this time because we already defined it right here. So this is going to fail. It's going to be like, okay, double.h is already defined, so we don't have to do anything up to this define preprocessor directive up here. And then it's just going to copy in the header.h stuff, and then is all our main stuff down here. So what this allows us to do is it allows us to set up multiple variables and check if this variable is defined, then compile all this code. If it's not defined, don't compile this code, and stuff like that. And we can make sure to define variables like that in our header files to make sure that they're not included multiple times in our tutorial.cpp file once all the inclusions get together. Let's press Ctrl-Z, Ctrl-Z. I'm actually going to get rid of header.h because we don't really need it. Let's just remove and delete. And in double.h, okay, Visual Studio is kind of slow. Another way, instead of doing this, define double.h and then check if double.h is defined. If it's not defined, then define it as this. Instead of doing that, there's another thing, which is a newer feature of a lot of compilers. And you can just put pragma once. And this will just, I'm pretty sure pragma once is just for a single file. It will just say only copy the contents of this file once. If you find this file in another include statement somewhere, do not copy it. So that's what pragma once will do. And you need a newer compiler usually to do this. The Visual Studio compiler does support pragma once though, and it's been supported for a while. So you don't have to ever really worry about it. You will see though, you will see this version though to be able to support legacy compilers. So older compilers can also compile this code. And so I can put pragma once here to make sure that this code right here is only included in the tutorial.cpp once. The reason that we don't actually want to include the code multiple times, if you remember, is because it's the same way with if you define the same variable twice, this is gonna give us an error. And actually, let's get rid of all this stuff just to make sure this is not giving us errors. This is giving us an error because we're initializing the word here. We're creating the word variable, and then we're creating the word variable again right here, which we're not allowed to do. And it's the same way with files that are included. Imagine if we somehow managed to include this Geobor function twice because it was included in another file that we included. And we would have two of these Geobor functions, and it would the compiler would start yelling at us. We can check that now. It yells at us, and actually it might be yelling at us because of that. Let's get rid of it to make sure it's not. And it's yelling at us still, and it's telling us function int Geobor already has a body. You're gonna see down here it says int Geobor void. The reason it has void right here is because in older versions of C++ and the language that predates C++ called C, if you had no arguments, you could put void into this. You don't have to put void though. So you only want to define a function once. That's why you use the those header guards is what they're called. This pragma once thing and the if n define stuff that you saw, those are what's called header guards. Now, finally though, double.h, now that we finally got through including a file, let's do something with double.h. Let's say it has a function called add1, right? And this takes a const int const int reference a, and it returns a plus 1. Down here we could just say add1 12, and then let's run this, and you're going to see we get 13. Remember that when we copy over the contents of double.h, we're actually copying over the contents of double.h. This is not in some double.h namespace. We don't have to put double.h and then the scope operator to signify that it's inside of the double.h file, because this all the contents of the double.h file is just copied over to this file, so it's natively included. This is just like if this function was inside of this file, except it doesn't have to be it doesn't have to be in this file taking up so much space and looking ugly. And that's what header files are generally used for. Header files a lot of the time will contain a lot of functions and a lot of classes and a lot of different objects and stuff for you to use that will be and they'll be declared in the header file and defined elsewhere. So they might declare a whole bunch of functions that do a whole bunch of stuff, and you can look through the header file and see what the functions take and what they return, but the actual logic for how the functions work will be elsewhere in some type of file that's already compiled, like a DLL file. So, for example, this double.h might be declared like that in this file, but it will not be actually defined in this file. This would include another file somewhere else that's already compiled that would define this add one function, define the actual logic for it. So header files are a means of distributing functions and distributing classes and distributing objects to people without distributing really your whole library and code base. It's a way to allow them to look at all your stuff without them having to go through all the actual definitions and all the logic and all the code on how everything works. It just the names of the functions, what they take, and what they return. In this case, we are defining a function in this header file just because there's not much of a reason to do anything else, because our function right here is already is very simple. We don't have to define it elsewhere and then declare it here, so we can include it in our tutorial.cpp. Let's get rid of this double.h file. Let's remove, press delete. Let's take a look at what is going to be the next thing that we're going to talk about. We talked about preprocessor directives. We talked about header files. Let's talk about the let's talk about classes. But before we talk about classes, I'm going to go take a piss. So remember previously we had at a certain point a struct object that we created that was a book. Right? This time we're going to create something called a class, and this is going to be a class called a book, and this book will include let me actually change the syntax. I don't know what the preferred proper syntax for a class really is, but this class will have first a specifier called public, and I guess our Visual Studio wants our public to be right there, and in this public section, let's say we have we're going to have some functions. We're going to have a get we're going to have a double get price function. And this function, all it's going to do, let's define it like this: return price. And let's do that. And we're going to have another function, and it's going to be right down here. It's going to be called get title, and we're going to have one more function, add price, and we forgot an R. And this is going to take a object of type, it's going to take a const int or a const double reference, and it's going to return what it's going to do is it's going to say price plus equals P. Now we don't, I'm using this price and title terminology, but we don't have anything called price or title or anything. Let's say title right here, and we're going to create something else down here. Call it private. We're going to say double price equals 0.0, and std string title equals this empty character list. Now at the top here, we're going to have to include string and why is that not working? Oh, that's because that's a double. You notice we have to put std string here because we're not putting any using string or using std string declaration up here. So this almost acts like a struct. It creates a data type called book, and this book data type is defined by whatever is right here. Now, if we go to tutorial.cpp, we'll see that what we can do is we can say include, it's called header.h, and this is going to include our book class, and we're going to create a book data type. So we're going to say book 1 there, and then what we're going to put right here is we're going to put cout book 1 not get price. All right, let's do that. We get 0. Okay. What if we say book 1 dot price not add price? Oh, remember, we can actually, I don't know why I'm saying remember, because you guys don't even know yet. We cannot access any of the data inside this private section of the book. And so I created this add price section to do that for us. Add price, and we're going to say 10. And let's put this here. And then once we print out the price, we're going to see that it is 10 now. Book.add price must return a value. That's because this needs to be a void. And right here, that adds 10. So what is going on in this what is exactly going on here? Well, we create a book. We create a book data type, and we call it book 1. Let's check what a book data type is. Well, book data type is what's called a class, and there's structs and classes. I said that a struct is a data type that only includes data, and a class is a data type that includes data and functions. So right here, these are what is called class functions. So get price, get title, add price. These are all called class functions. Remember when we did string word equals Geobor, and then we called word dot size, and I said that word dot size is a class function. Well, in the string data type, they defined a function like something like this, and they called it size. And so you can use the dot operator to look inside of the word object for the size function. And that's the same thing with right here. We can use this dot operator to look inside of our book1 object. Our book1 object is a type book right here, and we're going to look for the get price function, or add price function in this case. Well, add price, let's see what it does. It says void add price. It takes a constant double reference p, and it adds and it says price plus equals p. Well, that means that what it's doing when we call this add price function, we're putting in 10, and what it's doing is it's taking that, it's using that as a parameter for this function, and it's adding 10 to price. Well, what is price? Down here, price is this object within the book class. Price is a member of the book class. And what you notice is we don't have to put something like book or book price or anything like that. We can put book price, but since we're within the book class, it automatically knows that what we're talking about is the book class, because we're already in the book scope. So it already knows by price, we mean this price right here that is within the book scope. For example, I could say this book1 object is not of type book. It is of type book add price. This book1 object is not an object. It is a function called, it is of type book add price function, and it's called book1 because add price is a member of the book class. It's within the book scope. That's not what we want to do right now. That's probably almost never useful to do something like that. So we're just going to create a whole book class. And in this this add price function is a member of this book class. So when you call book dot add price, it'll look inside this book class, find add price, and it'll do whatever add price is. And price right here adds whatever you put in for the parameters to price. Price down here, since we're within the book scope, we can just directly access price without putting book with the scope operator and then price. Down here, why can't we, for example, say book1 dot price equals 20? Why does that not work? It's going to give us an error. Or book1 not dot add price. We just want book1 dot price. And nothing, this is not working. Well, this is because this is the price member of the book class is within this private section. This means that this private section, only other members within the book class can access this private section right here. And so this void add price function can access this private section, see price over here. It can take price, it can add whatever it wants to it, and now book.price is going to equal that. Imagine we want to get the price. We go down up here to the get price function, and this get price function just returns back price. So down here, when we call the book1.getPrice function, well, it looks inside book1, it finds price equals 10 because we added 10 to price using that add price function right there. So when we call get price, it's going to return 10. These variables right here, they don't even have to be in the private section. They can just be in the public section with the rest of them. That's not an issue. And now, since they're in the public section, we don't have to call the add price thing. We can just say book1.price equals whatever we want it to be. And instead of calling book1.getPrice to get the price, we can just say book1.price. And book1.price is not a function that returns price. It's just a double value that is equal to the price right here, in this case being 69. And as you could see before though, for these functions up here, this add price function, it does not necessarily, the price variable over here, the price object, doesn't have to be within the private section for this add price function to work. This add price function can work regardless of where that price variable is within that class, unless this price variable is within another class. So, you know, if you, for example, if you had a struct Geobor, and then you did something like this and something like this. Now this can't find price, this can't find title, this can't find price, because this price object is within the Geobor scope. So if we wanted to find price, this would be within Geobor price, and it automatically did something dumb like that. But generally, we're not going to be doing weird stuff like that. That's just kind of strange to be trying to do, like create classes inside of classes, so we don't have to much worry about that. Well, let's actually control Z our way back to where there is no struct. Now, why would you include a private section such as this one right here? Well, the reason to include a private section is, for example, if you do not want whoever is using your class to be able to change the data just manually. You don't want them to be able to set price to whatever they want. You want them to have to go through your add price function, because your add price function might do some very specific set of tasks that that you need to do to be able to properly increase the price. If you had a much more complicated class, you might have to do something like that. And so you want them to go through your add price function instead of just manually setting the price, because if they manually set the price, they might just mess something up. And that's why data would generally be in the private section right here. Now, if we go up to if we go up to this section right here, we see public and private. So these somewhat look like the, if you remember, the in a switch statement, which was switch like this, and it had a variable like 1, and it had a block like that, and it had something like case, which looked like a header like that. And I called it a header because it was case 1, and there was case 2, and these were all like headers. it's the same thing with classes. These are only headers. Everything within this block right here is the same thing. Everything can access, everything within this class can access everything within this block. But when you are limited to a specific header, then that's when you are limited to either the private or the public or whatever functions that you get right here. Let's see, what did I want to do? And these functions and such can do pretty much whatever you want them to do. They can even print out something. So, for example, this function itself could, instead of returning price, we could say that it's a void function, so it doesn't return anything, except it just calls std cout price. And then we would have to include namespace std up here. Or not include namespace std. We want to include the IO stream. When you're including files in a header file, generally put them below your pragma once or your header guard, the if and define, then define this type of thing. Put them below that because if they're defined, you don't have to have the preprocessor check through these again. You can, by putting them below here, you can avoid the preprocessor checking through these again, pretty much. And yeah, that's generally how classes work. Let's demonstrate this getPrice function though, because I did not demonstrate it. Add price. Ooh, one thing I wanted to do is also say constructors, which is the last thing I'll talk about. We're just going to say 69, and we're going to call getPrice right here. Remember, getPrice no longer returns a value. All getPrice does is it actually prints out the price right here. So without even calling print on getPrice, we should just get the price printed out right there. Yep, 69. Epic. Nice. Last thing I want to do is, if inside of this public function, or inside of this public header, imagine you have a function just called book. And this is what's called a constructor function. And let's say that this constructor takes in a const double reference p and a const std string reference p, and this is going to be s. Now at the end of this function right here, we're going to put in some nice little brackets like that. And within these brackets, we're going to say price equals p, and we're going to say that title equals t. So this, or not title equals T, title equals S. So what this does is it's going to set the price to whatever P is. It's going to set the title to whatever S is. So whatever we put in for S for this function, that's what it's going to do. How do we call this function though? Do we say does this work? Let's see if this stops yelling at us now. It might. Now it stopped yelling at us. So generally, you saw I set the default values of the price and the title by just setting the values down here of price and title by default. Generally, what people do when they're actually making functions is they make something called a constructor function. This book function is what's called a constructor function, and it's automatically called. This function is automatically called whenever you create a book object. So right here we're creating a book1 object, and it will automatically call the constructor, right? This constructor, it was yelling at us previously because we did not provide any default values for it. So if you do not provide any default values for the constructor, then the constructor doesn't know how to make your object. So right here, this is going to print a 0. Now, right here, if we do not have these default values, then this is going to start yelling at us. It says no default constructor exists for class book. And what that yelling is saying is that it does not know how to make a book object. It does not know what to do, because we have a book constructor right here. So it's assuming we're trying to use this constructor to create a book object, but this constructor didn't have any default values, and we didn't provide any values for it right here. So if you want to initialize a book like this, then and have constructors in your thing, you're going to need to provide default values for your constructor, so it knows what to do. We can also say book1 equals 19.99, comma, the adventures of Geobor. And if we run this, we're going to see that we get 19.99. The way that this works is when you have a constructor included in your class, you don't have to have a constructor. If you do not have a constructor included in your class, it'll just default initialize all your variables. But when you have a constructor included in your class, it's assuming that you're trying to use this constructor to set all the values pretty much for your class, to get everything ready for your class. And so this constructor will be called every single time that you create a new object of that class. And so right here, when I created a new object of that class and it had no values put in for the constructor, it was trying to call the constructor because it has a constructor to be able to construct the object, but we didn't provide any values for the constructor to be able to construct anything. In this case, we're providing these values for the constructor to be able to construct the object, and what the constructor will do is once the object is created, it'll see, okay, what did you put in for the first parameter for book 1? Well, you put in 19.99, that's going to be P, right? So it's going to set price to P equals 19.99, so price is going to equal 19.99, and it's going to set S to the adventures of Geobor, and title is going to equal S right here. The object is constructed, everything is set to what it needs to be. But when we didn't have these default values right here, it was we both had a constructor here to construct the book and did not have any thing to put in for the constructor right here. So when it creates this book object, it's going to try to call the constructor, but it doesn't have any parameters to put in for the constructor. And so the way to avoid that is either do not make a constructor or provide default values for this constructor, which is generally what people do. Generally, this constructor will have default values like that, and you can override those values with whatever you need to put in like that. And if this constructor does not have default values, then it's just going to be it's going to have to require you to put in parameters like that. So our constructor currently just sets the price and sets the title of the book. Now, is there constructors for other classes? Like, do other classes also have constructors? Yes, they do. So let's take an example of another class that has a constructor. String word equals I'm just joking. No string word equals Geobor anymore. This time we're doing string word, and we're calling the constructor on word. This word constructor, it should tell us what values it takes in. I'm not exactly sure if it's gonna do that. Let's put in that, and let's see if this works. And let's see out word. This prints out a single n. If we put 3 right here, it prints out 3 n's. This is a nice method to just make a string with whatever amount of n's or any character that you want inside of it. And the way that this works is when you create a word, generally, it has a default constructor that assigns nothing to the value of the word, but or strings rather than words. But we're calling this constructor right here manually to specify these parameters. And these parameters that this constructor takes is, first, the amount of characters that you want, and 2, the character that you want. So we're saying that we want to construct, we want to set the value of word to whatever this constructor returns, and this constructor is going to set the value of word to 3 G's, because that's just the parameters that it takes, and that's what it does. And that's just defined by the string class to do that. And that's the constructor that does. When we put in nothing, it uses a default constructor, and the default constructor sets the value of the word to an empty string. So by default, that constructor just sets the value of word to that. That's classes and constructors now. We got preprocessor directives, got header files. Now we're going to do vectors, and that's going to be the last thing. So we're going to do vectors now. A vector is a very, very useful object. Let's actually just delete our header.h file right here. Just press remove and delete. And let's get rid of this. We're going to include vector right over here. And in this vector, or with this vector, what we're going to do is we're going to make a vector. So right here, we have for int I equals 0, I is that we're going to say strings dot push back. We're going to do strings dot push back Geobor, and do that. Then what we're going to do is we're going to say for string s in strings or we don't have to put std. And we get Geobor printed out 100 times, which you love to see it, man. Geobor is just such a great word. So what exactly is this doing right here? Well, we're including vector right here. We're saying using std vector. Vector is what is called a class template. So vector is like a class almost, like that book class that we made, except it's a template of a class. Because when we use a vector, we define our own class to make. I'll explain that a little bit later, but we define our own class vector and we call it strings, right? And now strings is a class that was created from the vector template. And down here, what we're doing is 100 times we are calling the pushback function onto strings, our strings class that we just created up here. And we're pushing onto that. We're putting in the parameters for that pushback function, Geobor. And then right here, we're printing out every single string. So what exactly does this vector strings thing mean? Well, vector is the name of a class template. Vector is like, you can think of a template as literally what that is. It is like a pseudo class. It is a class that's not finished. You need to provide it some extra information to finish it as a class. And so what a vector does normally is a vector is a list, like an array, except an array, you normally have to say that array is 4 long or 5 or 6 or 7 long. The vector class, what it is, it's a class that dynamically allocates memory so that you can constantly add stuff to it. So in this vector class, this vector class will create a class that will act just like an array, except we can add stuff to the array and remove stuff from the array. Using this pushback function, it adds this Geobor string to the end of the array right here. This string right here, inside these angled brackets, this is what we have, the information that we provide for the vector template to create our strings class. And we provide the data type string because we want to create a vector of strings. And so when the vector template sees that we put in that data type of string, it will create an array that holds strings, and we're going to call that class that has that array, that class that is that array. We're going to call that class strings. And then we can call this function on that class, and we can iterate through that class right here, and we can print out all of its contents. You can also subscript strings like string 0. That will work. And you can call an iterator on it. So if you remember how iterators work, iterators would be like string str. You would do auto it equals strings dot end. Generally, remember how the string class itself, the actual class right here, string, std string, that class also did have a .end function. Vectors also have a .end function that also returns an iterator, so you can return an iterator from a vector. A vector has very similar properties to a string, except you define, instead of a string includes only char data types, a vector you define which data types it includes. And the reason that you have to define which data type it includes, the reason why it's a function template and not just its own class, is because you have to define which data type inherently that this function or that this class deals with. So instead of making a whole bunch of different class, like instead of putting vector strings for strings and then vector ints for ints and then vector doubles for doubles and vector floats for floats, they just created a class template to allow you to decide which type of data that you're working with inside of your vector. And what this allows you to do is something like this, for example. If we do struct book, and we can put price equals 0. And we're just going to put price as a double price equals 0.0. And this book object is its own data type. So we can say that this vector is a vector of books, and we can call it books if we want. We can create a books class that is a vector that holds books, which it could be super useful for various things. And we can call the same functions on it, because despite the fact that it now holds books, we can call books.pushback, because this is the same class, just holds books instead. So it has all the same functions. It just has all those functions in relations to books this time, because we defined the class template to use books. And we're not going to go into how to define class templates in this video, because this is getting very long. I started at 7 this morning and I'm at 9 p.m. So we're going to do class templates. We just finished vectors. So right here, vector is an iterable object that you define a data type that it holds, and it creates a iterable list array type object that is dynamic and can increase. Now, there's actually one more thing I want to say. Vectors have their own we're actually going to call this words, and we're going to get rid of this struct. Vectors have their own constructors. So since vector, this vector creates a class, right? A class words. Words will have its own constructor as well. So let's create let's use the constructor of words. So what if I put, for example, 3 Geobor? Then we did 4 we get 3 Geobors. The reason is because we're calling a constructor on this words class that we just created. This constructor says that create 3 objects of type of Geobor. Now, that constructor might be nice, but it is oftentimes inefficient. And the reason that it is inefficient sometimes to use a constructor like this is it is a lot of the times more efficient to use the words.push back function in a loop, for example. If you're going to be adding 100 objects to it, it's better to use the words.pushback function, because the words.pushback function copies the values into the vector, while using this constructor will if I put example 100 like that, this will call the constructor for a string literal 100 times. If we, for example, put into a loop words.pushback, and we had a loop that ran this 100 times and just copied Geobor into the vector, we wouldn't be constructing the word Geobor 100 times. We wouldn't be calling a constructor for Geobor 100 times. We would just be copying the word Geobor to the vector 100 times. And so oftentimes, instead of using a constructor or initializing a vector like using a list like this, so instead of doing this 100 times, this is often inefficient, because for every single one of these, you'll look at this Geobor string and call the constructor to construct this Geobor, then this Geobor, then this Geobor, then this Geobor. And if we just used words.pushback and then continuously copied Geobor to it, it wouldn't have to construct Geobor 100 times. It would just copy Geobor 100 times to it using some type of for loop. One last thing I want to mention, which I forgot to mention previously, is whenever you create struct or class objects in their bodies, after the curly bracket, they require a semicolon. So classes and structs require semicolons, for loops, ifs, and functions do not. Finally, with that being said, we're going to make a final last program, and then we're going to discuss some compilation settings, and then this tutorial is finished. We're on the final stretch, gamers. So what we're going to be doing for our next trick is we're going to be going to this website. This is from a guy named One Lone Coder, which is he's a YouTuber, quite a nice YouTuber. You should check out his videos. He made this game engine right here called the Pixel Game Engine, and it's a very simple 2D game engine. So let's right click this, and how would you get this game engine? Just look up Pixel Game Engine on Google and go to this site. You're going to be brought to a page like this. Just click the GameEngine.h file right here, and you notice that it's .h. .h is a header file, so this is a header file. If we click up here, raw, it's going to bring us to something like this. Let's save page as, and we want to go to see users, your profile, source, repos, and whatever project you have. Actually, whatever project you have, repos, the name of your project, and then the name of your project again. And this is finally where you want to save it. Just save it as all files. And now, right here in the header file section, we're going to press add existing item. Just double click pixelgameengine.h right here. I'm going to do Ctrl, Ctrl Shift, comma, to zoom out a little bit. And so you can see that he has a lot of weird looking code that we haven't quite learned, but some of this we've learned. And we can kind of figure out how this works. We don't really have to know how it works exactly to use this though, which is nice. What we're gonna do is we're gonna go back to that site once again, this site, and he has example program.cpp. Let's just go into here. Let's just copy this, because this right here is just the basic template for a program using this Pixel game engine. Now let's clear out some of the fluff in here so we can see exactly what is going on. All right. So right here, we have a preprocessor directive. It says define OLC PGE application. This would be used by other files that are interacting with your file to see that, oh, your file is in fact a Pixel Game Engine application. And this preprocessor directive, just when you define it right here, it is just telling other files that, because this Pixel Game Engine.h might check, is this defined? And if it is defined, then this Pixel Game Engine does stuff. And if it isn't defined, then that Pixel Game Engine doesn't do stuff. And so he defines that right here, just to make sure this is a Pixel Game Engine application. Now, right here, we can see that we have a class example, and it has this colon operator, and it says public OLC Pixel Game Engine. Let's not worry about what this is right now, but I'll explain to you very briefly what that is. This means this colon operator and public OLC Pixel Game Engine means that this example class right here is derived from the OLC Pixel Game Engine class. So it copies most of the Pixel Game Engine class into the example class. And if we control and click Pixel Game Engine, we'll see this class Pixel Game Engine right here, and it has a lot of different stuff inside of it. And so let's go back to tutorial.cpp. So that means that this example class includes all the stuff that are inside this Pixel Game Engine class right here. And so and that's just how this game engine operates. Let's rename this example to window, or let's call this our game window. Let's replace, wait, no. And I'm going to put this as so what is going on here exactly? Well, we're defining a class called game window, and it is derived from this Pixel Game Engine class, so it includes everything that's inside this Pixel Game Engine class. Right here we have a public section for the constructor, and this constructor just constructs various stuff that this Pixel Game Engine class might need to know. So it says that sapp_name equals example, and if we check by pressing F5 what sapp_name is, sapp_name is actually just this little thing at the top right here that says example. Let's close this. We're going to change that to tutorial. I'm going to press F5. and this is gonna say tutorial now. So that's what that constructor does. That constructor just changes the name of that right there. Let's change this back to debug instead of release. To be perfectly honest, I don't know why there's two different public sections. It doesn't really matter though. And it has two functions. So it has this on user create function, which returns a boolean, and that boolean is true. And it has an on user update function, which takes in a f elapsed time parameter, and it returns true, and it returns a boolean. Well, let's not worry about what these override keywords do yet. Down here, what we're doing is we're creating an instance of this game window class called tutorial, and then we're saying if tutorial.construct, this .construct presumably calls the constructor, and this start presumably maybe calls the onUserCreate function. I'm not exactly sure, but this is how you would start, just however this person decided that this is how the game engine should be started. He created a function to do the construction and a function to start it. So this construct function takes a lot of nice parameters. For example, height and width of your application. So I'll just put 1,000 by 1,000 pixels. And I'm just going to say each pixel takes up one on-screen pixel. So one on-screen pixel in the X direction and one on-screen pixel in the Y direction. And this 1,000 is 1,000 in the X direction, 1,000 in the Y direction. Then we're going to do a comma. The next variable to put in is a boolean for a full screen. And these presumably, they don't have to be put in because they have default values. Like by default, full screen is set to false. Let's just set it to false here because I'm actually trying to get to the value after that, vsync. You can set that to false or true. In my case, if I set that to true, that would limit the game to running at 165 frames per second. And if I set that to false, it would be, over 1,000 probably, because we're just creating a black screen. So let's keep these at false for now. So we call to run his game engine, you call the construct function, then you call the start function, and you return 0 from int main. Int main, after this tutorial.start function is finished, int main returns 0 and then signifies that the program is finished. Most of the action on this program, though, is going to be happening inside this class, though, because this class defines a whole bunch of functions for us to use. So some useful functions are the onUserCreate function. So, for example, we can say onUserCreate. Let's do something on userCreate. Let's say that we create a struct, and let's call it line. And in this line struct, we're going to have v1 x equals 0, v1 y equals 0. And these are both going to be double. And then we're going to do v2x equals 0 and v2y equals 0. So this struct right here is going to be created after this onUserCreate function is called. This onUserCreate function is presumably called somewhere inside of this pixel game engine.h header files somewhere. But what I know is that when I start this program, I know that this onUserCreate function will be called. So right here, I can define a struct line to create my line objects, and each of these I'm saying is going to have a vertex 1 x position and a vertex 1 y position. Then it's going to have a vertex 2 x position and a vertex 2 y position, because as you can imagine, a line has 2 points, and each of those points have an x and a y position. Next, we're going to put right here hashtag include vector, and we're going to create a vector right here. We're going to say vector, and this vector is going to hold lines, and we're going to call it lines. And we have to specify std vector because we didn't put any using statement at the top. And there we go. So now we have lines struct, and we have a vector class of lines. Now let's define one more variable. We're going to say that we have a line called current line, and I'm actually going to rename this lines to be lines pool, because it's going to be kind of where we store all of our lines, and this struct is going to be capital L. So right here, we're creating a struct called line, and it has vertex 1 x position, vertex 1 y position, vertex 2 x position, vertex 1 or vertex 2 y position. Then we create a vector of lines. We call it lines pool. Then we create a standalone line object called current line, and we'll see what we use those all for. Down here, let's say if get mouse get mouse 0 dot be pressed then we want to say current line dot v1x equals get mouse, or actually we're going to change these from doubles to ints. So because I remember this get mouse function right here returns an int. So right here we're going to say get mouse x. Local variable line current line. This theoretically should work. Current line is undefined. Let me check. Is that because presumably the reason that this current line is undefined is because it might be that this onUser update function is called before this onUser create function. And so what we might have to do is instead of having all these things in this onUser create function, we might just put them outside of any function. So let's put them. Oh yeah, yep, I see what that means. It was my mistake. So the reason that didn't work was that we put them inside of a function, right? Remember that functions are outside of scope for stuff that is not inside of the function. So all of these were outside of scope for this onUser update function. Now that they're right here, though, they're outside of the onUser create function. This means that the onUser update function can see them. I'm going to do Control-Shift period to zoom in a little bit. So let me finish this. We're going to say and we're also actually going to define another variable right here, just a Boolean variable called vertex num. And this vertex num variable is going to be equal to true. So this is what that whole program does. It lets us just draw lines on the screen. And I don't know how much you guys have been following, but we'll take a look at exactly what this does. So starting right here, I talked about the struct lines and this line current line, and this Boolean vertex num. What this Boolean vertex num does is when we are creating a line like we did on screen, we have to click twice at the first vertex and the second vertex. So that vertex num, since there's only two positions, there's either two states. We're either drawing the first vertex or we're clicking the second vertex for a line. We can use a Boolean to represent that. You can, because there's only two states, either the first vertex or the second vertex, and we can represent the first vertex as true and the second vertex as false, for example. And so we're using this vertex num to represent whether we're drawing the first or second vertex, and we'll see exactly how we're doing that right here. Right here, we see if getMouse.bePressed, getMouse0.bePressed. So getMouse0, well, let's see actually exactly what's going on here. We have a dot operator right here. This dot operator tries to find the bePressed object inside of the getMouse function. So, or inside of whatever's on the left-hand side. The getMouse function, that will return presumably some type of mouse object, and that mouse object or something similar will have a bePressed object inside of it, and that bePressed object is a Boolean value. So getMouse0, what it does is it returns probably an object representing the 0 being the left mouse button, 1 being the right mouse button, 2 being the middle mouse button. and so on. So get mouse 0 is a function that returns the mouse, some type of mouse object that has a B pressed object inside of it, and so we access that .b pressed object. That B pressed object is a boolean, and you can tell that it's a boolean just by looking at it, because whoever this guy is he decided to preface his variable name just by putting a B right before it. So B pressed to indicate boolean pressed. And so if this evaluates to true, then it'll execute what's in here. Well, when does this get checked? Well, the onUserUpdate function right here, this function is a function that is called as fast as the program can run it, just every single frame. And you can figure out this stuff by reading the documentation on that GitHub page that you downloaded this thing from. But this onUserUpdate function just runs as fast as it can. And so every single time it runs, it'll check, okay, is this true? And if it is true, then it executes this code. If it is not true, then it does not execute this code, whatever is in here. So you can imagine when I click, this boolean .b pressed probably evaluates to true. And so it goes through this code right here. This code right here, if we check what it does, is it says if vertex num. Remember, vertex num is up here. We have a boolean vertex num to check, are we saving the first vertex or are we drawing the second vertex? And the way that we check if we're drawing the first vertex or the second vertex is we just check, okay, if vertex num, so whatever vertex num is, true or false. So vertex num in this case is going to be true. So if vertex num, which is true, then current line dot v1x, which is this line object, current line dot v1x, which is vertex 1x that I just defined as being vertex 1x. That's what I decided would be vertex 1x, equals getMouseX. GetMouseX is another function just provided by this Pixel Game Engine header file, and that getMouseX will just return the position of the mouse on that screen. And then we also say with a comma right here, we say that current line dot v1y, so vertex 1y equals getMouseY. So it saves the x and y position of the first vertex to our of our mouse to our current line object right here. So this current line object just holds the current line that we're creating. In this case, the current line that we're creating would be whatever we're assigning our mouse inputs to, and we're assigning our mouse inputs to current line.v1x and current line.v1y. And then what it will do after it assigns the position of your mouse is it will flip vertex num. So vertex num equals not vertex num. Vertex num equals the opposite of vertex num. And if you remember, this exclamation mark is the negation operator, and it returns the opposite of whatever is on the right hand side. And so if vertex num is true, it's going to return false, and so vertex num would equal false. And then when the onUserUpdate function is called once again, it'll check, okay, is the mouse pressed again? If it is pressed, then it's going to check once again, okay, is vertex num true or false? Pretty much is if vertex num in this case would be false because we reversed it right here. And so it would go down to this else statement right here. And this would save the positions of the second vertex in our current line object. So in our current line object, we're going to save the positions of the first vertex initially when vertex num is true, and then the second vertex when vertex num is false. And then immediately after that, we know once we save the second vertex that our line object is finished, right? It has both vertexes. And so we do lines pool, which is our vector up here. Lines pool push back, which is a class function on lines pool vector, current line. Current line is our object that we were saving all our values to. So current line dot v1x. And then down here, after this whole if statement, we have a for loop that is inside of the onUserCreate loop. So inside of this onUserUpdate loop, we have another loop right here. And this loop will go through every single line. So line S inside of lines pool vector. And it will call this draw line function on every single line. And that draw line function takes several parameters. First, it takes the position of the x position of vertex 1, then it takes the y position of vertex 1, then the x position of vertex 2, then the y position of vertex 2. And since we saved all those back up here, and we added that current line object, we pushed that into the lines pool. Right now, the lines pool has a line object that has all those values saved to it. We check that inside of that line object, inside of the lines pool, for all of these different values, and we put them in as parameters to this draw line function. The last parameter right here is pixel color, and this color is just defined inside of the namespace OLC, which is the guy who made this is one lone coder. OLC stands for that. And he has the OLC namespace, and red is a some type of variable in that namespace that defines the color of the pixel, presumably. And then once we do that, this means that every single update on here, it's going to check whether we click, and it's going to save those clicks to either vertex 1 or vertex 2, and then it's going to add that line that we just created into the lines pool, and then it's going to draw every single line in the lines pool. So overall, pretty simple, pretty easy to do. And we press F5 to build it. We can see we're getting 1500 FPS and 1800, 1700, whatever we want. And this just lets us create lines right here. Now, there's one other thing I want to show. You probably remember I said that lines have vectors have iterators, and so we're going to be going through vector iterators right now. So we're going to say for auto it equals lines pool dot begin it does not equal lines pool it would actually be like this, the syntax. Come on. Lines pool dot end and I should probably do that. We're going to also do ++ iterator. And then instead right here, so if we remember correctly, this S, we can no longer use this S because this S was a line object that was defined by the for loop. Now we only have iterators, which are pretty much pointers. So imagine these pointers point to line objects, right? So what we could do is, I imagine we could put dereference iterator dot v1x. And if we try to do that here for all of these instead of s, because you can imagine s was a line object, right? Now to get those line objects, we have to dereference this iterator, because this iterator holds the memory address to the line object now. So we dereference it and get v1x. The issue is this dereference operator is applying to this whole statement. This dereference operator is trying to dereference the result of it.v1x, and it doesn't know what it.v1x is, so it can't dereference that. The way that we fix that is you put parentheses like this. And now this is saying inside of dereferenced iterator, find v1x. So v1x inside of iterator dereferenced. Iterator dereferenced returns a line object, and so we'll find v1x inside of that line object, which is perfectly fine. Which it is not fine doing it like this, because this will try to find v1x inside of the iterator and then dereference the result of that, which doesn't make any sense. Now there's a shorthand for doing that. You don't have to put these parentheses. It's very kind of awkward and time consuming to have to put these parentheses around it, and it makes it look confusing. So they added a specific operator that automatically dereferences and finds and combines the dereference and the dot operator, which is this operator. So this arrow operator, what it does is it dereferences the iterator and then returns the v1x member of that iterator. And so instead of using that dereference operator and that dot operator and the weird parentheses, we can just use this arrow operator. Run F5, and this works exactly how you would expect it to work. One last thing I'm going to show you is just options within Visual Studio for this. So you saw we were running it in debug mode. Once you're finished your project, you probably want to switch it to release mode, and maybe if you're making a 64-bit application, you can change it to 64-bit mode, and then you can press Ctrl F5 to run it just in release mode without any debugging options. And this will usually have a higher frame rate. Right now the frame rate is not really noticeable being any higher, but a lot of the time this will run your programs much more efficiently, and that's because it puts in place optimizations that it does not put in place when you run it in debug mode. Like if you know, for example, what AVX is, it will try to implement AVX instruction sets into running your programs. Another things I want to show you is in tutorial right here. If you click properties, you get this window right here. What you want to do is probably go to all releases or all configurations, and what you can do is you can change the standard of C++ that you're using. The C++ standard is pretty much just like what version of C++ you're using. By default, it's set to C++ 2014, which is C++ 14 right here. But there's also the newer C++ 17 standard, which we can use, and it adds a whole bunch of new features, which when you get more advanced in C++ you would learn. And then there's C++ 20 right here, which this is just, it says preview latest features from C++, but really that is mostly C++ 20. And the reason it says preview latest features from C++ 20 is because C++ 20 only came out like a month ago. So the compilers are not 100% updated. You can do the same thing for for C, which is the language that is before C++. You can do the same thing for C right here. Say that you use this C language standard instead. And inside of what was I thinking about? Right here is another option for C++ language standard. And you can just press apply now, and it will use the latest standard of C++. This one last thing, this all configurations button just is whether you want to do release, debug, or all configurations, and we're doing all configurations, so we're just going to do that. That really changing to the C++ 20 standard shouldn't really affect our program at all. It's going to do the exact same thing. So, yeah, that is the finished for the tutorial. Hopefully, my hope is that you gained a more fundamental knowledge of how everything interacts and works with each other, rather than a lot of the other tutorials which fail to explain things in depth and why things work and all the intricacies of everything. My hope was that this tutorial covers all of that, rather than just the code itself. So knowing all this knowledge from this tutorial, watching other tutorials should be much easier. You should be able to skip through things. You should be able to intuitively understand exactly what's going on in those tutorials now that you know pretty much all the fundamentals of what's going on here.